This is what they're talking about. We used an analogy of two ports seamlessly or being configured to work together. This could be switch number 1. This could be switch number 2. You could have a whole VLAN that comes off this switch as well as this one. And what you want to do with connecting these two by enabling the ports, configuring them, let me tell you exactly what's happening. I'm basically opening up an information highway for switches to move information back and forth at will. Super speed highway. And anytime information goes through a switch, it has to look in the CAM table. It looks in the address table. But what happens is, if you got a whole bunch of computers looking in the address table here, then it looks in the address table here. If in order to find out which port you live on, you're seamlessly taking away bandwidth, vital bandwidth, from the switch and the network traffic. Okay? You're depleting your bandwidth. So with link aggregation control protocol, it does two things for you. The first thing is I can connect two ports directly. I can combine channels. Therefore, I get more speed and I get redundancy. The second thing that this thing does, it says, I don't need Martin to always look in the switch routing table in order to get this information moving. I trust these two devices, so therefore, I will specifically team these ports together to move information between two devices that I own. I don't need network traffic being hampered any more than it is. I just need it to move. Remember that song? We like to move it, move it. Move it. We like to move
Yeah.
it, move it. Right? I know, Mike. It's Monday morning. Yeah, getting you guys going. I'm the comedian for the morning. So that's why we want to just push it. Oh, salt and pepper. Push it. We just want to push that information. Get what I'm saying? 1985, salt and pepper.
Yeah.
Listen. Let me get back on track here. So this is what we're looking at with lack piece. So remember that. So we're going to get into some examples also in Packet Tracer, where we have to do that. Standard Ethernet frames, as a reminder, maximum transmission unit, 1,500 bytes. Can anybody remember what the size is for a giant? It has range, right? We know this is the starting range, but what is it? Yeah, there you go. You got it, Leah. Runts. Size for runts you generally see. Yep, somewhere around there.
30
Small,
to 50.
right? Good to go. All right, this is where we're at today. Spanner tree protocol. We know that with spanning tree protocol, and I don't know if you got to the video yet in SkillSolve, but with spanning tree protocol, what it does, it puts all the switches in what they call a hierarchical order. Hierarchical order. Okay? When you add switches to a network, you'll have the edge. Usually the edge device or edge switch, usually called the root bridge switch, the root. It is the main switch that controls everything before it exits the gateway. So it is the root bridge, okay? When you start adding other switches, okay, there's a packet that needs to go around to each switch. Okay, so let me tell you how this works. Remember when we were talking about those trivial files on port 69? East Charmer said, We have to log into the server. We have to get those trivial files, it's configuration files for the switch. Okay. In order for switches to communicate with each other, okay, they have to sometimes tell each other what they're doing. One switch on a network he don't have anybody to talk to. He's talking to himself. I talk to myself because there is no one to talk to. Okay. So when you start adding additional switches, they have to communicate. So this is what happens. And maybe y'all can relate to this too, Elaine and Mike. Y'all worked on satellites and stuff like that. So they might call us something else. Switches have to advertise certain telemetry with each other when they're on a network. It is called a bridge protocol data unit. Every 30 seconds or so, switches tell neighboring switches, you are correct. They will broadcast to each additional switch. They tell each other, hey, bridge A, 5'9", 250. I could bench 300 pounds. By the way, my bandwidth is. So they tell each other their statistics, their stats, right? You never heard the term till now? Yeah. So they're telling each other their stats in order for the best route to be chosen to transmit your data. So as these BPDUs fly around between these switches, right? So you have the receiving port, you have the bridge port, which is BP, right? And then your transmitting ports. So when it goes out, when a bridge advertises, if something comes into the switch, they rebroadcast the stuff out of every other port, but not the receiving port, right? So they do it on the broadcast ports, right? There's another thing that happens too. Has anybody ever seen this on Twitch or whatever, where somebody shares their screen and it's an infinite screen, just keep sharing with each other?
Yep.
You seen that before?
Yep.
So if I was to share something like if I'm broadcasting and I brought up a screen on Twitch or it's my main screen that's broadcasting Twitch, it keeps going.
Yep.
It's that same screen going on forever.
Yeah.
It looks like a mirror, like a Justin Timberlake video.
Yep, it happens in OB.
Yes, it happens in OBS. You are correct. Yeah. Right? Basically, what you're seeing is it's causing this eternal loop of the screen being rebroadcasted upon a rebroadcast upon a But what? This is crazy. Okay? The same thing happens on the network. They call it spanning tree protocol, or you call what you get a broadcast loop. Let me tell you how this works. You have to be careful when you plug up switches because this is the root bridge switch. Anytime you add, so this is switch number 1, and you get switch number 2, then you can have switch number 3. You'll configure this switch 1 to talk to this switch talks to this switch, and then this switch gets plugged into here. All right? Bridge protocol data unit starts to flow, telling each other stats. Bridge A, 6'1", right? Long hair. I can transmit in less than 2 nanoseconds, right? So they're broadcasting each other. But what happens is, if somebody ain't paying attention, and they'll take this switch and reconnect it back into the network twice, it can only connect once. If somebody's not paying attention and you use a port and reconnect it back into the network twice, it causes a broadcast storm. Now you have bridge protocol data units being broadcasted so fast It fills the network with all of this trash, and all your switches go down. Done.
Oh.
You just created a broadcast storm, which is a bunch of collisions. It's just colliding. Data can't move, and basically your wires are full of trash. All those data segments, all of those bits, packets, frames, packets, segments, they're all clogged up in here. All right? So your switches need a colonoscopy. You gotta turn them off.
Cleanser.
Brings your whole network down. All right? So, spanning tree protocol prevents what they call bridge loops. Bridge protocol data unit, in order for switches to work together, you have to bridge them all together. You're preventing bridge loops. Does that make sense? And it provides fault tolerance. Okay? So when when spanning tree protocol is enabled on a switch, it will recognize if a switch connection has re-entered the network twice, because it reads these bridge protocol data units and the headers on it to say, whoa, buddy, be wheezy. You got hooked up at 9 a.m., buddy.
Yeah.
Why is somebody trying to hook you up again to come back in the network?
Yeah,
Can't allow
reconnect it
it.
again.
And
Yeah.
it gets blocked because it recognizes its packets are starting to go around twice. Okay? The other thing that you'll see is you have to also turn on PPDU guard in a switch. You have to enable that. You have to go in that switch and configure bridge protocol data unit guard. All right? It works with spanning tree protocol to identify somebody trying to sneak into the club twice. All right? Can't do it. It'll be there. It's like your cop, your traffic cop for the network. All right. Any questions on that though? Because that could be confusing sometimes. All right, who wants to take a gander and explain to me exactly what STP is and BPDU guard?
BPS.
Who wants to explain it back to me?
STP.
Just to make sure we know what's going on.
STP?
In your own words. James didn't say it was going to be a quiz this morning. Feel free to dance too. So, do the dances that we did, to make sure,
Yes.
you know.
So security terminal
Charles
protocol.
like, no, I'm not dancing this morning.
What is it? The security terminal protocol. All right.
Charles says it's too early. All right, Mr. T says, let's see what he's got. BPDU guard is blocking rebroadcast to Moving on. Thank you, Mr. T. Well said. Spanning tree protocol, BPDU guard. Way to go. All right, so next topic of concern on what we have here is what they call power over Ethernet. Power over Ethernet. This is pretty cool. Allows one cable to transmit both data and power to network devices, simplifies network expansion. Cool. So you have VoIP phones. Last time I checked, anybody seen a separate plug-in for a internet phone sitting on a desk? Elaine's like, nope. It's like, how does this wizardry happen? Right?
Yeah.
It's magical. You bring it out the box, you plug it into your computer. Why not?
Yeah.
RJ45 jack. I was mystified by it. But it's power over Ethernet. Okay? Where can I find, first of all, before I start plugging in additional items to my computer, what are some things I need to consider? Mainly about power. Well, yes, you're correct. When we start plugging up additional hours that items, and the main focus is power over Ethernet. You are diverting power from the motherboard straight out through an additional connection to help power and move data to an item. So if you start plugging up too many external items to a computer, sometimes it will intermittently turn off and on, off and on. If you have never even checked how much wattage that computer can push, you might be stealing vital energy from the rest of the computer and it can't handle it.
Yep.
All right. So always refer to the manufacturer specs before you plug it up. 9 times out of 10, you're fine. Doesn't take that much. But just to make sure, go ahead and check. All right. Okay. Technician is setting up a new network and wants to create redundant paths. Redundant paths through the network. Which of the following should be implemented to prevent performance degradation?
To
Within the
prevent
network.
performance degradation.
You say 4? Who says 4? Okay, you're right.
Spanning tree.
Spanning tree protocol. There's your redundancy, right? But here's another thing though. Wait a minute. I read this wrong. Look at this. Let's look at it again. A technician is setting up a new network and wants to create redundant paths. You want to create redundant paths in a network.
Would be 2 then.
Which of the following should be implemented?
Would be 2 then.
I would say, well, port mirroring, you could do that. It takes information coming from one port, copies it straight over to another port. It's like tapping a port.
Oh.
ARP inspection would be address resolution protocol that does that anyway in a switch, right?
Yeah, that's a given already. Yeah.
VLAN, variable, right? Virtual local area connection.
Network, yeah.
Hold that thought. So we're saying port 2. All right, let's go to answer number 2 and see what we come with. To improve network resiliency, a network engineer at a medium-sized data center implements multiple interconnections between switches. Shortly after the deployment, the monitoring system reports excessive
broadcast traffic, yeah.
Traffic, and several applications begin to have connectivity issues. Suspecting that there is a loop, which of the following scenarios most likely led to the creation of the loop? There you go, 2. Connecting switches together without activating STP. That motor oil. Now, with one spanning tree protocols, network protocol that builds a logical loop free for Ethernet networks, okay? If a loop occurs, that's what's going to happen. Right here, a virtual LAN, any broadcasting domain is pretty much partitioned and isolated on the OSI. You can do port mirroring, ARP inspection, VLANs. Do not add redundancy to the network. All right. Port mirroring, just send a copy, like I was saying before. It'll go ahead and copy anything coming over from a port. Right?
Yeah.
Here, if you have redundant links set up, it's important to use STP. Now, the way the question is worded, I've seen this question before. That's why I wanted to show you the definitions. The technician is setting up a network and wants to create redundant paths through a network. Okay? You can't do that with ARP inspection. Port mirroring taps a port and sends a copy of what's coming through. Virtual local area network creates segmented, all right? And then you have STP that prevents loops. So does any of these really cover redundancy or redundant paths? If you willingly want to create redundant paths through a network, does any of these cover that?
Not necessarily. You pretty much have to choose the best one there.
Not really.
No.
What happens is, I would say the closest answer, you could do VLAN tagging, and we're going to get to that in a minute. This is on the exam. It's called VLAN tagging. All of these come into play when setting up a network and to set up various other paths through a network. So it will prevent network degradation. But keep that in the back of your pocket, in your back pocket, VLAN tagging. Elaine says mainly to choose the best one, CompTIA hiccups. Yes, it is CompTIA hiccups. Yep. If I would have read this question like I did before, fast, and I was like, oh, wait a minute, I want to. None of these will do it. And then it really didn't give you a firm answer, did they?
Yeah.
No.
Yeah.
It's a combination of all of those. All right, what we got? Any questions so far? I know, Jesus, it's early in the Monday morning. Yeah. Early in the Monday morning. All right. Let's go to switch troubleshooting. Oh, wait a minute. Before we do that, I got something for you. Dun-dun-dun-dun-dun-dun. Let's go ahead and I got this video for you. It's gonna pretty much explain spanning tree protocol. Pretty animated. I like it. Give you another look at it. Here we go.
Hello everyone. In this video, we're going to be talking about the spanning tree protocol. Now, when network devices want to communicate with other network devices, they first need to know the MAC address of those devices. And the way they find the MAC address of a device that they want to talk to is by broadcasting a signal out on the network asking for that device's MAC address. And then once the MAC address is known, communication can take place. So, for example, if computer A wanted to communicate with another computer on this network, it'll send out a unit of data called a broadcast frame. And then once the broadcast reaches the switch will forward that broadcast to every device that's connected to it. Now, in a typical network, you would have a switch with computers connected to that switch, forming a local area network. However, in some cases, network administrators may want to add redundancy to their network in case of a switch or a cable failure. So instead of having one switch, they may use multiple switches. So for example, this network is using 3 switches on this network. So that means that this computer here has 2 options it can take to communicate with this computer over here. It can communicate using this path here, or if this link goes down, it can use this path instead and vice versa. But the problem with having a setup like this is that it could create a problem called broadcast loops. So for example, as I stated before, whenever a computer wants to communicate with another computer, it first has to send a broadcast frame out on the network to find the computer it wants to talk to. So if computer A wants to talk to computer C, computer A will send out a broadcast frame to the switch it's connected to, which is switch 1. And remember, switches will always forward broadcasts to every device that's connected to it. So the switch 1 will forward the broadcast to computer B, switch 2, and switch 3. And then when switch 2 receives the broadcast, it will forward the broadcast to computer C and computer D. But it's also going to forward it to switch 3. And then when switch 3 receives the broadcast, it'll forward the broadcast to switch 1, and switch 1 will forward the broadcast again to switch 2, and then this will continue on in a never-ending loop. And the same thing happens in the other direction. When switch 3 receives a broadcast from switch 1, it'll forward the broadcast to switch 2, and then to these computers again, and then switch 2 will forward the broadcast to switch 1, and then it's rinse and repeat. The whole network will be caught up in a never-ending loop of broadcasts, which is known as a broadcast storm. And when this happens, the network can't do anything because of the constant broadcast, and the entire network will come to a grinding halt. So this is why the spanning tree protocol was developed. It was designed to prevent broadcast loops when multiple switches are used on a network. So the next question is, well, how does STP prevent this? Well, the short answer is that it does this by blocking certain ports on the switches. And so the next question is, how does it determine which port or ports to block? Well, the first thing that STP does is to determine which switch will be the root bridge. The root bridge will be considered the most important switch. And the way it determines this is by having all the switches talk to each other. And they do this by sending out messages called BPDUs, or Bridge Protocol Data Units, out on the network. These units contain information called the BID, or Bridge ID. The Bridge ID consists of the switch's priority number plus the VLAN number along with its MAC address. And STP uses the Bridge ID to determine which switch will...
You will see this on the exam. Bridge Protocol Data Unit, priority number, from which switch is coming from. So the bridge ID, inside that BPDU that I was telling you about, is like these advertisement packets. Remember I told you that? They're advertising to each other, VLAN and MAC address. All right.
B, the root bridge. And the switch with the lowest bridge ID value will be considered as superior and will be elected as the root bridge. So for example, by default, each switch will have a priority value of 32768. And let's say that all the switches are on VLAN 1. So we will add the 1 to the priority value, which will now equal 32769. But since all the switches on this network have the same priority value, that means it's a tie. However, the tiebreaker will be determined by the MAC address. So whichever switch has the lowest MAC address will be elected as the root bridge. So we see that switch 3 has the lowest MAC address, which means that it'll be elected as the root bridge. And the ports on the root bridge are labeled designated ports. Designated ports are ports that lead away from the root bridge.
At Full Sail, our technology programs are designed with a different approach to learning. We let our students get hands-on and start creating.
Now, the next step
Oh, darn it. It's Monday morning. Okay, thank you. Appreciate you. So it's good to know here, designated port, root port, and block port. So when you go in here and turn on spanning tree protocol, it's going to look for these designated port, root port, and block any ports that aren't being used. So you can't create a storm to come back in to the network.
Yeah.
is to determine the root ports. The root ports are ports on the non-root switches, so these switches here that forward data to the root bridge. Root ports are elected by what's called the lowest path cost, which means that the port on the switch that's the fastest link to the root bridge. The path cost is calculated in the following chart. If the link speed is 1 gigabits per second, the cost is equal to 4. If the link speed is 100 megabits per second, the cost is equal to 19. And if the link speed is 10 megabits per second, the cost is equal to 100. So let's say that all the links between the switches are 100 megabits per second. And if we look at our chart, 100 megabits will have a cost of 19. So all three links will have a path cost of 19. So starting with switch 1, it has two paths to the root bridge. This one here, or this longer one here. So this path here has a cost of 19. But this path here has a cost of 19 plus another 19, which equals 38. So since this path here has a lower cost, this port on this switch will be the root port. Because as I stated before, whichever port has the lowest cost path to the root bridge will be the root port.
I'm so glad that came up in the video because I'm about to give you a freebie. There's one question that allegedly pops up on the exam. It'll give you, when we start going into routing protocols, it'll say, with path costs, which one of these has the lowest path cost? Is it OSPF? Is it blah, blah, blah? Or is it a direct connection? It's a direct connection.
Yeah.
It doesn't have to get routed anywhere. It doesn't have a path cost because you plugged it straight from here, straight to there, right? So if you see this type of question and path costs needs to be evaluated, if I'm connecting my computer straight to Michael's, we got the lowest path cost of the whole network. Doesn't have to get rerouted anywhere.
No.
Yep. Okay, here we go. Sorry. Just giving you tidbits.
And the same thing goes with switch 2. This path has a cost of 19, and this other path has a cost of 38. So this path is lower, so this port will be the root port. Now just to give you another example, let's say that these two links here are 1 gigabits per second each. And if we look at our chart, that would give them a cost of 4 each. So going back to switch 1, if we add up the cost of this path, it would be 4 plus 4, which equals 8. And the other path is still equal to 19. So since 8 is lower than 19, this port would be the root port. So this is how root ports are determined. So let's go ahead and put these links back to 100 megabits each and continue on with the lesson. So now that we have our root ports figured out, it's time to determine which of these last two remaining ports are going to be blocked to prevent broadcast loops. And the way to determine which port will remain open and which one will be blocked is again based on the switch's bridge ID. And since the lower bridge ID wins, the port on switch 2 will remain open and be labeled a designated port. But the port on switch 1, because it has a higher bridge ID, its port will be blocked. So by blocking this port, it will shut down this link, which will prevent any broadcast loops. So STP has to go through all these steps to find out which port or ports to block. But if any of these other links or devices were to go down, STP will reactivate this port and bring this link back up. The spanning tree protocol was developed in 1985 as the IEEE 802.1d standard. And in 2001, RSTP, or Rapid Spanning Tree Protocol, was developed, which was labeled the IEEE 802.1w standard. RSTP was an improvement to STP by significantly adapting faster to a failure or to a change in the network. So where STP can take 30 to 50 seconds to adapt, RSTP can do it in under 6 seconds.
That's on the exam. Rapid STP. When they talk about convergence for the whole network, basically, I got a classroom full of kids, which are the switches, right? I come in as a teacher. They're all being rowdy. Sit down. Rapid. They're all getting in order. Rapidly. The other way is it takes long.
And it is also backward compatible to STP.
Trading options can be a great way to generate income, but
most traders out there are relying on... Guys, if you want to do your own little experiment, you can do this to create your own broadcast storm, just to get an idea of what happens. So you just need a standard inexpensive switch with no loop blocking features, plug in your computers into that switch, and then get a network cable and then plug both ends of the same cable into the switch and see what happens. So what's going to happen is when these computers send their broadcast frames to the switch is going to endlessly loop the broadcast. And as it does this, you will see the LED lights on the switch rapidly flashing in sync, which means that this network is in a broadcast storm, and the computers won't be able to do anything. They won't be able to exchange data between them, or if they are connected to the internet, they won't be able to access anything on the internet. So if you try to bring up a web page, nothing will happen. So this is actually a simple way to bring down a local network. But as soon as you remove the cable, everything will go back to normal. So guys, I hope you learned something from this lesson. But speaking of learning, I would like to thank the sponsor of this video, which is...
Okay, we know who Brilliant is. Okay. Let me drop this link in here for y'all. Okay. So for the exam, I like targeted learning. Talks about the root port was T.
Spanish.
RP is root port was DP.
Oh, designated.
Designated port. Then you have the block port.
Mm-hmm.
So these switches, they use a couple of things. Let's recap so we don't get confused, because it's a lot. We have that frame. We have to use that. Frames are on layer 2, right? So they start sharing those frames that go back and forth. Then BPDUs, Bridge Protocol Data Units, they advertise and share. The advertisement is what? When they share that one file with each other to find out who's going to be the root bridge, what's inside that advertisement? What is the name of that goes around and around and around and around? Yeah, the bridge ID, path cost, right? They start using that to figure out, okay, who's going to be designated as the root switch or the root port. So then they'll start converging. They start sending stuff to each other. They be like, okay, they start getting themselves in order. They start looking at path cost. Yes, correct, Kevin. Uses the lowest MAC to determine root port if they have the same transfer rate. Yes. So the cool thing about STP, now, that's why I didn't like that question that we were presented with before we started this. Now you see why? Because if you want to on purpose create redundant paths, technically they were talking about STP. You want to open designated redundant paths on a network. Well, you can, as long as you have STP enabled. So that would have been the right answer for that question. But I didn't like the question because the answers didn't match what it was asking. But anytime you set up multiple switches and you need to start transferring information, you have to have spanning tree protocol for redundancy. Okay. Anytime you see a path come back into the network a second time, it creates the broadcast storm. Okay. So the STP gets turned on, convergence happen. They look at frames, then bridge protocol data units. Then they start putting each other in order. They use path cost to do so. The determining factor, if they have the same transfer rate, is the MAC address. Bam. Then they said, guess what? That takes too long because it can take up to a minute for that to happen when you turn on all the switches. So then they came up with rapid spanning tree protocol. And under how many seconds did they say that can happen?
30 to 50 seconds.
Bingo. 6
6
seconds.
seconds.
Okay. Just know that that's the difference. With rapid spanning tree protocol, it doesn't take you through all the switches and back and forth and determine path costs and all of that. One-on-one,
Asim,
got you.
how are you
One-on-one,
doing?
got you. Nope, this is what I'm determining. Bam, this is what's going to happen. I don't need to talk to everybody. I'm getting my telemetry off everybody, and I'm going to make the decision as the root port. You get what I'm saying? So that's how it's going to happen. You guys are amazing. Thanks for sticking in with me this morning. I know it's after a long weekend. All right, here we go. Well, I need to give you a break.
Is it?
Yeah, let's go on break.
Yeah. All right.
Let's take 10 minutes. See you when you get back.
How are you guys doing? Doing class as usual.
I'm James Messer. Welcome to Professor Messer. We'll start our Network Plus course with a broad discussion of something we refer to as the OSI model. This is referring to the Open Systems Interconnection Reference Model, and it's a model we use in IT to describe the process that data takes as it traverses our networks. The OSI model is not designed to be a detailed description of this data, but instead is intended to describe a broad overview of how data traverses our systems. We're also not describing the OSI protocol suite. Indeed, most of the protocols we use today are based on TCP/IP, but the OSI model is one that we can apply to many different protocols, and it works perfectly with the TCP/IP protocols that we use today. Also keep in mind that there are many different protocols that might operate at an individual layer of the OSI model. So as we step through an individual layer, keep in mind there might be tens or even hundreds of protocols that might exist and work at that particular layer. By understanding this OSI model, we can converse with other people in information technologies in a way that we would all understand. It doesn't matter if they're working inside of your own company or with a different organization. When you mention OSI Layer 7 or OSI Layer 4, everyone understands what that means and what effect it has on the overall operation of the network. If we start at the top of the OSI layer, or OSI Layer 7, and work our way down to OSI Layer 1, we have Layer 7 being the application layer, Layer 6 is the presentation layer, Layer 5 is the session layer, Layer 4 is transport, Layer 3 is network, Layer 2 is the data link layer, and Layer 1 is the physical layer. There are many different mnemonics that people use to memorize this, but if you start at the top and work your way down, you can take the first letter of each one of these layers, and you might have a term such as, all people seem to need data processing. That's application, presentation, session, transport, network, data link, and physical. Let's start our conversation of the OSI model at the bottom of the OSI model, or Layer 1. We refer to this as the physical layer because it's describing the physical signals that we send through the cable and fibers on our network. At this layer, we really don't have many protocols to speak of because we're really just talking about getting a signal from one part of the network to another. When we refer to a physical layer problem with the network, we are referring to the OSI Layer 1 physical layer. This means that we might have a bad cable, a bad fiber, there might be interference on a wireless network, and it may require us to do a series of tests to determine if we are really able to get a signal across this particular wire or this particular fiber so that we can keep this network running. A lot of the troubleshooting that you do at layer 1 is running loopback tests, testing cables and fibers, and checking different adapter cards and other devices to make sure they're working properly on the network. One step up from the physical layer is layer 2, the data link layer. This is the fundamental layer that's used to communicate between two devices on the network. We often refer to this as the MAC address layer because that is the data link control layer, or DLC layer, that is commonly associated with the network cards that are in our devices. And most of the time, these are Ethernet adapters or wireless adapters, and we refer to that physical address on that device as the data link control address, or the MAC address. In this case, MAC address is not referring to an operating system, it's referring to the media access control address. So anytime you hear someone talk about a MAC address, they are referring to the hardware address of that particular adapter card. Since the network switches that we use on our network determine how to forward traffic based on the destination MAC address, this is a layer that we often refer to as the switching layer. So anytime we're referring to a MAC address, a problem with a switch being able to operate, or anything else that may be associated with this particular hardware address, we're referring to OSI Layer 2, the data link layer.
I would describe Underline as fast, affordable, and local. Incredibly fast, very reliable, zero lag.
That's kind of fast.
Consistent, fast, just simple. No brainer.
We put it through the worst, so you get its best. Nissan, #1 in new vehicle quality.
The next layer up is OSI Layer 3, or the network layer. We often refer to this as the routing layer because this is the layer that routers use to determine how to forward traffic. And they are specifically looking at the destination IP address in order to determine what the next hop might be for traffic traversing the network. This is also the layer that we're able to fragment these frames into multiple pieces, especially if we're sending it across a network that may require smaller frames than what is on our local network. So we can cut those frames up into smaller pieces to be able to fit them through the network and then put those pieces back together on the other side. Anytime we're referring to a problem relating to IP addressing, subnet masks, anything related to an IP address or anything about routing, then we're probably referring to Layer 3, the network layer. Layer 4 is the transport layer, and as the name implies, we're referring to the ability to transport information from one device to another. You might also refer to this as the post office layer because this is responsible for getting your letter or your information from one side of the network to the other. The protocols that are often used and operate at Layer 4 of the OSI model is TCP, that stands for Transmission Control Protocol, and UDP, or User Datagram Protocol. These two protocols are commonly responsible for getting all of the information within our IP packets from one device to the other. In many cases, this involves taking a large amount of data, putting it into smaller pieces to be able to get it across the network, and then putting those pieces back together on the other side. Before we can send that information from one side of the network to the other, we may need to create a session so that a device is able to receive that data. Layer 5 is the session layer, and it provides communication management between point A and point B. Anything relating to the initiation of a session, stopping the session, or restarting the session can commonly be associated with that Layer 5 session layer communication. If an application is using some type of control protocol or you're tunneling information within existing data, then you're probably using OSI Layer 5. OSI Layer 6 is responsible for putting all of this data into a format that we will eventually see with our human eyes. This refers to character encoding, application encryption, and decryption, and it's often combined and discussed in conjunction with the application layer at Layer 7. Layer 6, or the presentation layer, is the layer that is commonly in operation just prior to us seeing this data on our screen. And the top layer of the OSI model is OSI Layer 7, or the application layer. This is the layer that we see on our screen. So anytime that we are interacting with an application, we are operating at Layer 7 of the OSI model. Common applications that would operate at OSI Layer 7 are HTTP and HTTPS, FTP, DNS, POP3, and thousands of other application protocols. Well, that's a broad overview of the OSI model, but how do we fit things in the real world into each of those layers? Let's start down at the bottom with Layer 1, or the physical layer. When we refer to cables, fiber optic connections, the signal going across those connections, or a wireless network, then we're operating at OSI Layer 1, or the physical layer. When we refer to OSI Layer 2, or the data link layer, then we're talking about Ethernet frames, MAC addresses, or addresses referred to as extended unique identifiers, or EUI. There are EUI 58 addresses and EUI 64 addresses, for example. And as we described earlier, anytime we're referring to the switching process, we are referring to OSI Layer 2. At OSI Layer 3, or the network layer, we're referring to IP addresses. So anything that has an IP address or subnet mask, or referring to the way that routers forward traffic, all happen at OSI Layer 3. If you're referring to a TCP port or a UDP port, then we're operating at OSI Layer 4, which is the transport layer. At OSI Layer 5, or the session layer, we're using control protocols to start and end different sessions, or we may be tunneling traffic using protocols that operate at OSI Layer 5. We often associate the encryption of application data with OSI Layer 6, or the presentation layer. So if you're communicating to a website and you're using SSL or TLS to be able to encrypt and decrypt that data, that process is occurring at OSI Layer 6. And at OSI Layer 7, or the application
I see you,
layer,
B. Still trying to wake up?
are interacting with the application itself.
Yeah.
Anything that you're seeing on the screen, the application itself, or any messages
All right,
from
welcome
the
back from break,
application
everybody.
are often referred to as Layer 7 information. If you wanted to drill down a little bit further,
All right, so as we
into the
get
OSI
into the
model,
second
you
half
might
of
want
this,
to capture some data on your network and view
switch
that data
troubleshooting.
inside of an application such as Wireshark.
Sometimes,
I have
well,
Wireshark
let's put it
protocol
this way.
on my screen where I've captured data on my network.
Speaking honestly, we know
Wireshark
coming
has
into the
3
network
separate
and
windows
getting all
that
these search
display
right,
different views of the same data.
we want to set the
Top window
correct
is a
level
frame by
of
frame
expectation when you get into the exam room. Okay? And the reason why I say that is sometimes you may feel like once we get through networking, like I have no clue what's going on. The base of information that you are learning is to make quick react decisions to try to get something online or to get something working, right? So it's the best demonstrated practices that you're going to use. If in the event you get hired straight out the gate, you drop somewhere on the network and you're like, oh crap, what do I do now, right? So those are the basic things that are going to help you get straight to the source, okay? And with this networking class, it gives you the background knowledge on how it actually just works on the inside. Now, the rest of it, you're going to have to get from either training from this website called, and I'm going to take you to there too so you can get set up, Juniper Networks. This website will give you free training, and then they'll give you 75% off vouchers, right? They're pretty much the open source version for routers. And then you have Cisco, where you start getting your CCNA exams. They are proprietary. Juniper networks are like open source, like Linux and LDAP, right? You can pretty much load anything on their networks. Remember we were looking at East Charmer. She went to the server. She got the image for the router. Y'all remember that? image for the switch, image the switch, and then she put all the commands onto it. Juniper is one of those network switches that can adapt to any type of open source OS for a switch. So you can add it to different networks. It's not proprietary. Cisco demands that you have a license. Has anybody dealt with trouble calls with Cisco switches? Mr. T, I don't know if you have, but they have proprietary. So you got to pay for the licensing for all their stuff to talk like Windows, which is crazy, right? So people are starting to leave Cisco and go over to Juniper. So Juniper's like, well, let me give free training to everybody, and we'll give them a voucher if they complete the training. And we'll not only give them a voucher, we'll give them 75% off the exam to get certified. So we'll look at that too. All right. So in the event, what I'm trying to say is the exam, all of this information where you're at seems overwhelming, but pretty much it is the introductory layer to networking. So there's more that you can learn on your own once you get into it. Okay, so with hardware failure issues, switches are nothing more. Overwhelming is an understatement. I hear you, Mike. Switches are small computers, just like your phone is a small computer. A VoIP phone is a small. They're all small computers. They're going to have their power issues too. You have to make sure that the network adapters are good. Switches, routers, and modems. So here's some things that you have to look at. We already know, check the specs. If something's going wrong with power, install an UPS or a secondary power resource that can provide redundancy. If you're having problems with network adapters, sometimes it's damaged ports. I've seen that before. I've seen a user either drop their computer too many times, and you know it because when they drop it, the network cable is still installed. And then usually what will you see if you have a heavy item hanging on a network cable and it drops from their desk too many times? There's an indicator that you'll see to be like, did you drop this thing? Who knows what that is? It's right where the connector is, where the terminator. This will happen. Torn or bent. You are correct. It's disconfigured. Yes, all of those are right. So you start inspecting it and you pull it out, but then you notice you have wiggle room. The net card interface is wiggling. Wiggle it just a little bit. Joe approved, right? So you start messing with that. And so what? So the net card is typically soldered onto the motherboard. Now what? You might have to replace the net card that goes on the inside of the laptop if it is upgradable, right? So that's crazy. It leads to all these different things. Test an alternative adapter, make sure things are good. And sometimes you might just need to update or reinstall the drivers. And we'll know that by going to Device Manager, Network, all the stuff y'all mentioned before. Different ways to get there at the end of the day. But get to your drivers and see what's going on. Switches, routers, and modems, visually inspect, look at the indicator lights. But we have noticed that manufacturers are no longer putting these indicator lights on most computers. I don't know why. The LED lights are vaporizing. I don't know if it's to save money or what. Can y'all look on the side of your laptop and see if you have an indicator light next to your network card interface? I have a Lenovo gaming computer like you guys have. I don't have one. They took mine out. Like that little LED light, which I love to see flickering. It was so soothing to see the LED light. I just stare at it. None on the Mac either, Mike says. Even the Apple logo doesn't light up anymore. That was a selling point for a lot of people to have the Apple light up. No light. Charles says no light, but that might be different if it's wired. Yeah, like mine is it. It's wired and it's got nothing. So I think they're trying to just save money, the dollars, and then you'll have overheating, of course, which is the enemy. Right here, dust. This is going to be a question for you on the exam. It's going to say computer turns off, turns on, turns off, turns on. It's intermittent. We would think it's cooling, right? Cooling issue. But in fact, you're right. But what caused the cooling issue? If this is a choice for you, depending on how they worded their question, and this is a selection, in order for you to have cooling issues, you must have a cause of a cooling issue. This is usually the cause of a cooling issue. It has so much dust in it, the heat is being held in the computer. Yeah. So that's another freebie for you. Allegedly. Oh, y'all so crazy. Y'all just keep me going every day. I know y'all. All right. Here we go. Okay, we have these port status indicators in which you'll see. Now, I will say, a lot of these hold true generally, but depending on what brand or port or brand of switch you may have, this could change. But for what CompTIA says for the exam, this is what it is. Okay. Solid green means that the link is connected, but there is no traffic. They'd be like, yo, man, you got both ends connected. We're hooked up, but ain't nobody at home. We ain't got no traffic. If it's flickering, yeah, it's operating normally. The blink rate indicates the link speed. Ooh, so that's a little trivia question for you. The blinking light indicates the link speed. No light, you done something way wrong. You ain't getting nothing. Solid amber color, which is orange. The port is blocked by the spanning tree algorithm. It's solid. And the blinking amber means there is a fault detected. Cyclic redundancy check for a network. Mike gave an example last week when he was doing this for the satellites and the equivalent, right? Data's moving, how many errors? 5 errors, that's acceptable. Under 5 errors, boom, network comes back up. It's the same thing for a regular network. He did his satellites. Elaine, did you do this on the Apaches too? For any links? You did something like this to check links or anything like that with satellites?
Yeah, like
If you could talk about it. I don't want you to talk about it. You can't talk about.
Link 16.
Okay, link 16.
Yeah.
Okay. So as you can see, this type of technology is in everything we're gonna be touching. For the switch commands, this is what we have. Show config, it shows the device's current configuration. That's why I like talking about this, the PVQs. Remember that big 10-minute one I told you about that you might see? They have switches, something's wrong, just like cider. You have to show config. Show configuration will show the config and what you set up for every switch port, everything on that switch, it's gonna come up. It's gonna come up. Your switch ports will come up like this. It'll look like this in your configure. So if it's a 26 port switch, I meant to put 26 there in the beginning. 126, 226. It'll give you the port number of what's going on. It'll also give you the IP address in which it is connected to and give you other telemetry. So it'll list it. Now we're going to go on 101 network plus commands, and we'll go in here and walk through it today. We'll at least do one. Yeah, I know, Mike. So we'll walk through to see what it looks like. At least one or two of them. So no show config shows the whole device configuration. Next, show startup dash config. It'll show the configuration used on the next restart. It could change. You might see this because what if you have to download a configuration from a server, right B, and then you loaded it, and then you say show startup config, it may show you what the next load's gonna be because you just refreshed it, right? You just put it in there. So say next time this thing's restart, this is what it's gonna look like. You're like, oh, okay, dope. Means you loaded it right. Show running config, active configurations currently used by the device, by the switch. And show interface, so detailed information about the device network's interface. Okay. Technically, is an IP address assigned to a port or the port interface?
The port interface, of course.
Little quiz question. What you think, Martin? Charles? You think an IP address is assigned to? You're correct, Elaine. It is assigned to the port interface, technically.
Yeah.
Not the port itself.
Yeah.
Because it can always change. The interface address can always change. You can always reconfigure it. These are your basic ones that you will see. Another one is you'll see show route. Show route. Right? It'll show you, depending on what you put after that. Now, these are the designated commands. You still have to put stuff behind it. Right? Aaliyah, why would show config and running config be different? Oh, maybe if I change something, right? So it shows the configuration, but it shows the running configuration. What is currently being used? What if it's been altered? What if somebody went in there and altered those configs and commands? It'll show you right there. No, well, wait a minute. This doesn't match what it should be. What's going on? It's configured for this, but why is this running? Right? So you can get the true telemetry from that device at that time. With switch statuses. Did I answer your question, Leah? I want to make sure I did. Did I answer your question? I think I did. Okay. Switch show commands. So when you see down, both layer 1 and 2 are down on the link. So it's down physically, meaning there's a physical connection down, and the data link in which I need to send this stuff out is down. So you got to down. The next one, administratively down. That means the interface has been manually disabled by the administrator using the shutdown command. So I purposely shut it down, and now that port is down. Then you have down error disabled. The interface has been automatically disabled, so that gets you there, due to a network error or policy violation. Now, I like this one. On the military network, see this a lot because people like to take these devices that have static IP addresses assigned and they move them whenever they want. Specifically, we had this issue with the printers. In that wall jack, when that printer has been being installed, we take the number of the wall jack in the unit, in the room. Remember we talked about what are the two types of maps as a network admin that you have to have on deck in order to look at all the time. And where you get out there, you're going to find that nobody's done it. So you're going to be the first one to do it. What are these two type of maps?
IMAP and what is it?
One tells you where the hardware is. One will define IP, MAC address, OS on the map. One starts with an L. One starts with a P. There you go, physical and logical. Okay, those are your two maps. On these maps, we like these devices like printers, cameras, fax machine, whatever. We don't want those IP addresses to change because they're reserved on the network. We talked about that. So if we lose power and come back up, everybody just continues on. Because if a printer, video camera, or whatever else starts getting brand new addresses, you're going to throw the whole network out of whack and that device won't work. Okay? So we have to make sure they have static addresses all the time. So, printer has a static address, reserved address, connected to a port for port security. On the logical map, it tells us, yep, that should be there. But you get a brand new printer in, and it knows this too by the deciding factor, which is the printer's MAC address. It notices you plugged in a brand new printer. You configured it with the IP address, but the MAC address is different. Down error disabled means now you've enabled port security. You have assigned a specific MAC address to that port. As soon as you plug in the new printer, the port goes down because it thinks the network is being infiltrated. Now you got to call the network operating center and say, my printer don't work. And they say, what happened? Did you move the printer or did you put something new on that port? And they always say, no, I didn't do that. They're like, yeah, right. We've had port security enabled. You did something, right? Then they got to come down there and do all the other kind of stuff. So that's what that is. You use this with port security. And then you'll see up but down suspended. The physical layer is operational mean. The physical connections, it's happening. Data's being transferred or able to be transferred in ones and zeros through wires or whatever. But the data link is inactive due to somebody configured something wrong. It's ready to be transmitted, but the data link layer, somebody configured something wrong. All right, so we got to look at that. Look at that too. So let's get with the link states. All right. This is a question on the exam too. What are link states? Link states. Well, let's look it up. There are 4 of them. You need to have this in your back pocket. Always have this and know where to find it. Link states and networking. The link state, there you go. They didn't put it in the curriculum, but I'm going to tell you what it is. The link state, or LSP, is essentially a data message used in networking to exchange information about the connections and the statuses between these routers. Think of it as a digital map that updates real time, telling each router in the network about paths that can be taken to send your data efficiently. Okay? The reason why I sent this to you is we're going to start moving into what they call link state routing protocols. Oh my God. Jay, what are you doing? Yeah. Link state routing protocols depend on, first of all, they're going to talk router to router. That includes a layer 3. Right, switch. It's a router and a switch on the inside, okay? So these link state routing protocols will help you either on the inside of your network route information faster, or ISPs use link state routing protocols out on the internet to help that information be routed. Anything you do on the inside of a network for routing, the ISP does on the exterior of the network. Does that make sense? While you might be using clients, hosts, all this other stuff, switches, routers, on the outside, they're typically just using router to router, switch to switch, or internet IP exchange, right? So that's what they're using. These are some terms that you'll see. Neighboring discovery. Each router sends out a hello message. Hello, router. How are you doing? I'm doing great. How are you doing today? Right? It will tell each router how are they feeling as far as their routing protocols. It's pretty much they're using the same thing, right? The advertisement package, letting each other know this is what I can do for you. This is how I can send your information the quickest. Then you have link state packet. After discovering the neighbors, the router creates LSP containing its identity. There's the packet I was talking about. It'll send that out. I'm covering a hole in the that you may not see. All right. So it sends out that link state packet to each router so it can update its routing tables to see which router can send it the best. It's like FedEx. It's like this battle between UPS, FedEx, and Amazon. They all have their own tables or their own routes they like to send stuff, which is the quickest. If we had access to all of their routes, we could make the determining factor. Do I want to send this package to Germany, to Mr. T, right? Via FedEx, I'm going to pay more, but man, their routing table is quick. Or should I send it United Parcel Service? Man, they're slower. The rates are slower, but sometimes they'll use FedEx or Amazon to send it. You get what I'm saying? So it's kind of like you got to make the decision on which way it's going and how you want it to go. I just mentioned this. It builds a routing database from now please write this down. This is the order in which it's happening. It builds the routing database based off the LSP, the advertisement, the protocol. It reads that link state packet, talking about bandwidth, delay. Yo, we got a traffic jam over here. You might not want to come over here. You might want to go another way. The path cost. There's path cost again. And the link state packet. It takes into account the cost. All right? Routers then flood the LSPs, so the routers creating a complete map, building the routing database from the LSPs, and then it starts to calculate the shortest path. The shortest path. Which way do I want my data to go? It'll start determining that. And then it populates the routing table. So these are your 6 steps. This is what's happening. All right. Again, you can Google link state routing protocols. You'll get the same thing specifically. All right. So moving back to here, so you know, with these link states, checks the interface to see if it's up and down, immediate alert for downtime, count of manual automatic restarts, high frequency. These are the errors you might have. And then the other part of that is you might have some packets that get discarded. They won't arrive. There's something wrong with them. Mismatched MTU size anomalies. Are they runts, giants, or regular MTU? You could be overloaded. Somebody's trying to overload your traffic. There might be a problem with the access control list, open and close ports. VLAN configuration is wrong. So you got to take all this into account when you're troubleshooting. When you come into account with cyclic redundancy checks, okay, common errors. Frames calculated checksum doesn't match what's being transmitted. There's noise on the line or interference. Runt, when we talk about the runt frame factors and giant frame errors. Too small or too big. Something's misconfigured. This is the result from collisions. Remember, say runt frames usually are resulting from fragmented segments. So now it creates runts on the line. Here's some of the other errors that you might see. Network loops. We talked about what are some solutions to not have loops. Well, implement STP or fast STP. DHCP issues. The broadcast storm could bring down the DHCP and the whole network goes down. So you want to monitor the traffic, segment the network. It's another reason why you want to segment networks. So if something happens, the whole company doesn't come down. The whole company is not on one LAN. Okay, I fibbed. I said I wasn't going to ask no cider questions this morning, but since we're talking about this, if I use a /23, what's better to use, a /23 or /24? You're correct, Elaine. 512 devices. You remember when I said, if you using a LAN that's got 1,024 devices, I will find you. And you have no reason to do that. That means you're putting everything on one LAN. Yeah. Why? Why are you doing that to yourself? Don't do it. 512, you're pushing it, but at least it's manageable, right? You can kind of manage that. All right, power over Ethernet issues. Cabling considerations. Make sure your cabling's matching. I don't need to go down here. We learned about compatibility. And make sure you have all that going on with your power budget and your management. Can your power supply handle what you're putting on the load? Or your UPS, uninterruptible power supply, right? Or your, what's the other one? The external one where you can plug up multiple computers to it and it has conditioned power. Conditioned power.
Yes.
It escapes me now. I can't remember the acronym for that one, but I'll circle back. So in summary, this is what we're looking at. Your NIC card is a basic transceiver. Transmits and receives. We need to make sure when anything is connected to a transceiver that the cabling or the wireless or the wired can handle the data coming in and out. Okay? You don't want to have mismatch, so you want to make sure everything's configured properly. When you now connect that item, that host, item, endpoint, node, whatever you want to call it, to a switch, now you have to make sure all of that's compatible. Now the switches need to make sure that they are in a hierarchical order too. One switch, no problem. 2 and 3 switches, you got a problem. You have to make sure they don't create storms amongst themselves or have data just floating around. Time to live, right? All these collisions are happening. So now you have to implement what they call STP. One of those has to be the boss. One of them has to have a root port in order to put everybody else in an order. Okay? So that has to be implemented. You also have to turn on BPDU guard. They send things in frames. That's because they're layer 2. Layer 2 protocols come into play. So you put BPDU guard, bridge protocol data unit guard, on to make sure frames don't come back into the network twice. Right? It's like having a bouncer at the club at the front door. Right? You've been in once, I can't let you in again. Then we talked about link states, how those And this is important. You'll see a couple of questions talking about this. As you can see, this applies to switches and routers, is what they call path cost. Path cost. And the path cost, they take into account the bandwidth. When they start using protocols to route traffic or to put themselves in an order, right? Bandwidth, link speed, delay, right? Each one gets an assigned number. And when it comes to switches, what is the determining factor? If two links have the same path cost. I thought I heard you, Mr. T. You said MAC. Yep, lowest MAC address. Yep, smallest MAC. Good job. So those are some things we have to take into account. Are there any questions on getting bombarded about switches this morning? I got you when y'all are most vulnerable, early in the morning. Yeah, it's a lot. We just take it slow and easy in here, man. We give the information, then we circle back, we season it a little bit, and then we season it again, and then we re-explain it again. We're good. That's how we do it. We just don't give it to you and forget about it. We circle back over it, right? Till we have some kind of understanding. So I'll let y'all digest that. What we can do then is turn to on our assignments and studying. And in SkillSoft, we can do that. And then, 11? In 7 minutes, go ahead and go on your break for 10 minutes and come back, and then you guys can get turned on that. And we'll do that till 1. Then we'll get into a lab at 1, and then our other lesson. But I'm here for you guys. Got any questions?
The Cisco packet tracer that we downloaded, well, we'll be doing the same thing on the test as well. Will that be a PBQ?
Yeah, but good question, Mike. On a PBQ, see, we always reiterate, you'll see some trash like this. Remember that reverse telemetry we were talking about? From that one address, we're figuring out block size, net ID broadcast. Yeah, you need to do that to figure out segmented LANs and networks. Somewhere in there, there's going to be an IP address that they're saying is trying to talk to another VLAN and can't. Because the subnet mask is going to be wrong, the IP address is going to be wrong, or the pool is going to be wrong. So just by looking at that, you can click on all the little computers and devices that they're telling you. And please, I'm so glad you said this. When the PBQ asks you a question about a specific computer trying to talk to another specific computer, if A is trying to talk to D, follow the path only. Most of y'all like, James, what does that mean? I'm going to tell you what it means. Let's go back to this example. If this is computer A, and it says up here trying to talk to computer B, follow only what you need to get to computer B to get the telemetry. They're going to have a whole bunch of these all over the place. It's a distractor. You're going to start clicking stuff over here like, well, this says this, and this says this. That's not what they asked you. They said this, can't talk to this. Follow with your finger that path and mess with those devices only, they're going to have some interesting stuff that's going to tell you stuff when you click on it, and you're going to go down a rabbit hole, and you're going to get that PBQ wrong because they distracted you. Does that make sense? So stay on the yellow brick road, as I call it. All right? Don't go venturing off, because this ain't got nothing to do with what they asked you. Yep. If you get confused, there'll be a reset button up here. Click reset. Click, click. Start all over on the PBQ. It'll put you back where you need to be, and you can quickly just re-identify and keep going. But they'll do that stuff. Now, VLANs, when we get into that, that's why we need to learn how to set up a VLAN. What'll happen is, this will trip people up on the exam. Let me get my annotating. Think. We haven't talked about it yet, but we're here already. When this stuff gets set up, okay, wait. I want y'all to do an exercise. Look at this picture and tell me how many VLANs do you see? Now, remember, a VLAN is a segmented, isolated network. It's done on purpose because you don't want somebody getting into your network and do what they call VLAN hopping from network to network to network to network. So you separate all these networks by using CIDR and assigning a group of IP addresses to that one network segment. This is important because they'll throw you some trash in here and you're like, what? So how many VLANs do you see?
It has 1 and 2 collision A and B. Yep. AB equals 2.
I'm gonna give you another hint. There's only 2 things that separate collision domains or VLANs: a router or a switch port. A switch port can separate VLANs. Okay, we got 1 or 2. I'm assuming y'all think these, right? All right, here we go.
Yeah.
For enterprise security purposes, not a SOHO network, this is coming in. First of all, that's 1. It's isolated. When this gets talking over here, 2, 3, we're at 3 already. You want to isolate all of these. They'll have their own VLANs. Considering if these are 2 different departments, you can even go further. If this is a segmented VLAN off of a switch port, you can have 3. That'll be 4 and 5 if these are different departments. But let's just leave it as basic as it is on the example. This is 1 collision domain. So, hey, we're just having this VLAN over here has 2 computers on it. And this one over here has 4. Okay, just to make it simple. So there's 3. Now, when you get down to it, you'll start seeing this. 172.16. We're just going to make up an IP address scheme, but usually it'll be something like 29. How many devices can I have on a 29? Active devices.
Active devices, so 2, but
8, right?
yeah.
So usually with core devices, you'll start seeing them using this address IP scheme. This is the first octet, second octet. I didn't have room to put the other ones. The whole point of this is you'll see a 29 or a 30 because they want these to have very little IP addresses on them. And they'll have another IP address interface to connect to another one. You'll see this one over here be like a /29 or a 30. All right. And this one could be 172 something else, and this would be 172 something else, dot 30 or dot 15 or something. Well, you can't have 15, it has to start with 16, or dot 17. That's how they're giving them their own CIDR schemes. Okay? But don't get fooled. Look right here. Get your IP address schemes and know if these addresses that they're giving you fit inside of there. Could be a configuration issue in here. Does that make sense? All right. Sorry to overload you so early in the morning, but since we're already here, I want to talk about it. Mike asked a good question. All right. I'll let you turn to the break, and I'll see you when you get back.
Based services. This allows you to control what traffic can go outbound and inbound to your VPCs. Most of these are based around a series of port numbers and protocols. So you can define a TCP or UDP port number and add that to your inbound or outbound rules in your security groups. You can also add layer 3 addresses to this. So you can add IP addresses that are individual addresses, maybe an entire block of addresses using CIDR block notation, or specify IPv4 or IPv6 ranges directly within your security groups. This is very similar to configuring a traditional firewall, which operates looking at TCP or UDP port numbers. In this example, the inbound rules have a number of predefined rules, but you can customize these as well with your own port numbers specific to your application. In your cloud provider's front end, you would include in your network security list the list of rules that you would like to assign. For example, I have a rule that is inbound using TCP port 443, and any IP address is allowed to communicate inbound with that rule. I have another rule that's an inbound rule for TCP port 22, and it's the same broad range of any IP address. Once you define your network security list, it will be applied to all of your virtual private clouds. You can see that I have a virtual cloud network for Subnet X, Subnet Y, and Subnet Z. These very broad network security lists will automatically be assigned to each one of those individual networks. One of the challenges with these network security lists is that they don't provide a lot of granularity. When you configure a network security list, it's automatically assigned to all of your virtual cloud networks, even if you don't need that particular rule in that cloud network, and even if you need additional rules for one of the individual cloud networks. Fortunately, there are ways to add additional granularity using a network security group. With a network security group, I can assign rules to individual virtual network interface cards, or VNICs. So you can see I have similar security rules that I've defined as a network security group. I have network security group A, which is inbound TCP to port 443, and I have a network security group B, which is also an inbound rule to TCP port 22. I've identified these as the network security group A with the green shield and the network security group B with the blue shield. And you can see that I can assign those network security groups to individual network interface cards that may be inside of a virtual cloud network. This one is on a single subnet where I've defined different rules for different interface cards within the same virtual cloud network subnet. You can see by using these network security groups that we do have additional granularity that we could bring down to the individual interfaces. But this also increases the amount of administration required to manage all of these different lists. If you find that you need additional security above this, you might want to look into a virtual firewall or other virtualized platform to include additional security to your application instances.
Welcome back to the strongest connection.
With most options, I've been waiting for something special, but it's been buffering.
But underline, our connection is strong and ultra fast.
This is gonna last.
Underline, local gigabit internet that loves you back.
If you've been injured, we get to know you. We get to know your case. We will fight for you. We know who to call. We know the experts. We know the doctors to use. We have the litigation in-house. It's all going to be handled here.
When you're deploying a cloud-based application, you also need to consider who will be accessing that application and from where. If you're creating an application that anyone on the internet would need to access, then you would probably want to include it in a public cloud so that everyone can gain access. But if you're building out a cloud-based application that is for internal use only, you may want to deploy this to your own virtualized local data center where you have a private cloud. In many organizations, we often use both of these, and we need a hybrid configuration of both public and private clouds for all of these applications. One type of cloud model is software as a service, or SaaS. This is commonly associated with software that is on demand. You have a login screen on your browser, you log in, and now you have access to the application. Someone else has written the application, someone else manages the application, your data is stored somewhere within that application, and you don't have to do anything else to be able to use that particular app. You don't have a local installation of software, you don't manage or upgrade any of the software itself. Instead, you simply log in and use the app. This allows for centralized management of the application and the data that you're putting into the application, which means everything is being stored on a third-party cloud platform. This is a complete application offering, and you don't have to do any type of development work to be able to use that app. A good example of software as a service would be an app like Google Mail or Office 365, where you simply log in and use the app. There may be times when you would like to build your own application and deploy and manage your own data, and all you really need are the computing resources to be able to run that application. In that model, you want to use infrastructure as a service, or IaaS. Sometimes you'll see this referred to as hardware as a service, or HaaS, because you're effectively using hardware in the cloud and then using your own software on top of that. This means that you would be responsible for installing your software and managing all of the data associated with that software. If the software needs to be upgraded, you would be the one to upgrade it on your infrastructure as a service model. The application that you're using and the data that you're putting into that application is still in the cloud, but you have much more control over the access and security of that data when you're using infrastructure as a service. A good example of infrastructure as a service is with web service providers, where you can buy time on a particular web server and they make that server available to everyone on the internet. A middle ground between software as a service and infrastructure as a service is platform as a service, or PaaS. This is still in the cloud, but you're the one who manages all of the development efforts to customize the application to your specifications. The cloud provider gives you all of the tools necessary to build this particular app. You can think of this as a series of building blocks provided by the platform as a service infrastructure, and then you build out those blocks to create your own application. The underlying engine that runs the application is the responsibility of the platform as a service provider, and your responsibility is to build and maintain the apps that are running in platform as a service. A good example of a platform as a service infrastructure would be something like Salesforce.com, where they give you all of the tools necessary to create a customized application running on the Salesforce.com platform. Here's an example of a cloud responsibility matrix that you might find with any cloud service provider. In this chart, I've separated out software as a service, platform as a service, infrastructure as a service, and then an on-prem device that you would manage yourself. Obviously, with on-prem, everything from the data to the applications to the physical data center are all the responsibility of the customer. But with infrastructure as a service, you have the physical data center, the physical network, and the physical host, all provided by the cloud provider, and then you handle all of the other pieces of that particular application. With Platform as a Service, you can see that network controls, applications, and the identity and directory infrastructure may be shared between the customer and the cloud provider, but you'd still be responsible for the accounts, devices, and the information and data. With Software as a Service, much more of these are provided by the provider themselves. For example, everything associated with the applications is clearly in the responsibility of the provider. Everything above that would still be the responsibility of the customer. So depending on the type of infrastructure you want and the type of responsibility that you're willing to take on, you'll need to pick the right cloud model for your application deployment.
People can go crazy trying to stop a cyber attack. Acronis, take the headache out of IT security.
In this course, there will be a lot of conversations about TCP/IP, moving packets across the network, and very often we lose track of exactly what that means. So I thought it would be good if we started with an overview of Internet Protocol and how it operates. The goal, of course, is to get data from one side of the network to another. And there are a number of different processes involved in being able to transfer large amounts of data from one computer to another. In the analogy that we use today, we're going to describe this transfer of data from one device to another as using a moving truck to get data from one house.
All right, everybody. All right.
This might be a wired Ethernet network, a wireless network, a wide area network technology, or many different types of network connections.
Everybody's making their way back.
Those network connections are referred to as the road that are.
Okay, there's a link
in this example,
that I put in the chat. Please click on it and bookmark it. It's called Notes Networking, notes.networking.com. Notes.networking.com. I have it up on the screen right now. This is going to help you during Network Plus so much, and it's going to simplify for you. Like what protocols work with other ones, like link state protocols, exterior gateway. How hard is the exam?
We have boxes within that moving truck. We commonly refer to those boxes as the TCP or UDP protocol.
Because it all comes back to
inside of those boxes is application
how much you understand the routing protocols and configurations.
Encapsulating data within other protocols, which are
it's an individual basis type of thing. Like the exam, looking back on it now, knowing as much as I know now, I could probably walk in there 90%, 92% sure or 90% sure all my answers are correct no matter what. Am I going to get something wrong? Yeah, I am. It's a test, right? I might have something I need to brush up on. But if I get 90% of those questions right, I'm passing the exam. You get what I'm saying? Based off where your knowledge base is right now, it's going to seem so challenging because you're trying to learn all these things, right? I've seen it repeated so many times. So it's based off on how well you understand the proper use of that configuration, whatever we're talking about.
So if we were to look at a protocol,
it'll help you eliminate
header,
what's not needed in that question. I know, Michael, I didn't really answer it, but I kind of answered it. So, yeah, it takes practice and not being here. You can't live on the surface level of Network Plus. You got to go down one level and understanding the information. If you do not do that, you will probably not be successful on your first attempt.
Both of these protocols are very similar.
Yeah, you got to dig.
They're obviously moving data from
this website here.
But the internals of how those protocols work are a bit different between the two, in an application.
And I'll click up here if you ever need to return home and you're somewhere. This tells you everything you need to know about routing protocols.
Remember that TCP and UDP.
The one thing I like it here is like, let's take this, the physical layer. Or if I want to look, let's look OSI model.
Many different applications across the network simultaneously between exactly the
Okay,
same devices.
brings up the OSI model. The cool thing here, physical layer, bam,
multiple applications.
tells you everything that's happening on the physical layer with links and everything. PoE for power over Ethernet, right? Power over a gigabit.
We refer to TCP as
It has a mind map. This is called a mind map over here. If I scroll up my wheel, my mouse wheel, as I hover, it tells me everything that is associated to PoE.
Different than UDP is the ability for a station to.
I like it just for the fact that it does that.
We refer to this as.
So, if you want to learn about PoE, it's connected to Ethernet. It has standards. There's passive EoE. There's this, PoE. Oh man, network discovery. You can click on any one of those, and it'll take you to that standard on the web page.
This also means that
or wireless. You double click on it, and it brings it up. If I want to learn about routing protocols, which we're gonna get into,
resend that information to ensure that it's able to receive all of the data. These packets
link state and dynamic routing protocols. We're going to learn about both of those. But we talked about link state. It brings it up. Oh, what is it? Oh, they saying what they call a link advertisement. 5'10", 120 pounds, lean, brown hair. It's an advertisement. I got to tell my buddies what's going on with me over here. And it brings the topology, scalability, how could you use it? And if you want to bring up the mind map over here for link state routing protocol, there you go. Tells you all the link state routing protocols that goes along with it. So it's a good study tool to know. Oh, if we're talking about link state, we're talking about OSPF, ISIS, routing. Oh my God, interior gateway routing protocol. It helps narrow it down on the exam. So some might like it, some may not, but it's just another tool for you to use. So I just wanted you guys to have that. Oh, okay. Charles says, based on prior experience, it's hard. Sorry. Yeah. It's just based on your experience and how well you understand everything to bring it all together to get through the exam.
Exactly the same way with exactly the same probability of.
All right, but this is what I want to show you. Go ahead and bookmark it.
The difference is,
and I'll let you turn to you if you don't have any questions.
So we can't guarantee that information has truly been delivered. And since there's no acknowledgement and no notification that anything has been delivered, there's no way to perform any type of error recovery or be able to retransmit portions of the data which may have not been received. And because there's no ongoing communication back and forth between these two devices using UDP, there's no way to configure any type of flow control. The receiving station can't reach out and tell the sending station to speed up or slow down because nothing is ever sent back to the originating station.
Tackling your security concerns starts with a prompt. With Sola AI, you get answers to the security questions you...
Now that we've loaded our boxes of data into our IP truck, we need to tell the truck driver where to take this information. And in a moving truck, we do this by giving the truck driver the destination address for the truck. In the world of IP, we give it a destination IP address. But of course, in a house, we have many different rooms that we might deliver these boxes to. Some boxes might be for the bedroom, others might be for the kitchen or bathroom. And when we bring the box into the house, we can take that box directly to the appropriate room. IP works in a similar way, where each box of data is provided a room name. And in the world of IP, it's provided via a TCP or UDP port number. Instead of having bedroom, living room, kitchen, or bath, there will be a number associated with that data, such as port 80, port 443, port 123, or port 25. When those TCP or UDP boxes arrive at the house, we simply look at the TCP or UDP port number and deliver that box to the appropriate application running on that server. If you were to look at a protocol decode of IPv4 traffic being sent over the network, you would see a set of IPv4 sockets for the server and for the client. This socket is a combination of data that consists of an IP address, a protocol, which would be TCP or UDP, and then there would be an application port number. For the server side, there would be a server application port number, and on the client side, there's a client port number. Once both sides of the conversation know what the IP address is, they know the protocol, and they know the port numbers of both the server and the client, we're able to send information properly between both devices to the appropriate application. If you were to look at well-known applications that are using TCP or UDP, you'll notice that many of those port numbers are from 0 through 1023. We refer to these as non-ephemeral ports, which means they are permanent port numbers. If we need to communicate to a web server, we're almost always going to use port 80 and port 443. Those are very common and permanent port numbers that you would find on almost any web server. On the client side, we tend to use port numbers on a temporary basis. We refer to those as ephemeral ports. Those are ports that are commonly associated with 1024 through 65,535. Although it's very common to find applications using non-ephemeral ports and the clients using ephemeral ports, the reality is any device can use any port number that it would like to. And although we commonly associate servers with non-ephemeral ports and clients with ephemeral ports, the reality is you could find application servers using port numbers within the ephemeral port range. So you can see this is not a hard and fast rule, but instead broadly describes the way that we use these port numbers on our network. Anytime you see a TCP or UDP port, it can be a number between 0 and 65,535. That is a lot of room to be able to use different port numbers for different applications. Most servers, as we mentioned, will use non-ephemeral or non-temporary port numbers, but that's not always the case, and you could see applications using port numbers that are in the ephemeral port range. Remember that changing port numbers is simply a way to designate what room inside of the house will be receiving that particular data. It's used for communication, and this is not a security mechanism. You'll still need a firewall to decide whether traffic is truly allowed or disallowed through the network, and simply changing a port number doesn't increase or decrease any type of network security. If you're connecting to a web server, your browser automatically knows that it should be looking for port 80 or port 443 and will use those ports by default. If you change the port numbers of the server, your browser will no longer know how to connect to that web server. That's because we expect web servers to always use port 80 or always use port 443. These are well-known port numbers, and if you change those port numbers, you'll have to make sure that all of the clients use the new port number instead of what normally would be well-known. Also keep in mind that TCP port numbers are different than UDP port numbers. Although both of them can be between 0 and 65,535, TCP port 80 is a different port number than UDP port 80, and you could theoretically use two different applications with both of those protocols at the same time. Here's how this might be practically configured on our network. In this example, we have a server. Its IP address is 10.0.0.2, and we have a client at 10.0.0.1. These two devices are communicating across the network using three different applications. The server has a web server at TCP port 80, a voice over IP server at UDP port 5004, and it's also providing email services over TCP port 143. This means the client can communicate to the server with all three of those applications simultaneously because they all have different TCP and UDP port numbers. If we were to then look at the IP data that was being sent on a single communication, you can see that this IP address of 10.0.0.1, our client, is sending information to this 10.0.0.2 address. You'll also notice that the client is using a temporary port number for this session. In this case, the randomized temporary port number is port 3000. And this device is communicating to the web server, so it's using the well-known port number of port 80. And you can also see there is HTTP data contained within this packet as well. This data is received by the server, and when the server needs to send information back to the client, it simply reverses the TCP source port and destination port and the IP source and destination to be able to send that information back to where the original request was sent. This same process occurs if you're using voice over IP data. In this case, the client is using a source port of 7100 and the UDP destination port would be 5004, which would be the voice over IP service on that server. And for email data, the source port that's being used is a random number of 4407, and the destination port is the well-known port for email, port 143. So every device on the network that is communicating via IP is using this fundamental process to transfer data. This allows us to scale up into a worldwide internet and be able to send data between two devices anywhere in the world.
I would describe Underline as fast, affordable, and local. Incredibly fast, very reliable, zero lag.
That's kind of fast.
Consistent, fast, simple, no brainer.
One wash it smells so clean. Don't need rinse and refresh, it's a dream.
As a networking professional, you may be asked to configure port numbers associated with a particular application. So in this video, we'll look at the well-known port numbers associated with those apps. We'll start with a generic form of file transfer that's used across many different operating systems. This is FTP, or the File Transfer Protocol. This is a very common and generic form of file transfer that can be used on Linux, Windows, Mac OS, and practically any other operating system. Unlike many applications that use a single port number to communicate, FTP is configured to use one or two different port numbers, specifically TCP port 20 and TCP port 21. TCP port 20 is commonly associated with the file transfer process itself, and port 21 is commonly sent to send control information between one device and another. FTP has an authentication method, so you can use usernames and passwords, and when you're transferring information, you can choose to not only transfer the file, you can list information in a particular directory, add different files, delete, rename, and perform other types of file maintenance. TCP port 22 is commonly associated with SSH, or Secure Shell. This is a way to communicate to a remote device from a console. So you have this text-based front end, and you're able to configure and manage this device over this text-based command line interface. An important characteristic of SSH is the secure part of SSH, because all of the communication between your device and that remote device is all sent across the network in encrypted form. Well, if there's encryption being used with Secure Shell, it would be great if we could use encryption with our file transfer protocol. So, of course, there is a version of the FTP called Secure FTP, or SFTP. This allows us to transfer files from one device to another, and that entire communication across the network is all encrypted by default. Interestingly enough, Secure FTP is really using the SSH protocol to be able to perform this encryption. So SSH and SFTP use the same port number of TCP port 22. And just like our FTP protocol that allows us to perform file management of that device, we can also perform the same file management using the secure version of FTP. So you can view the directories, you can make changes to the directory names, you can modify files, delete information, and perform all of the normal file management from the Secure FTP application. Both Secure Shell and Secure FTP have that foundation of SSH as the underlying protocol. So not only does Secure Shell allow you that remote terminal communication, you can also have remote file transfer communication, and all of that communication will be encrypted using the SSH protocol over TCP port 22. Before we had encryption over SSH or Secure Shell, we used a non-encrypted form of terminal communication referred to as Telnet. This stands for Telecommunication Network, and it commonly uses TCP port 23. Visually, this looks almost identical to what we use with Secure Shell. The difference, however, is the communication that we're sending between our device and the remote station is all being sent in the clear. There's no encryption that's taking place across the network. This means that someone could potentially capture those packets and view everything that's being sent back and forth over the network including your login credentials. It's for this reason that you don't commonly see Telnet being used on our network, and instead we'll use SSH to ensure that all of this communication will always be encrypted. Another important application on our network is the use of email. And of course, we need protocols to be able to transfer these emails from one email server to another. To be able to do that, we use SMTP, or the Simple Mail Transfer Protocol. SMTP is commonly associated with server-to-server email transfers using TCP port 25. All of this traffic sent over TCP port 25 is sent in the clear, or in plain text. There's no encryption that's automatically configured when using TCP port 25. That's why many SMTP servers will use TCP port 587, which is SMTP using TLS encryption, or the transport layer security. SMTP is also used from client devices that are sending email messages, and it's often sending those to a mail server using this SMTP protocol. For receiving email messages and being able to manage your email inbox, we often use other protocols such as IMAP or POP3. So anytime that you are sending email or you're transferring email between email servers, you're probably using SMTP or the Simple Mail Transfer Protocol.
People can get crazy trying to stop a cyber attack. Acronis, take the headache out of IT security.
If you've been injured, I understand what that means. I understand what you're going through. I've been in combat. I understand PTSD. I understand being injured. I understand how confusing this process can be. If you're hurt, we want to do everything for you.
We don't often memorize the IP address of devices that we communicate with. Instead, we use the fully qualified domain name, or FQDN. And the way that we translate between the fully qualified domain name and the IP address is we use a DNS server, and that stands for Domain Name System. DNS commonly uses UDP port 53 to be able to perform this name query. So we'll ask a DNS server what the IP address of www.professormesser.com might be, and it will respond back with the IP address that your device can use to communicate to that server. For those small queries, we commonly use UDP port 53, but if there's a large transfer of data from one DNS server to another, we commonly would use TCP port 53. These DNS servers are obviously very critical resources because without them, we wouldn't be able to communicate to servers.
It is 2 final exams. Elaine, good job.
A very common protocol to find.
Already submitted the final? What?
You're almost guaranteed to capture some type of DNS traffic. We've become very accustomed to simply plugging into a network or connecting to a wireless network and automatically being able to communicate across that network. But behind the scenes, there is an automatic IP configuration process using DHCP, or the Dynamic Host Configuration Protocol. This is the protocol that allows us to automatically configure IP address settings for anyone that connects to the network. By default, DHCP uses UDP port 67 and UDP port 68. To be able to use DHCP, we need a DHCP server. At home, we commonly use a DHCP server that's integrated into an existing wireless router, but in an enterprise network, there are often standalone DHCP servers. We usually configure a pool of IP addresses on DHCP, and anyone who connects to the network will be automatically assigned an IP address from this available pool of addresses. There's also a lease time associated with this IP address, so you're only able to use that IP address for a certain amount of time, and if you are still using that address at the end of the leasing period, you can choose to renew that lease with the DHCP server. We can also configure certain devices to always receive the same IP address every time they connect to the network, and we associate that IP address with the MAC address of that device. We configure that in the DHCP server. That's often referred to as a DHCP reservation. All of this communication that occurs across the network for DHCP will almost always use UDP port 67 and UDP port 68. We talked earlier about the FTP, or File Transfer Protocol, that we use to send files from one device to another. And we described the process of authentication and the many different management functions associated with FTP. But what if you just needed to transfer a small bit of configuration information from one device to another? You don't need to view the name of a directory or change any of the file names. You simply need to transfer a small amount of information very, very quickly. To be able to do that, you might use TFTP, or the Trivial File Transfer Protocol, and by default, it uses UDP port 69. You'll often see TFTP used for very simple file transfers. Usually this is something that doesn't require any type of authentication or login process, so it may be something like a voice over IP device that has no IP address and no configuration. And when you plug it into the network, it is powered on using power over Ethernet. It uses DHCP to get an IP address, and then it uses TFTP.
Hey Zeus, are you there?
Configuration file from the server. This is a quick and easy process. It transfers data without any extra overhead. It's able to do that very efficiently and very quickly using UDP port 69. If you're communicating to a web server, you're probably using one of two different port numbers. This is using HTTP or HTTPS. This stands for Hypertext Transfer Protocol, and it's a communication that is commonly associated with browser-based communication. If the information between your browser and the web server is being sent in the clear without any type of encryption, it's commonly using TCP port 80. If you need to perform encryption of that data, and that is probably the default for most websites that you'll visit these days, it is using SSL, that stands for Secure Sockets Layer, or a newer version of SSL referred to as TLS, or Transport Layer Security. If this is encrypted data, then it's probably using TCP port 443, which is sending HTTPS for secure. Another thing you may notice with the devices that are connected to the network is they all tend to have the correct time and date, down to the second level. We're able to do that through an automated process called NTP, or the Network Time Protocol. Every device on the network, operating systems, routers, switches, and any other device, can use NTP to stay synchronized with their clock across all of those different devices. By default, NTP uses UDP port 123. Being able to synchronize these clocks is more than simply a convenience. In fact, it can be a very critical part of synchronizing log files between very diverse devices. This allows us to go back in time and piece together communications, even though that communication occurred on many different devices. This is a process that usually occurs automatically behind the scenes, and many devices will synchronize their clock multiple times during the day using the NTP protocol. You might also be able to configure this process. Maybe you'd like a device to update its clock every hour, or maybe simply updating once a day is sufficient. This is also a very accurate way to keep these clocks in synchronization. And usually we get about a 1 millisecond difference between devices that are all on the same network. This provides a level of granularity that's sufficient for most applications, and it's something that occurs automatically using UDP port 123 and the Network Time Protocol. As a network professional, you'll be responsible for the uptime and availability of routers, switches, firewalls, and many other devices on the network. One way to manage those devices is through a protocol named SNMP, or the Simple Network Management Protocol. By default, SNMP uses UDP port 161 to query devices and receive information about how that device may be performing. For example, we might have a management station, and we might be querying a device to determine how much traffic has traversed that particular device over a certain amount of time. And then it can provide us with a summary of how much data has been transferred over that time frame. We can then store that data, create graphs, reports, and other information that allows us to manage that device. You might also find that different versions of SNMP may be used on your network. Version 1 of SNMP is the original version. This allows your management station to perform a single query to this device and receive a single response, and all of this is sent over the network in the clear with no encryption. Version 2 of SNMP allowed for bulk transfers, so we can ask for many different variables from this device and receive a large group of data from that device, which simplified the network communication and made it much more efficient. But it didn't provide any type of encryption. All of this information is still being sent across the network in the clear. A more modern version of SNMP is what you may commonly find on your network today, which is version 3. This is a more secure standard for SNMP, which allows message integrity, authentication, and encryption of the SNMP data.
Organic and dairy-free? Woo! Woo!
Here we go.
Third time today.
One of the things you'll find with this default use of SNMP is the management station is interactively making a query and then receiving a response for that query. So it's up to the management station to initiate that communication. But it would be nice if these devices could identify problems and proactively send that information down to the management station. We can do that by using a feature of SNMP called an SNMP trap. This allows these notifications to be sent directly from these devices using UDP port 162. Many organizations may have hundreds or thousands of devices on their network, and it may be a challenge to be able to keep track of what devices are on the network, what users are connecting to those devices, and how the relationship might be between the user and the device. We're able to maintain a database of all of these devices and all of these users through a protocol named LDAP. LDAP stands for Lightweight Directory Access Protocol, and it commonly uses TCP port 389. LDAP allows us to very easily query these databases and retrieve information that we may have stored. There's also a secure version of LDAP called LDAP Secure. It uses TCP port 636. LDAP uses a hierarchical structure to be able to lay out the network and the devices. This is a graphical view of an LDAP database. It starts with the root of the database, which is an organization. In this case, the organization is Messer Studios. We've also grouped together like devices into organizational units. There is a production OU, a support OU, and an engineering OU. Within those organizational units, there may be common named devices. For example, there may be users such as Jack and Daniel, or there may be a database or storage device named TechDocs. We're able to organize and access these devices through this structure, making it a very common and simplified way of gaining access to this data. Microsoft Windows has some very unique features when it comes to data transfer. Microsoft stores information on the network in a file share. You can also share printers through Microsoft's operating systems, and there is also authentication built into this entire process. To be able to provide all of this functionality, there is a specialized protocol named SMB, or Server Message Block, to be able to share files, share printers, or authenticate to the network. You might also see this referred to as CIFS, or the Common Internet File System. SMB is integrated into Windows itself. You don't need to add additional software. There's no additional FTP or SFTP process. Instead, built into the Windows Explorer or the File Explorer within Microsoft Windows is the SMB functionality that allows us to access file shares, print to remote printers, lock different files on the network, and provide processes for authentication and permissions for all of that data. Early versions of Microsoft Windows used the NetBIOS protocol to be able to facilitate this communication. But most modern versions of Microsoft Windows communicate directly across the network using IP, and TCP port 445 is the one that is usually associated with Server Message Block, or SMB. As a network professional, you'll find that you are constantly referring to logs that are being kept on your routers, your switches, your firewalls, your servers, and almost any other device that's connected to the network. One challenge is being able to consolidate all of these different log files to one single location, and there is a standardized protocol for transferring these log files called syslog. Syslog commonly uses UDP port 514 to be able to transfer this log data across the network. You'll often use syslog in conjunction with a security information and event manager, or a SIEM. This is a consolidation point where you can have all of your log files transferred into one single consolidated database. So if you're using syslog and transferring that over UDP port 514, and you're probably transferring it to a very large drive array or some other device where you can collect that log information over an extended period of time. We store a lot of very diverse information on our databases, but fortunately there is a very common form of storage and retrieval for those databases referred to as a structured query language, or SQL. Some people refer to this as SQL. This SQL database uses a standard language that you can use to be able to query and retrieve information from that database. Microsoft has its own form of SQL database called the Microsoft SQL Server, or MS SQL. It stands for Microsoft Structured Query Language. It very commonly uses TCP port 1433. There are other types of SQL databases you might find on your network, and they usually use different port numbers. So if you see TCP port 1433, then you're probably using a Microsoft SQL Server. Many of us start on the help desk to be able to provide support for our end users. And one way that we're able to view the remote desktop of those devices is through the use of RDP, or the Remote Desktop Protocol. RDP uses by default TCP port 3389 to be able to view that remote desktop. The Remote Desktop Protocol is commonly associated with a service that's running on a Windows device. But fortunately, there are many clients that can use RDP to connect to those Windows devices, so it's not unusual to find RDP clients for Windows, Mac OS, Linux, iPhone, Android, and many other operating systems. There are many different protocols used for voice over IP. One of the most popular is SIP. This is the Session Initiation Protocol, and it commonly uses TCP port 5060 and TCP port 5061. SIP is commonly used as the control protocol that we use when we pick up the phone, we dial the number, it initiates the phone call, and then when the phone call is over, it disconnects the session. You might also see SIP being used for extensions of voice over IP that provide video conferencing, instant messaging, and even file transfers. All of this takes place using SIP over TCP port 5060 and TCP port 5061.
Welcome back to the strongest connection.
With most options, I've been waiting for something special, but it's been buffering. But underline, our connection is strong and ultra fast. This is gonna last.
Underline, local gigabit internet that loves you back.
Your Unstoppable's unlimited collection. Luxury laundry scent beads so you can smell unstoppable.
There will be many times as a network professional when you'd like to know if a device is on the network and operating. And one protocol that can provide you with that is ICMP. This is the Internet Control Message Protocol. You can think of this as a way to check in with that device, very similar to sending a text message to see if you get a response back from someone. ICMP is another protocol carried by IP, but it doesn't use TCP or UDP. Instead, ICMP is its own protocol. Although ICMP can be used for a number of administrative tasks, it's most commonly associated with a way to send a message to a device to see if it's alive and operating on the network and see if you can get a response back from that device. Whenever you use the ping command to ping an IP address on the network, it's using ICMP to provide that ping functionality. But ICMP can also provide you with information about other things that may be happening on the network. For example, if you're trying to access a network that is not accessible from your location, ICMP will give you a message that that network is not reachable. Or ICMP can tell you that the time to live that's inside of data that you've sent has expired and it's received an ICMP time exceeded message from that device. Another common protocol on our network is GRE, or the Generic Routing Encapsulation Protocol. If you're creating a tunnel between two endpoints, this is commonly done with VPNs, for example, you're creating this tunnel using GRE. This allows us to encapsulate information within an IP packet, send it across this GRE tunnel, and decapsulate it on the other side. This does not, however, provide encryption of this data. We'll need to provide additional VPN protocols to encrypt the data that we are encapsulating in a GRE tunnel. These VPN protocols are referred to as virtual private network protocols, and it's very common to use these VPN protocols to encrypt or protect any data being sent across one of those tunnels. It's often common to use a purpose-built appliance to provide this encryption and decryption process at the central point. We refer to this as a VPN concentrator. Sometimes this is a standalone unit. It's very often integrated into an existing firewall that's connected to the network. These concentrators are often hardware devices with specialized encryption hardware built into the device to add efficiency and throughput. But if you have a limited number of users, it's also possible to use your VPN concentrator as software in an operating system. This is a common site-to-site VPN configuration where a corporate network may be connected to a remote site over a public network such as the internet. We'll have VPN concentrators, which are usually firewalls or routers. Those are connecting these two sites together over the internet, but all of this traffic that's being sent across that public internet is being encrypted using this VPN technology. One of the popular protocols used to provide that level of encryption over those tunnels is IPsec. This stands for Internet Protocol Security. It's one of the most popular ways to encrypt data being sent across these VPNs. Not only does IPsec provide encryption for confidentiality, it can also provide digital signatures of every packet, which includes integrity and anti-replay functionality. This is also a very common protocol, and it can be used across many different manufacturers' devices. For example, you might have a firewall from one manufacturer on one side of a VPN tunnel, and a firewall from a completely different manufacturer on the other side of the VPN tunnel. Because IPsec is such a standard protocol, those two firewalls can easily connect to each other and transfer information over that IPsec tunnel. When you're using IPsec, there are commonly two primary protocols that are in use. One is the authentication header, or AH, and the other is the encapsulation security payload, or ESP. In order for IPsec to be able to send this encrypted data across the network, we first need to create this tunnel. And we do this by performing a series of steps prior to sending any data. Those steps are referred to as the Internet Key Exchange, or IKE. Internet Key Exchange allows both sides of the conversation to agree on the encryption and decryption keys that will be used for the duration of that VPN tunnel. We refer to this agreement as a security association, or an SA. There are two phases to this key exchange process. The first phase commonly uses Diffie-Hellman to create a shared secret key for both sides of the conversation. This usually operates using UDP port 500, and we refer to this as ISACAMP. This is the Internet Security Association and Key Management Protocol. In phase 2, we coordinate which ciphers should be used for the encryption and the key sizes that would be appropriate, and it negotiates both the inbound and outbound security association to be used for this IPsec tunnel. So visually with phase 1, we're building the ISACAMP tunnel over UDP port 500. In phase 2, we're including the encrypted data over the encapsulation security payload, or ESP tunnel. This gives us the foundation we need to be able to send this encrypted data over the IPsec tunnel. If you're building your own IPsec tunnel, you may be asked whether you'd like to use transport mode or tunnel mode. Both of these work differently and will protect data in different ways. Let's take the original packet, which includes an IP header and some data within that IP packet. We would like to send that over an IPsec tunnel. If we use transport mode to send this IPsec data, we're going to insert an IPsec header between the IP header and the data. All of that is going to be in the clear. Anything within the data portion of that IP packet will be encrypted, and then the IPsec trailer is put at the end of the packet. Notice that the original IP header is not encrypted when using transport mode. And if someone does capture this data, they'll be able to see the original IP header and be able to understand where this traffic is intended to go, even if they can't see the encrypted data within the packet. A much more secure method of using an IPsec tunnel is tunnel mode. In tunnel mode, the original IP header and data is all encrypted, and even if you capture this data, you'll never know what the original destination is for this data. Tunnel mode adds a new IP header, which includes the destination of the IPsec concentrator and includes the same IPsec headers and IPsec trailers that we saw in transport mode. It's probably not too surprising that most implementations of IPsec are going to use the tunnel mode to ensure the highest level of encryption of your original data. Earlier, we mentioned the two protocols that you commonly see associated with IPsec. One of those protocols is the authentication header, or AH. AH is used to validate the information that you're receiving over an IPsec tunnel. And if you're only using authentication header mode, you're sending all of this information over the network in the clear, but you're including some additional hashing to ensure the integrity of this data. However, in most cases, we want to be able to encrypt the data that we're sending over the IPsec tunnel, and for that reason, we'll use Encapsulation Security Payload, or ESP. This protocol is going to encrypt that original data and encrypt the trailer that we're associating with ESP, and then put around this packet a new IP header, an ESP header, and an integrity check value at the end of the packet. This is going to encrypt all of your original data, but also provide the authentication that you need to ensure that the data is received properly on the other side.
People can go crazy trying to stop a cyber attack. Acronis, take the headache out of IT security.
At King Soopers, you never compromise. You get up high quality that's guaranteed fresh and down low prices on over 1,000 items. With quality and savings that add up, King Soopers shoppers never compromise. King Soopers, fresh for everyone.
A unicast is one of the more popular ways of sending information across the network. It is when one station sends information directly to another station. This is a one-to-one relationship, and nothing within that conversation is ever sent to anyone else on the network. If you need two devices to be able to send information to each other, and no other device on the network will be involved with that conversation, then you're probably using a unicast. So anytime you're connecting to a website, you're transferring files, or you're checking your email, it's probably all taking place with a unicast communication. This one-to-one relationship is also one of the disadvantages of unicast, especially if you need to send information to many people simultaneously. With unicast, you would have to build separate one-to-one communications with all of those individuals, and you would have to send separate data for each individual device. But for single communication between you and another device, whether you're using IPv4 or IPv6, you're probably going to use unicast. To be able to efficiently send data to multiple devices at the same time, then you'll probably want to use multicast. Unicast is a one-to-many of many communication, so when you send information out, it is sent to multiple recipients all simultaneously. These recipients are usually subscribing to your multicast feed. So if someone is trying to receive multimedia, they're receiving stock exchange information, or maybe a device is sending out routing updates, you can send those out via multicast addresses. Multicast is relatively specialized, and it requires that equipment understand and recognize how to deal with multicast communication. This is why we don't use multicast when we're sending information across to a different network or even within a very large network. But we do use multicast quite a bit with IPv4 and IPv6, and in the right environment, it can be a very efficient way to send and receive traffic. Multicast is used where one device needs to send to many of many devices. Anycast is used when one device needs to send to one of many devices. This is where a single destination IP address may be sent to one of many different devices that are on the network, and it's something that you'll commonly find with both IPv4 and IPv6. In this scenario, the devices that are receiving the Anycast communication are all configured in very similar ways. This allows the originating device to simply send data to the unicast address, and whatever device is closest is going to receive that traffic. A good use case for Anycast would be something like Anycast DNS. where a DNS query can be sent out on the network and the closest data center will be able to respond to that anycast DNS request. And if you want to send a frame to everyone who's on your network, then you'll want to send a broadcast. This is a one-to-all relationship where a single packet is sent out and everyone on the network receives that single packet. Fortunately, the scope of this is limited to your local broadcast domain, so there's no way to send a broadcast frame from your local network and somehow have that frame appear everywhere else on the internet. This is a type of communication that's best fit for something like routing updates or ARP requests. And although this is something that you will commonly find with IPv4, we decided with IPv6 to remove broadcast completely and go to a multicast form of communication instead.
Organic and dairy-free?
Woo! Here we go.
At Sprouts, our shelves are filled with new, exciting, and delicious discoveries. This is that Sprouts feeling.
Strengthen your hair and protect from heat damage. With Cream of Nature Leave-In Conditioner. Cream of Nature. Unstoppable hair.
If you connect to a network at work or at home, then you're probably very familiar with wireless networks. You may have also noticed that no matter where you go with your wireless device and whatever network you connect to, you always seem to have the required connectivity. This is because there is an international standard for wireless network that's managed by the Institute of Electrical and Electronics Engineers, or the IEEE. The IEEE standard for wireless networks is in their standards committee for the 802 series, specifically 802.11. So anytime you hear anyone mention 802.11, they're referring to the standards associated with wireless networks. Another interesting characteristic of wireless networks is that they are constantly evolving and constantly changing. So you'll want to check in with the IEEE standards to see which type of wireless network you're using. There's another organization involved with wireless networking called the Wi-Fi Alliance. And you'll notice there's a Wi-Fi trademark logo on every device that the Wi-Fi Alliance has tested. This ensures interoperability with the standards that are set by the IEEE. In the past, we used to refer to these wireless networks with their standards name. For example, 802.11b or 802.11ax. We've recently added additional names to these standards to make them a little easier to understand for everyone who's connecting to these wireless networks. For example, if you're using the 6th generation of Wi-Fi networks, then you're connecting to an 802.11ax network. But we also refer to this network as Wi-Fi 6. This chart shows a list of all of the major Wi-Fi standards listed by their 802.11 name. I've also included the new generational name for those standards, the frequencies they happen to use, and the maximum theoretical link rate for each of those standards. The first three of these standards, 802.11a, b, and g, are rarely used today, and we did not formally set a generation name to those, although you could colloquially refer to these as Wi-Fi 1, Wi-Fi 2, and Wi-Fi 3. The newer standards of Wi-Fi 4 through Wi-Fi 7 are covered through the standards of 802.11n through 802.11be. You'll also notice there's a difference on the type of frequencies that are used for each of these standards, and most of these refer to the 2.4 gigahertz, the 5 gigahertz, and the 6 gigahertz ranges. There are a number of differences on how these wireless standards can be implemented. There might be a different number of antennas or a different number of radios, and that accounts for the differences in the theoretical link rates that you see in this final column. Notice as we've introduced newer standards of wireless networks, that we've also increased the overall link rate of those networks. Well, we use more than our local 802.11 networks for wireless networking. If you have a mobile phone or a mobile tablet, then you're probably using a wireless provider's network that uses 4G, LTE, or 5G technologies. LTE stands for long-term evolution. It is what we refer to as the 4G technology, and it was a conversion between different standards of GSM and CDMA into a single standard that every provider can use. These 4G networks supported download rates of approximately 150 megabits per second, and the improved version of LTE, which is LTE Advanced or LTE-A, supports download rates that double that to 300 megabits per second. A more modern version of mobile networking is the 5G networking that was introduced in 2020. This greatly improved the performance of wireless mobile networks, and with the right configuration, the goal will be to have 10 gigabits per second as the overall throughput. And in other implementations, you may see more reasonable speeds such as 100 to 900 megabits per second. 5G has dramatically changed the way we look at mobile connectivity, especially since we're now able to get similar bandwidths over our mobile providers that we currently have with wired network providers in our own homes. This also means that we're able to greatly increase the size of our Internet of Things, or IoT footprint, because now bandwidth is no longer a constraint. This means we can transfer much more data over a shorter period of time. We can receive notifications much faster than we could in the past.
All right, everybody, let's take 10.
We can process
See when you
more
get
data
back.
in the cloud. There may be times when an organization might have a remote location that is not accessible through any type of traditional internet connectivity. For that reason, we may want to use a non-terrestrial form of connectivity known as satellite networking. This means that we can add a satellite dish to a location and begin sending and receiving data from the satellite. This obviously adds additional cost and complexity, and the speeds of satellite networking, although reasonable, are not as fast as those we might have for traditional terrestrial-based networking. For example, satellite networking can commonly provide you with 100 megabits down and 5 megabits up. This means that if you have a remote site that has no other way to communicate, you can add a satellite dish to the roof and begin communicating directly to the internet. As you can imagine, there is a delay as information is sent into space and back down to Earth again. Traditional satellite networking provided 250 milliseconds up and 250 milliseconds down, so each conversation to and from the satellite took approximately half a second. Newer technology such as Starlink advertises a 40 millisecond latency, and they're working to decrease that down to 20 milliseconds. Another challenge with satellite networking is that it requires a direct line of sight to the satellite that's in orbit above the Earth. This means if anything does get between the satellite receiver and the satellite, then we may have a decrease of performance or lose connectivity altogether. For example, if a thunderstorm was to come through, we would suffer through what we call rain fade, where we lose connectivity while that storm is going over. In those situations, it may be necessary to wait for the storm to blow through, or we may have other forms of connectivity that we might use when a storm is currently active.
I would describe Underline as fast, affordable, and local. Incredibly fast, very reliable, zero lag.
That's kind of fast.
Consistent, fast, simple. No brainer.
Dear Savvy, who says you can't have it all? You've got the tech, you've got the drive, and now you've got Toyota value. Toyota, let's go places.
If you've connected your computer to a wired network, then you're probably using Ethernet. Ethernet is the most popular networking standard in the world, and almost any device you use will be able to connect to an Ethernet network. There are also many different types of Ethernet. They vary in speed, the type of cabling we use, the connectors at the end of these cables, and the type of equipment that's required to connect all of these devices together. Our modern Ethernet networks have many different standards for both twisted pair copper cabling and for fiber optic connectivity. The reason we're able to connect any device in the world to any Ethernet network and be able to have this connectivity is because there is a single set of standards for all of these Ethernet networks. Those standards are created by the IEEE 802.3 committee. IEEE is the Institute of Electrical and Electronics Engineers. and they're responsible for designing and documenting the standards we use to connect all of these Ethernet networks together. For example, a very common Ethernet network would be 1000 base T. This is a gigabit Ethernet network that operates over twisted pair copper cabling and operates at a speed of 1 gigabit per second. A newer version of that standard is the 10G base T, or the 10 gigabit Ethernet network. This also uses twisted pair copper cabling and operates at a speed of 10 gigabits per second. There are also Ethernet networks that use fiber optics. An example of that would be 1000 base SX, which is a gigabit Ethernet network that uses fiber optics and operates at a speed of 1 gigabit per second. This is just a sample of a few of the more popular Ethernet standards, but there are many Ethernet standards to choose from using different types of media and supporting different speeds. The IEEE has told us that the names they use for these standards don't necessarily correlate back to the details of the standard, but there's usually some information that we can discern from the name itself. For example, if we look at a standard such as 1000 base T, we should be able to break that term apart and determine what type of media and technology is used as part of that standard. For example, the number that's used in the name of the standard is often related to the speed of the standard itself. For example, the 1000 base T, that 1000 refers to the 1000 megabits per second, or 1 gigabit per second overall speed. If this standard started with 10G, then it would be related to a 10 gigabit per second network. We often see the term base in the name of the standard, and that's referring to the term baseband, which means there is a single frequency that is used to be able to send this data over the network. This is in contrast to something like broadband, which uses many different frequencies to be able to communicate across that network. And very often you can determine what type of media is
Agitate, are you using Agitate's name, or you just decide that that's a cool name that you want to use? Agitate. What are you asking, by the way?
This is twisted pair copper. If there was an F at the end, it's very possible that this particular standard would use fiber optics. There may be additional letters at the end of the standard. For example, if there's an SX at the end of the standard, it might be referring to a short wavelength light that is sent over that fiber optic connection. As mentioned previously, the IEEE tries to put the name and terms within the standard.
No, I am not Korean.
But that is not a requirement for the name of the standard itself. If you were interested in the details of what that's,
is it because I look like I have like the squinty eyes?
Standard, and not just look at the name of the standard.
But no, I am not Korean.
Tackling your security concerns starts with a prompt. With Sola AI, you get answers to the security.
Many of us are accustomed to using twisted pair copper, especially if we have networks that we use at home or even at our office. But you may occasionally have a need for fiber optic connectivity, and that fiber optic connectivity allows you to send traffic across the network using light. These are often used on very secure networks because it is very difficult to tap.
Where are you watching from? Which country are you watching from?
This is very different than a copper-based network, which uses RF and is relatively easy to tap and gain information from. Fiber optics are also used over very long distances because the signal doesn't degrade as fast as a radio frequency might. So the same signal that we can send over 100 meters of a copper network might be able to be sent over kilometers if you were using fiber optics. And of course, light is not susceptible to any type of radio frequency interference. And if you're working in an environment where there is interference, you might want to use fiber
Tuvalu. I'm not sure where that is. Let me take a look, see if I can see where that is.
Copper-based networks, there are also many different standards and connectors for fiber optic networks as well. So you'll want to check the configuration and documentation of your devices and make sure that the fiber optics that you're connecting are using the right type of fiber and the right type of connector. If we were to deconstruct a fiber optic cable, you would have something very similar to this. On one side of the cable is the light source. This might be an LED or a laser, and on the other side is the receiver. This LED is sending a light through this fiber optic. And that consists of a core that is very reflective, and you can can see the light bouncing through this core as it receives on the other side. Around the core is a low reflective cladding, and the entire fiber optic run.
So you're located halfway between Hawaii and, so you're somewhere in between Hawaii and Australia. That's what I just pulled up on the internet. I'm not sure where Tuvalu is. Is that how it's pronounced?
Barely make out the core of the fiber that's in the middle. I'll highlight it here so that you can really see where that happens to be. Let's remove that highlight, and now you can start to see that discoloration where the fiber is connected on the end of that cable. We will generally install one of two different types of fiber optic cables. One is a multi-mode fiber, and the other is a single-mode fiber. Multi-mode fiber is commonly used for.
So right off in the West Pacific Ocean, close to Fiji and places like that. Those are some beautiful places, actually.
Emitting diode or an LED. The core of the fiber optic is relatively large, certainly larger than the wavelength of the light, and because of that, the light itself can use different modes to be able to transmit through that fiber, and you can see the different modes bouncing off the edges of the fiber optic cable itself. Because there are different modes that are being communicated through this fiber, we refer to that as multi-mode fiber. If we're communicating over a much longer distance, we may want to use single-mode fiber.
Yeah, I just typed it in.
Communicate up to 100 kilometers without a need to regenerate the signal. Because we're going a longer distance, we may be using a very bright.
Okay, so it's not one of the islands, but it's in the surrounding area. From what I'm seeing here on the internet.
Has a smaller core, which can only allow a single mode of light to propagate through the fiber.
Nissan Rogue has been named to Consumer Guide Best Buy for 11 years in a row.
Cabling is the foundation of everything we do in networking.
Wow, that's pretty cool though. You are all the way out there on, it looks like such a small island on the map from what I'm seeing. That's pretty cool.
Once the cabling is installed, it's very difficult to uninstall or remove that cabling and replace it with something else. So make sure you're using the right cabling for the right infrastructure. And even if your network happens to be mostly wireless, eventually that wireless connection will need to connect to a cable. So you need to make sure you have the right cables installed in the right place to be able to provide the best possible throughput of your network. One of the most common cable types is the twisted pair copper cable. This is something we use for practically all wired Ethernet connections, and it usually consists of multiple wires twisted together within a single sheath. You'll often see that the cables themselves are paired together. That's because
8 kilometers long country. Wow.
One of the wires and a reverse of that signal on the other wire. You may see this written as transmit plus or transmit minus, or receive plus and receive minus. The reason that we have the same signal being sent in different forms is so that we can recognize and correct if there happens to be any type of interference. This twist in these two wires means that at least one of these wires will always be moving away from interference. This allows us to compare these signals on the receiving end to determine what the actual signal should look like. Another interesting part is that the different cable pairs have different twist rates. So if you look very carefully at an individual cable, you'll notice that some pairs of cables are twisted much tighter than other pairs. One common misnomer that I often hear about cables is that a certain cable has a particular speed. But in reality, the cable doesn't have any speed at all. The copper is literally just sitting there in the cable. The cable itself is supporting a signal, and that signal is allowing us to send a certain amount of data over that particular type of connection. The specific Ethernet standard that you're sending over that wire determines just how much data you'll be able to move across that particular cable. If you're ever wondering what type of cable you should be using for the type of Ethernet network that you have, you should go back to the 802.3 standards. Those standards will specify the minimum cable type that's allowed for that particular standard, and it will specify the type of signal and the total throughput expected over that cable. To be able to easily determine the type of cable that's appropriate for a specific Ethernet standard, we've created a set of standards for the cables themselves. We refer to these standards as a
Welcome back from break,
category.
everybody. Remember, if
For
you
example,
need something,
might
let me
find
know.
Category 5, Category 6, or
Don't forget to
Category
get your
7.
cams back
When you
on
check the Ethernet standard,
for
it will
auditing
specify the
purposes.
minimum category of cable that is required for that particular standard. For example, if you're using 1000 base T, you can look at the 1000 base T standards from the IEEE, and it will tell you that the minimum cable category for that specific Ethernet standard is a Category 5 cable. If you install Category 5 cable or anything above Category 5, it will work properly with the 1000 base T standard. Although twisted pair wiring is very common for our local area networks, another type of Ethernet cable that's very often used is a coaxial cable. This describes a cable where two or more forms within that cable share a common axis. For example, you can see the single wire conductor that's in the middle of this coaxial cable. There's also an insulator, a shielding, and a jacket that are also sharing that same axis. One common type of coaxial cable, especially on our Ethernet and internet connections, is an RG6 cable. If you
Kevin, disregard that.
bringing in a cable modem,
I sent you something. Disregard it.
it's probably being brought in on a coaxial cable. If we put two conductors inside of this cable type, then we have a twin axial cable. We often refer to this as simply twin-ax. Twin-ax is a type of cable that you can commonly associate with 10 gigabit per second Ethernet. It's often installed as part of an SFP plus interface. This allows for full duplex communication over a single cable, but it limits the amount of distance that you can send this signal to about 5 meters. This has a relatively low cost when associated with fiber optics, and very often
don't worry, it'll show up.
Much lower latency.
You'll get a text
compared
message.
to using something like a twisted pair connection. If you're at work and you look at the ceiling, you may notice that you're not seeing the actual ceiling of that floor. Instead, you're seeing a drop ceiling and something like
You're good, just disregard that.
tiles that is sitting above the actual ceiling. There is a space between this drop ceiling and the actual ceiling, and we refer to that space as the plenum. Inside the plenum, we may have network cables, there might be heat sensors, you might have cables for power, and there may be other pieces of the infrastructure that run inside the plenum as well. In some environments, there may be a drop ceiling, and above the drop ceiling may be ductwork where all of the air supply happens to flow. You may have air supplied as part of a heating or cooling system in that ductwork, and there may be return air that's using additional ductwork to go back to that heating or cooling system. Since a plenum implies that there is a shared airspace in a configuration such as this where only ductwork is used to transfer the air, there would be no plenum. But if there's no ductwork and we share this same airspace with all of our networking cables, then we need to consider that we're using the proper type of network cables in that shared plenum. This would obviously be a concern in a fire, especially if we're using a network cable type that produces a large amount of smoke or perhaps even hazardous fumes if it was to catch on fire. If this was in a plenum, that smoke and those fumes would be distributed to everyone in the building. This means we need to make sure we're installing the correct type of cable if we happen to be installing this into a shared plenum. Ethernet cables have a jacket on the outside of the cable, and many of those Ethernet cables are manufactured with a polyvinyl chloride or PVC manufacturing. If you're putting this cable into a plenum, then you need a plenum rated cable, and that cable is usually manufactured with a fluorinated ethylene polymer, FEP, or a low smoke polyvinyl chloride, PVC. This plenum rated cable is designed to be much safer in a fire than one that is not designed for a plenum. One challenge when working with plenum rated cable is it may not be quite as flexible as non-plenum rated cable. So if you're going around a lot of twists and turns, it may be a bit more of a challenge to install that cable into the plenum. So if you're installing cable into a new building or you're replacing cable in an existing building, make sure you see where that cable is being run and you use the correct type of cable for that location.
At Sprouts, our wide open layout invites you in.
I know that all.
With healthy around every corner and tasty on every shelf. This is that Sprouts feeling.
regardless of the kind of essay they write, many students today use AI to help. When used properly, AI can help you write a stronger essay while still letting you sharpen your own communication ability. Now, the first step of the writing process is brainstorming. So let's start by heading to app.grammarly.com and clicking on New Doc. Next, let's toggle one of their features called AI Chat. Let's go ahead and click on Start Brainstorming and ask it to help us understand the different kinds of strategies for addressing climate change. Very quickly, it gives us a list of specific, widely recognized approaches. We can then conduct our own independent research on these topics or ask Grammarly for more details. Tell me more about geoengineering. Using AI Chat can be a great way to wrap your mind around certain topics and gather the high-level points. And then finally, we can ask AI Chat to give us an outline for an essay that compares geoengineering to mitigation. And there we go. We have a comprehensive structure that we can modify and work with. And that's what we want, a tool.
Transceiver is a combination of two words, transmitter and receiver, and these are usually combined within the same piece of equipment or the same component. A transceiver allows for modularity. You may have a switch like this one. You can see there are a number of open interfaces in this switch. You slide in the transceiver that's appropriate for the media or the network type that you would like to use, and now that particular interface will operate with that particular configuration. So if you need a copper configuration for gigabit Ethernet, you slide in a copper gigabit Ethernet transceiver. Or if you need a fiber-based 10 gig connection, you slide in a 10 gig fiber transceiver. This means that you could have every interface on this switch have a different type of media depending on what transceiver you are planning to use. There are different types of transceivers, different form factors, and different transceivers depending on the media. For example, if you are using an Ethernet switch, you need an Ethernet transceiver. If you're using a fiber channel switch, then you will need a fiber channel transceiver. You can't use fiber channel transceivers in an Ethernet switch or vice versa. This means you get to decide what media type works best for your configuration. If you need copper connections, you can use a copper transceiver, and if you need fiber connections, you can use a fiber transceiver. And if you need to change those connections midway through your installation, you can remove the copper transceiver and replace it with a fiber transceiver. This type of modularity often comes at an additional cost, but it does provide you with a way to plug into whatever network type you might need. One common transceiver type is the SFP type. It stands for Small Form Factor Pluggable. For example, you can plug in a fiber SFP and connect your fiber connections to that particular transceiver. But if you needed copper, you could easily slide in a copper SFP and plug in your RJ45 connector. SFPs are commonly associated with gigabit Ethernet, so that's 1 gigabit per second. There is an enhanced version of SFP called Enhanced Small Form Factor Pluggable, or SFP+. They look identical in size to an SFP, but they support much higher speeds, up to 60.
Remember those three as well for the third octet, just in case you get it on the exam.
SFP+.
23 and 24. All right.
To a rack that's in a data center, you have a limited amount of space available. First, the equipment is only
Just to make sense of it all.
And the total amount of space available in the rack
/25, 2 subnets. So when you break into the third,
put as much connectivity
I'll show you.
into a single space as possible. To that end, we've created the
It just starts over. It flips instead of going from divisible by 2 all the way down to here. When it starts with 1 all over again right here, now it just multiplies by 2 going up all the way down. Does that make sense? So it just flips. That's how you get 2, 1, 2. When it crosses over that decimal into the third,
is a 1 gigabit per second connection.
2, 1, 2.
SFP would be compatible with a 4.
Then this 4/22 it'll be 4
SFP plus. There is a quad SFP plus that is a
/24 would be 4/26. Excuse me, 25 would be. Oh wait, we're going down. Dang it. /22 is 4 /21 8 /26. Get it? Let's go.
Not only in the amount of space that we're using inside of these devices, but we can take a single fiber connection and effectively extend 4 separate links over that single fiber. There's cost benefit there for equipment and for the media itself. Although the names are very similar, the form factors are slightly different between an SFP and SFP Plus and a quad SFP or quad SFP Plus. On the left is an SFP or SFP Plus. Both the SFP and SFP Plus use the same form factor, although the transceivers are obviously very different. The quad SFP or quad SFP Plus also share the same form factor, but you can see it's slightly larger than the traditional SFP or SFP Plus. Although it is slightly larger than an SFP, it's not 4 times the size of an SFP, so we are getting an efficiency in space by using a quad SFP or quad SFP Plus.
Welcome back to the strongest connection.
With most options, I've been waiting for something special, but it's been buffering. But underline, our connection is strong and ultra fast. This is gonna last.
Underline, local gigabit internet that loves you back.
People who pick Post University choose our 100% online Master of Education program so they can learn practical skills from real-world professionals, making a difference in their own career and in the lives of their students. Are you a Post person?
When working with fiber optics, one of the first things you'll notice is there are many different connector types. You have to make sure that you use the right connector type for the right connection. A very common fiber connector type is the SC connector or the subscriber connector. We also have other names that we associate with this connector. One is a square connector because the connector itself is rather square when you look at it.
If you want to know how a network question will look on the exam, is the PVQ simulator. It gives you the answer. Take a look at that.
It pushes into the connection and snaps in place with a lock. Once you have that connector in place,
it's from CompTIA.
accidentally slip out of that connection.
So they show it to you.
You first have to pull on the
Play it, and then there's the answers right under it.
This is a common connector type, and if you're plugging into a connection in a data center, you're probably using some connections that are identified as SC. The connectors themselves support individual fibers, but they're often combined together into a pair. One of these is commonly used for transmit, and the other is commonly used for receive. Another common fiber connector is the LC, or local connector. This is slightly smaller than an SC connector, and as you can see, it has a clip on the top to lock it in place once you put it into the interface. This also means that it won't accidentally get pulled out of an interface, and to remove it, you need to push down on the clip. That will release the lock and allow you to easily remove it from the interface. Instead of local connector, you might also see this referred to as a lucent connector or a little connector. The LC connector can also be combined in a pair, looks like this, and you can plug both of them in simultaneously, and again, one is used for transmit and the other used for receive. Another fiber on our list is the ST connector that stands for straight tip. It uses a bayonet connector, so you push it into an interface, give it a slight twist, and it is locked in place. This will not easily get removed from the interface unless you reverse that twist, and then you can remove it from the interface. When you're working inside of a rack and there's a large number of cables and fiber, it can be very easy.
Kevin, do you want to go on this breakout with me and Leah? We're talking about something.
All of these different locking mechanisms for these different interface types. Here's a closer view of the ST connector. There's a protective ferrule around the fiber, which you can barely see in this picture, and you can easily see the bayonet connector where you would plug it in and twist it in place so that it is locked into that interface. One of the challenges with the connector types that we've seen so far is that those fiber connections take up a lot of real estate. It would be a lot more efficient if we could put more fiber into a smaller connection, and there is a connector type for that called the MPO, which is multi-fiber push-on. Inside the MPO are 12 individual fibers that are contained in that single cable connection. This also has a lock in place that's very similar to the SC connector, where you would push it in place and you would have to pull it out slightly to unlock it from the interface. You might also see this connector referred to as an MTP. That name is provided by Corning, and they refer to this as an MTP MPO connector. Here's a side view of the connector. It has this lock on the top, and the individual fibers are these smaller dots you can barely see in this picture. If we look at it straight on with some light being sent through the fiber, you can see that all 12 of those fibers are much easier to see on the MPO connector.
Cybersecurity today is so messy and expensive. And why does it take so long? It really shouldn't be that. Get started with Sola, the studio where you can build any security app. Whether you're the security person or just the person tasked with security, tie together some loose ends or build up your security stack. You fit Sola to your needs. It's simple, quick, and free. Get security done with Sola.
At King Soopers, you never compromise. You get up high quality that's guaranteed fresh and down low prices on over 1,000 items. With quality and savings that add up, King Soopers shoppers never compromise. King Soopers, fresh for everyone.
One common copper connector we use on our networks today is an RJ11. It stands for Register Jack Type 11. It is a 6-position connector, but we only use 2 conductors inside of this connector. Sometimes you'll see this referred to as a 6P2C, or 6-position 2-conductor. We commonly associate an RJ11 connector with an analog telephone, but you'll also see RJ11 used for DSL connections, since those use exactly the same wires as a telephone connection. Here's a better view of the RJ11 connector, and you can see the 6 positions, 1, 2, 3, 4, 5, 6 are clearly marked, but you notice that there are the 2 conductors in the middle that are used for RJ11. If you're using an Ethernet connection, then you're using an RJ45 connector, and this stands for Register Jack Type 45. It is an 8-position connector with 8 conductors inside. So we're using all of the conductors available on an RJ45 connection. This is slightly larger than an RJ11 connector, and it's what you would use if you're plugging in an Ethernet connection. Here's a device that has both RJ11 and RJ45 connectors on it. You can see this is a DSL connection that uses the RJ11, and these LAN connections or Ethernet connections are using the RJ45. You can see that they're very similar in shape, although the RJ11 is slightly smaller than the larger and wider RJ45. If you're using a cable modem connection, then you're probably bringing coax connections and plugging it into a cable modem. And the connector that you're probably using is the F connector. The F connector is a standard connection type. It usually has threads inside that allow you to fasten it very securely to the connector. And if you are using a cable modem, this is probably the connection type that you're using from the cable television infrastructure. This is also referred to as a DOCSIS connector, that stands for Data Over Cable Service Interface Specification. The connection that brings the signal is this single copper connection on the inside of the cable. This is what you would plug in and screw into a cable modem using that F connector connected to the coaxial cable. Another common connector used for coax is a B&C connector. This is a bayonet connector, that's what the B stands for, where you push it into the connector and twist it slightly to lock it in place. The NC in the B&C connector stands for Neil Consulman. This stands for Paul Neil from Bell Labs and Carl Consulman from Amphenol. They both were involved in creating this standard for a B&C connection. If you're bringing in a WAN connection or any other type of coax, it's very possible you might use a B&C connection to lock this in place. That is one of the benefits of using B&C, is that you're able to push the connector in and twist it. It's not going to easily remove itself from that connection. You would need to untwist before removing that from the interface. Here's a close-up view of the B&C interfaces on a device. You can see where you would plug in the B&C connector, you twist that connector slightly, and it's locked in place onto that device.
Organic and dairy-free? Woo! Woo!
Network Networks can connect to each other in many different ways, and in this video we're going to look at a number of different network topologies and how those different network topologies can be deployed in an enterprise network. This can be very useful during the planning process where you're designing the network. It's also useful during the troubleshooting process so that you can tell how different networks are connected to other networks. This is also useful during the troubleshooting process so that you can visually see how one network might connect to and send data to another network. Let's start this conversation with one of the most popular network topologies in use. That would be a star network. Sometimes you may hear this referred to as a hub and spoke network. This is what we use in most large networks to connect devices together. There is a central device that is used as the central networking component, and then everyone on the network is all connecting to that same central device. A good example of a star network or a hub and spoke network is one that we have with switched Ethernet. Our Ethernet switch sits in the middle of the network, and all of the other devices connect to that same Ethernet switch. If each of these spokes around the network would like to communicate with each other, they all must communicate through this central hub. A mesh network design is if one location or device connects to another location or device over more than one network connection. This means that we could have one link communicating to another, and it might follow one path to get to that location, or it may follow an alternate path to be able to get to that location. One reason we design a network this way is so that if one link in the mesh was to fail, we can use one of the other links to complete that communication. We might also perform load balancing over these links where half of the data is sent over one connection and the other half of the data is sent over a different connection. Although we can certainly design mesh networks for local area networks, we often see them deployed in wide area networks so that we can maintain connectivity to a remote site regardless of what network connection might be available. If you were to look at a large enterprise network, you would notice there are a number of different architectures all being used in different parts of the network. And when we combine all of those together, we've created a hybrid network. One part of the network might be a star network, another part of the network may be point-to-point, and a third part of the network might be a mesh network. Once we combine all of these together, we've created a hybrid architecture. Many data centers take advantage of a spine and leaf architecture. This is where you would have individual switches at the top that are the spine of the network. There would be switches in the middle that are leaf networks, and then you would have different devices connect to the leaf. You'll notice that the spine network is connected to all of the leaves, and the leaves are connected to each of the spines. However, those leaf switches do not connect directly to each other, and the spine switches also do not connect directly to each other. This works very well for an architecture we use in many data centers known as top-of-rack switching. In top-of-rack switching, every rack has a leaf switch at the top of every physical rack. We would then connect all of the physical devices in that rack to the leaf switch that is at the top of that rack. This keeps your cabling very simple because all of your cabling is self-contained within that same rack. There is redundancy because you have this rack connected to multiple spines. This also increases the overall performance of the network because we're no more than one switch away from any other device in the data center. If your data center only has a handful of racks, this may be a relatively inexpensive way to connect all of these devices together. But when you have tens or hundreds or even thousands of racks in a data center, you would need a separate switch for every rack, and of course the cost of that will increase for each rack you have in the network. When looking around the network, you may find some wide area network connections that are point to point, and as the name implies, there is a single point connected to a single point. This was a very common design on older wide area networks where you would use something like a T1 or a T3 connection. We refer to those as point-to-point T1 or point-to-point T3. We might also use this design in local area networks. If you work on a campus, you can connect one building to another over two connections, and the connection between those two buildings would be a point-to-point connection.
Nissan Rogue has been named a Consumer Guide Best Buy for 11 years in a row. Drive the award-winning Nissan Rogue today.
We're looking for adults 45 and under to be in our HPV vaccination ad. Sound like you?
Not me. In a relationship.
If you're sexually active and unvaccinated, it could still be you.
I'm too old.
If you're under 45, you're not. For most people, HPV clears on its own, but for those who don't clear the virus, it can cause certain cancers.
Wow. Gardasil 9 is a vaccine given to adults through age 45 that can help protect against certain HPV-related cervical, vaginal, vulvar, anal, and certain head and neck cancers, such as throat and back of mouth cancers, and genital warts.
Gardasil 9 doesn't protect everyone who doesn't treat cancer or HPV infection. These diseases may have many causes.
Your doctor may recommend screening for certain HPV-related cancers. Routine cervical cancer screenings are still needed. You shouldn't get Gardasil 9 if you're allergic to the vaccine, its ingredients, or yeast. Tell your doctor if you have a weakened immune system, are pregnant, or plan to be.
The most common side effects include injection site reactions, headache, fever, nausea, dizziness, tiredness, diarrhea, abdominal pain, and sore throat. Fainting can also happen.
Help protect yourself against certain HPV-related cancers. Talk to a doctor or pharmacist today.
Many enterprise networks take advantage of a three-tiered architecture. This is a very common design, and you'll find many organizations use a three-tiered network design for their network. This starts with the core of the network, and this is where we might have the central point for all of our resources. So our servers, our applications, our databases, and other critical points are going to be contained within the core of the network. The second tier in a three-tiered architecture is the distribution layer. This distribution is the midpoint between the users and those core resources. This is usually a series of switches that provides redundancy and connectivity for those users to access those critical resources. And lastly, our users need somewhere to connect, and they often connect to an access layer. These are switches that are usually located very close to the user, usually on the same floor of a building, for example, and that access layer allows us to connect to the distribution, which then connects to the core of the network. This three-tiered architecture is very common to what we might see in a large city. The downtown area of the city is the core of the city, and all of the major resources for that city may be located in a very small geographical area in the center or core of that location. To be able to get to downtown, we need some type of distribution method. For example, we need some type of highway that might connect our homes to the downtown area. And our homes are usually connected to these larger highways through access roads. This allows us to use our local roads for all of our daily chores, but when we need to get to the core downtown, we may need to use those distribution highways. Here's what this three-tiered architecture looks like in a network diagram. The core of the network usually has core routers that are allowing us to connect to other resources in the core. The distribution layer in the middle is the one connecting the core to the access switches, and at the very bottom, the access layer is the one that all of the users are connected to. You'll notice there are multiple links between the access and the distribution, and occasionally you might even find multiple links between the distribution and the core. So if one component happens to fail, we can always use other parts of the network to complete that communication path. This is often combined with multiple buildings. So here on a single campus, we have two separate buildings. All the users are connected on each floor of the building to an access switch. Each access switch in the building is usually connected to one or more distribution switches, and those distribution switches are connected to the core of the network, which may be located in a central data center. If you're a smaller organization, there may not be a need for a much larger three-tiered architecture. Instead, you might want to use a collapsed core architecture. This is a two-tier architecture that combines the core and distribution layer into a single collapsed core. And you can see the access layer is still exactly the same as it was before. This allows for a more simplified design and hopefully a much easier design when you're troubleshooting. This is also a lot less expensive to implement because you have less devices that you have to purchase and install onto the network. However, as you can tell by this diagram, there's not a lot of options for redundancy, so this may not be quite as resilient if you happen to lose any of these individual components. When you're describing the flow of traffic within a data center, it's important to know where the traffic originates and what the destination is for that traffic. One way to describe traffic flow is an east-west traffic flow. This means that the origination and destination for this data flow is all within the same data center. This also means that we probably have very good response times from one device to another since they're all located on the same local network. If the traffic flow is one that is leaving the data center or is coming into the data center from an external source, you would refer to that as north-south traffic. This would probably have a bit of a different security posture than something that is east-west traffic because we really don't know where this traffic is going once it leaves the data center, and any inbound traffic could be coming from potentially anywhere. Here's a better view of this traffic type. If data is coming into the network from the internet or we're sending information out to the internet, we refer to that as north-south traffic. Any traffic that is inside this local data center, for example, if we have a file server that is sending information to an image server, all of that traffic is staying within the data center and would be considered east-west traffic.
Tackling your security concerns starts with a prompt. With Sola AI, you get answers to the security questions you really care about instantly. Get started with Sola, the AI you need to get security done.
Calling all TV lovers. Sign up for YouTube TV and save $66 on your first 2 months to watch live sports, hit movies, and breaking news with no hidden fees. There's no TV like YouTube TV. Sign up today. Terms apply. Cancel anytime.
In the next part of this course, we're going to talk a lot about IP subnetting. And a big part of subnetting is the ability to convert between decimal and binary. So I thought it would be useful in this video if we step through the fundamentals of performing binary calculations. Binary, of course, is a type of numbering that uses two different numbers, either a 0 or a 1. This means that there are only two possible options when doing mathematics in binary. The answer is either going to include a 0 or it's going to include a 1. Each one of these zeros or ones is referred to as a bit. And when we combine 8 of these bits together, we have a byte. Occasionally, you will see a byte referred to as an octet to be sure that everyone understands that this is an 8-bit byte. In this video, we're going to perform a lot of calculations between binary and decimal. So what we need to create is a conversion chart to convert between binary and decimal. We'll create this chart by starting on the right side, and we'll simply put the number 1. Then we're going to double that number and put it to the left. So doubling 1 makes the number 2. If we double the number 2, we have the number 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, and so on. This is the conversion chart that we will use for almost all of our decimal to binary conversions. We created this chart with 8 individual places, but you could keep moving to the left with this chart and go past 128. We'll double it to 256. We'll double that to 512, and so on. You can keep continuing this process so that if you have a very large
How are you doing?
you can still perform the same type
What's your
of
name?
conversion
Vida?
back to decimal. Let's now use this chart to answer this question.
Oh, much love. It's good. It's good to be able to interact with everyone from around the world. So much love to you, brother. Oh, and thank you for that compliment for the mustache.
0010. And of course, we want to know what the decimal equivalent is.
I always see a lot of people, especially from countries like India, the Middle East. They're pretty much, yeah, they love their mustaches too.
Now we have everything we need to perform.
And I've been trying to groom it just a little bit. But thank you very much. How are you doing?
We're going to bring that 0 down to the bottom line. In every place where we have a binary of 1, we're going to take the number just above that and bring it down onto the bottom line. We're then going to add all of these numbers together on the bottom line. So 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 2 plus 0.
So most of the time when I'm here and I look like I'm particularly looking in one direction or I'm focusing on something, it's usually because I'm looking at the computer screen. I'm either studying or doing some kind of an exam or something, or I'm doing a video call, or so that'll be the reason for that. But in general, when I'm interacting or having a communication, then my expression will be a lot more different. But yeah, I appreciate it very much.
Ones in this number, and that's associated with the 2 and associated with the 128. So we'll bring down the 128, we'll bring down the 2, we add those together, and we've got 130 in decimal. So the binary value 10000010 is the same as 130 in decimal. And finally, let's do one more binary to decimal conversion. This binary value is 11111111. We'll bring down that binary value and we'll layer on top of that our conversion chart. And because each one of these spaces has a 1, we're going to bring down all of the numbers of our conversion. And if we were to count 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, you would have the value of 255 decimal. So the conversion of 11111111 in binary is the same as 255 in decimal. Now let's do the same conversion, but in reverse. Let's take a decimal number and convert it to binary. This question asks, what is the decimal 154 in binary? It's the same process. We're going to bring down our binary number, but of course we don't know what that binary number is yet, so we'll put some place marks here, and then we'll layer on top of this our conversion chart. Now we need to determine which one of these binary values will be a 0 and which one will be a 1 to make up 154 decimal. And there's only one combination of 0s and 1s in this chart that would equal that decimal value. We'll start on the right side where we have our 128 column, and we'll ask ourselves, is 128 less than or equal to 154? This is obviously less than 154, so we'll put a 1 in that column, and we'll bring down the 128. Now let's look at our next column of 64, and we'll combine that next column with the numbers that we've currently brought down previously. In this case, the number 128. So 128 plus 64 is 192. And we have to ask ourselves, is 192 less than or equal to 154? In this case, 192 is more than 154, so the answer is no, and we'll put a 0 in that column. Now we move to the next column, which is our 32. We'll add 32 plus anything that we brought down. That would be 128 plus 32, which equals 160. Is 160 less than or equal to 154? It is not, so we'll bring down a 0 in that column. We'll continue with this process by looking at the fourth column, which is 16. We'll add that to anything that we brought down. So 128 plus 16 is 144. Is 144 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the 16.
When you're watching the other football, you don't want to ask your friends, what's offside? And how can I sound like I know a lot about the game? You can just ask Google all of that at once. Oh, so that's it.
Mr. T, I sent you a breakout invite.
Happy place until you come back to bad odors. Use Febreze plug-in. It has a microchip that alternates between 2 scents to fight odors and provide freshness for up to 50 days. Try Febreze Plug.
Our next column is the 8, so we'll add 8 to anything that we've previously brought down. So 128 plus 16 plus 8 is 152. Is 152 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the number 8. Our next column is the number 4. We will add 4 to everything that we brought down into that bottom row. So that all adds up to 156. And is 156 less than or equal to 154? It is not, so we'll put a 0 in the 4 column. The next column is the number 2. We'll add the number 2 to everything we brought down so far. And if we add all of those up, it would be 154. Is 154 less than or equal to 154? It's obviously equal to 154, so we'll put a 1 in that column and bring down the number 2. And obviously we've hit the number 154, so we know that the number 1 on the last column will not be added to this final value. And if we add up everything in that last row, we see it does equal 154. And now all we have to do is look at the middle row to determine what the binary value of this is, and it would be 1001, 1010. If we look at 154 decimal, We know that that is exactly the same as 1001, 1010 in binary. With these 8 individual bits, we can convert any number between 0 and 255. So take any number you would like, put it into this particular format, and see if you can perform the conversion between binary and decimal. As you're increasing the number of bits in a binary value, you're increasing the total possible number of decimal results. For example, if you have 2 bits, there are only 4 possible outcomes: 00, 01, 10, and 11. And if you were to perform that conversion between binary and decimal, that's the same as 0, 1, 2, and 3. If you have 3 bits, then you can have 8 possible outcomes. If you use 4 individual bits, you have up to 16 different options. 5 bits moves you up to 32, 6 would be 64, 7 bits is 128 possible options, and if you were to increase the number of bits into 9 bits, 10 bits, 11 bits, and so on, you would also increase the total decimal number. You can see that this value is listed in this chart, and notice that I've also added the powers of 2 on top of this. This is effectively what we've been doing the whole time. 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. So as we increase this powers of 2, we are also increasing the total decimal value. If you've done anything with networking, then you've probably run into an IP version 4 address. In this video, let's look at the different configuration options for IP version 4. The IP address is the unique identifier that every device on the network must have if it wants to communicate using that IP protocol. An IP address is a series of 4 numbers separated by a period. This would be something like 192.168.1.165. To be able to properly communicate on the network, every device needs to have its own unique IP address. The IP address is combined with another value referred to as the subnet mask. The subnet mask is also a 4-octet value, for example, 255.255.255.0. The subnet mask is used in conjunction with the IP address to determine what IP subnet this particular device is on. This isn't something that's usually transmitted across the network. It's instead used by your local device to make the determination of what devices are local on this IP subnet and what IP addresses may be outside of this local IP subnet. This becomes especially important when you need to send traffic outside of your local subnet, and you do that through the use of a default gateway. The default gateway is the IP address of a device that's on your local subnet that allows you to communicate outside of this subnet. For example, if we have an IP address of 192.168.1.165 and a subnet mask of 255.255.255.0, a common default gateway could be 192.168.1.1. This is an IP address that is configured and assigned to the router on your local subnet by your network administrator, and it must be an IP address that is on your local network. There are also other IP addresses you should be familiar with. One of these is a loopback address. This is a way to define your local device without having to know a specific IP address. Every device on the network has a loopback address, and it's a number that is between 127.0.0.1 through 127.255.255.254. So if you wanted to ping your local device, you could ping 127.0.0.1, and hopefully your local device would be able to respond to you. This is often used to confirm that your local IP stack is working properly, and it would then be able to communicate to other devices. We also have a range of IP addresses that we've set aside as reserved addresses. This is a range of IP addresses that should never be assigned to other devices. They're used for future use or for testing in the future. This range of reserved addresses is 240.0.0.1 through 254.255.255.254. Anything that is a Class E address is also a reserved address. We'll talk about classes of addresses in just a moment. And another address type you might run into is one that is not real. It's a virtual IP address, or a VIP. Virtual IP addresses are not associated with a physical Ethernet adapter. Instead, VIPs are addresses that you would assign to the internals of a device so that you can always reference that device using that virtual IP address. For example, you might assign a VIP to a virtual machine, or the VIP may be part of an internal address that you're associating with a particular router.
At King Soopers, you never compromise. You get up high quality that's guaranteed fresh and down low prices on over 1,000 items. With quality and savings that add up, King Soopers shoppers never compromise. King Soopers, fresh for everyone.
Can you please just hear me out? No, all work management platforms are the same. Monday.com is the one you'll actually love to use. It lets you set up your workflows yourself. No admin, no long approval process. You're in charge. Did you see the dashboards? They update in real time for your team's day to day, so you're always in control. No freaking way. I don't have to put the data in myself. Are you for real? Monday.com handles all the boring stuff, so you can focus on what really matters. You know what? I'm ready to fall in love again. Thanks. Talking llama. You don't remember my name, do you? Of course I do. Monday.com, the first work platform you'll love to use.
Can you guys see her? Can anyone see Elsie?
The IP protocol and IP version 4 operate at OSI layer 3. So anytime you're working with an IP address, you're working at that network layer of the OSI model. Let's break apart an IP version 4 address and really see what it's made of. Let's take the address 192.168.1.131. We refer to these 4 values as octets. That's because they consist of 8 individual bits. And you can see the representation of that same IP address broken out into those 4 groups of 8 bits. Sometimes you'll see these 8 bits broken out and described as 1 byte or sometimes 1 octet. So if you were to count up all of these bits, there are 32 total bits in an IP version 4 address, and that is the same as 4 bytes or 4 octets. Since each one of these individual groups inside of IP version 4 consist of 8 bits, the maximum value that you would ever have in decimal for any of these groups would be a maximum of 255. In the early days of networking, we had to manually configure the IP address, subnet mask, and default gateway all in a manual way. We had to visit that device, change a configuration file, and then that device would be able to communicate on the network. If anything changed with our network configuration or we needed to change the IP address of that device, we had to revisit the device and manually make those changes. Today, of course, we can plug in any of our devices and it automatically receives an IP address. The way that we are able to receive this automated IP addressing is through a protocol known as DHCP, or Dynamic Host Configuration Protocol. When we plug into a wired Ethernet network or a wireless network and we're automatically able to communicate out to the internet, it's because we've received all of our IP configuration settings via DHCP. But if you've ever connected to a network that does not have a DHCP server, you may notice that you're still assigned an automatic address. But this address is not quite as capable as a DHCP address. Instead, it's what we call a link local address because it can only communicate to other devices that are on your local subnet, and we cannot route that traffic outside of your local subnet. For example, if you're assigned a link local address, you can't communicate to the internet because that's outside of your local subnet. In IP version 4, this link local address is assigned through a process known as Automatic Private IP Addressing, or APIPA. This range of IP addresses automatically assigned through APIPA is 169.254.0.1 through 169.254.255.254. There are also reserved sections of that range. The first and last 256 addresses are reserved and they're not assigned to end stations. So if you receive an APIPA address on your device, it's between 169.254.1.0 through 169.254.254.255. Just as DHCP works automatically to assign your address, APIPA also has an automated process to assign this address. It uses ARP to confirm that no one else on your local network has that linked local address. And if nothing responds to that address resolution protocol query, then it will assign a random number between that functional block. One of the challenges with IPv4 is that there are far more devices in the world than there are IP version 4 addresses. And in recent years, we've used up all of the available blocks of IP version 4 addresses. There are no other IP version 4 addresses that can be assigned in these blocks, so we need to find other ways to be able to communicate via IP version 4. One way that we've been able to extend the functionality of IP version 4 is to create an assignment of IP address ranges that can only be used on the inside of a network. We refer to these as a private IP address range, and anything that is a private IP address cannot be routed on the public internet. Fortunately, these are very large ranges, and we're able to use those ranges on the inside of our corporate networks. If you were to look at the IP address that's assigned to your device right now, it's likely that it's a private IP address. So if your device is currently using a private IP address and you're watching this video on the internet, how are you able to communicate on the internet with an address that is not able to be routed across the internet? We're able to do that through a functionality called network address translation. This allows us to convert a private IP address into a public IP address and use that public IP address to communicate on the public network. We'll learn more about network address translation as we go through this training course. If you want to learn more about private IP addresses, you may want to reference a request for comment, or RFC. RFC 1918 is the standard that defines these ranges of private IP addresses and how they can be used on our networks. If we were to look into the details of RFC 1918, you would see 3 different ranges have been set aside for private IP addressing. These 3 ranges are 10.0.0.0 through 10.255.255.255. And if you were to count up all of the possible addresses in that range, it would be over 16 million addresses. We often refer to this as a single Class A block of addresses, and we often write it as 10.0.0.0/8. If you were to write out the subnet mask of that /8 address, it's 255.0.0.0. This means the host size of this particular IP address range is 24 bits in length. Another range is 172.16.0.0 through 172.31.255.255. This gives us a total of just over 1 million addresses that we can assign in 16 contiguous Class B address ranges. If we were to write this out in CIDR block notation, it would be 172.16.0.0/12. The decimal subnet mask for a /12 network is 255.240.0.0, which means our host ID size is 20 bits in length. And the last range is 192.168.0.0 through 192.168.255.255. This allows us to assign over 65,000 addresses as part of 256 contiguous Class C address ranges. The CIDR block notation for this would be 192.168.0.0/16, and that /16 subnet mask is the same as 255.255.0.0. Half of this address is assigned for hosts, so your host ID size is 16 bits in length. As we step through the next series of videos, you'll learn more about CIDR block notation, the different classes of IP addresses, and other details that you see associated with these private address ranges.
Cybersecurity today is so messy and expensive. And why does it take so long? It really shouldn't be that. Get started with Sola, the studio where you can build any security app. Whether you're the security person or just the person tasked with security, tie together some loose ends or build up your security stack. You fit Sola to your needs. It's simple, quick, and free. Get security done with Sola.
Skincare can start in the laundry room. That's why I always recommend All Free Clear for sensitive skin. It's free of dyes and perfumes.
It's a key part of my self-care routine, and
We you start working with IP version 4, one of the things you'll hear about are classes of IP addresses. And in casual conversation, we might even refer to an address as a Class A address, a Class B address, or a Class C address. This was a method of describing an IP address as it related to its subnet mask. Anything that is a Class A address has 8 bits assigned for the network address. And
All right, everybody, don't forget to take your lunch. Click off lunch.
This means that the subnet mask for a Class A address would be 255.0.0.0. A Class B address default subnet mask is 255.255.0.0, and the default subnet mask for a Class C address is 255.255.255.0. This style of class-based subnetting is one that we have not used since 1993, but we still refer to some of these addresses in a very colloquial sense. And although you may hear someone refer to an address as a Class A address or a Class C address, in reality, we no longer use a class-based form of subnet masking. So if we don't use classes, why are we doing a video on class-based networking? That's because these classes do act as a starting point when we begin any type of subnetting on our networks. If you're going to subnet a network, it's important to know where to begin the subnetting process, and this class-based system is the starting point. These Class A, Class B, and Class C addresses have an obvious demarcation between the network part of the address and the host part of the address. With Class A, that line is drawn after the first 8 bits. In a Class B address, that line is after the first 16 bits. And in a Class C address, that line is after the first 24 bits. Here's a table that defines the different subnet classes for Class A, Class B, Class C, Class D, and the reserved Class E. And you can see if you look on the right side, the default subnet masks are the ones we just saw, where Class A has a default mask of 255.0.0.0, Class B is 255.255.0.0, and Class C is 255.255.255.0. The way that you can look at an IP address and tell immediately what class that IP address is associated with is the very first octet of the address. If the decimal octet is between 0 and 127 as the first number of that IP address, it's a Class A address. If the first number of the IP address is between 128 and 191, that's a Class B address. And if the first number is between 192 and 223, that is a Class C address. If you were to look at that address in binary, if the first bit was 0, it's a Class A address. If the first bits are 10, it's a Class B address. And if the first 3 bits are 110, it's a Class C address. Class D addresses are used for multicast communication, and therefore they are not assigned to an individual device. But there is a range for Class D addresses, and that is between 224 and 239, or the first 4 bits of a Class D address are 1110. And there is a range of IP addresses that are not used for any purpose. This is a reserved range. We refer to this as the Class E range, between 240 and 255, or the first 4 bits of 1111. So based on that chart and those ranges of IP addresses, let's see what class a particular IP address would be part of. Let's start with the IP address of 17.22.90.7. To be able to determine the class, we need to look at the first octet, which in this case is the number 17. And if you refer back to that chart, the number 17 is in a Class A address. Let's do another one. IP address is 220.10.77.40. If we look at that first octet, it is 220, and 220 is in the C class. The next IP address is 165.245.0.1. We need to look at that first octet. In this case, that's 165, and 165 is in the range of a Class B address. Next on our list is 128.90.10.2. That first number is 128, which means that is also a Class B address. The IP address of 191.77.24.250 has the first octet as 191, and if we refer to our chart, 191 is in the range of a Class B address. And lastly, 192.1.12.5, we're looking at that first octet of 192, which falls in the range of a Class C address. When you start calculating an IP subnet, there are 4 different values that are very important to know. The first is the IP address associated with the network address. This is the one that defines all of the other devices on this particular subnet. To calculate a network address, you set all of the host bits of that address to 0 and then determine what the decimal representation of that might be. The second important piece of information you need for an IP subnet is the first usable host address on that subnet. This is always going to be one number higher than this previously defined network address. You also need to know the network broadcast address. This is the last IP address of this particular network address. To be able to calculate the network broadcast address, you would set all of your host bits to 1, which is the same as 255 decimal, and perform the conversion between the binary and the decimal. And just as you need to know the first usable host address on the network, you also need to know the last usable host address. And to calculate that, you look at the network broadcast address, and it's one number fewer than the broadcast address. So let's calculate those 4 important subnet values. And let's start with the IP address of 10.74.222.11. If we look at our chart, we know that this starts with the number 10, therefore this must be a Class A address. And the default subnet mask for a Class A address is 255.0.0.0. Since we're using this Class A subnet mask, we know that everything that's on the left side of our bar, or this first octet, is going to be our network address, and everything on the right side will be associated with the host ID. So let's add those to our chart. We have a network column and a host column. Obviously, the 10 dot is going to be in the network column. That's what's on the left side of that bar. And then everything on the right side is going to be the host address.
Influencers aren't new. In 1941, Jeep wrote the book on four-wheel drive.
Years later, the Jeep brand is still influencing. Some create trends, we create our own trail. Some send a smiling emoji, we smile for real. Jeep is only one.
Now's the time to upgrade to the new Dell AI PC. It's optimized for AI workloads and engineered for the future. So no matter what's next, you're ready.
We first need to calculate the network address, and to do that we set all the host bits to 0. This means that everything in that second column will be 0, and the network address therefore will be 10.0.0.0. The first host address is one more than the network address, so our first host address would be 10.0.0.1. To calculate the broadcast address for this subnet, we set all the host bits to 1, which means that the broadcast address is 10.255.255.255. And as you recall, to calculate the last usable address on this subnet, we need to subtract 1 from the broadcast address. So the last usable address on this network is 10.255.255.254. With these 4 values, you'll be able to determine the network address. You'll know if an IP address happens to be one of the usable addresses within that range, and you'll know what the last or broadcast address is for that entire network. Let's do another one. In this case, the IP address is 172.16.88.200. If we look at that first octet, we can see that that is a Class B address, which means the default subnet mask for this network is 255.255.0.0. This means that we would draw our line right in the middle between the first 16 bits and the last 16 bits. So everything on the left side is associated with the network address, and everything on the right side is associated with the host address. Now let's perform those exact same calculations. We want to determine what the network address is, so we will set all host bits to 0. This means that the network address for this particular subnet is 172.16.0.0. To be able to calculate the first host address, we need to add 1 to that value, or 172.16.0.1. To calculate the broadcast address, we set all host bits to 1, which means the broadcast address for this subnet is 172.16.255.255. And to define the last usable host address on this network, we subtract 1 from the broadcast address, which means the last usable address is 172.16.255.254. Let's see if we figured out this process and step through another IP address, in this case 192.168.4.77. Looking at this first octet of 192, that fits into the range of a Class C address, which means the default subnet mask is 255.255.255.0. If we were to draw our line, the network side of the address is the first 3 octets and the host side is the last octet. Let's put that into our chart. So our first 3 octets, 192.168.4 is the network side and .77 is the host side. To be able to calculate the network address, we set all host bits to 0. So the network address for this particular subnet is 192.168.4.0. If we add 1 to that address, we get our first host address of 192.168.4.1. To be able to calculate the broadcast address, we set all host bits to 1, which means the broadcast address is 192.168.4.255. And if we subtract 1 from that broadcast address, we get the last host address, and that would be 192.168.4.254. Although we no longer use class-based subnetting, we can still use this same process when we look at anything that may be class or non-class based. And as we go through our additional subnetting videos, you'll notice that this same process is used over and over again, regardless of the IP address and the subnet mask. In a previous video, we talked about class-based subnetting and how IP addresses could be assigned a Class A, Class B, or Class C address. But since 1993, we've not used class-based subnetting. Instead, we use classless subnetting. Sometimes you'll see this referred to as classless interdomain routing, or CIDR. This classless addressing means that we can assign a subnet mask that doesn't fall into those same Class A, Class B, or Class C arrangements. And instead of referring to the subnet mask in its decimal form, we can simply refer to it as the number of bits. That number of bits is referred to as a CIDR block notation. For example, a decimal subnet mask of 255.0.0.0 is the same as a /8 CIDR block notation because it has 8 individual bits as part of the subnet mask. So it would be very common to see an IP address written as 192.168.1.44/24. Everything with the /24 is referring to the number of bits in a subnet mask, and a /24 mask would be the same as 255.255.255.0. When you're configuring a device, you're often giving it an IP address, a subnet mask, a default gateway, and very often a series of DNS servers. Most of the time, an operating system is expecting you to put the subnet mask in as a decimal mask. So for example, in Windows, you may put the IP address and then you might add in the decimal version of the subnet mask. But if you're using a router or a switch, it may be expecting the CIDR block notation for those masks. So instead of using 255.0.0.0, you would simply input /8. Make sure you check the documentation of the device you're using to see what notation it prefers for the subnet mask. As you've probably seen in our previous examples of subnet masks, the mask consists of a contiguous series of 1s followed by 0s. So the 1s would be on the left, the 0s would be on the right. For example, here is a subnet mask. You can see the contiguous set of 1s on the left and the 0s that are on the right. In this example, you can see 3 separate octets that are set to 1. So there are 24 1s in this particular mask, and there are 8 zeros at the end. If we were to write this out in decimal, it would be 255.255.255.0. And if you were to write this out in CIDR block notation, you would count how many 1s are associated with this subnet mask. In this case, there are 24, so the CIDR block notation would be /24. The subnet mask is obviously used to separate the network part of the address from the host part of the address. So for this particular subnet mask, the network address is 24 bits in length, and the host address is 8 bits in length.
Tired of struggling with impossible messes in your tub and shower? Mr. Clean Foaming Bath Magic Eraser cuts through 100% of soap, scum, and grime, while Mr. Clean Extra Durable effortlessly tackles messes throughout your home. Switch to Mr. Clean Magic Eraser.
season long on Fox and FS1.
Let's convert a binary subnet mask to one that is the CIDR block notation for a subnet mask. And we'll take this subnet mask that we have on the screen, which has all ones in the first 2 octets and all zeros in the last 2 octets. If we were to count the number of ones in this subnet mask, we have 8 in the first octet, 8 in the second octet, none in the third, and none in the fourth. That means the total number of ones in the subnet mask would be 16, so the CIDR block notation would be /16. This means that the first 16 bits of this subnet mask are associated with the network, and the last 16 bits are associated with the host ID. Let's do another one. In this example, the first 3 octets are all ones, but the last octet has 2 ones and 6 zeros. So let's count the number of ones in this subnet mask. There are 8 in the first octet, 8 in the second octet, 8 in the third octet, and 2 that are in the fourth octet. If we count all of those together, we have 26. So the CIDR block notation of this subnet mask would be /26. The /26 means that the first 26 bits of this address are the network part of the address, and the last 6 bits are reserved for the host ID. And here's one more. In this subnet mask, we have the first octet of all ones. The second octet has 4 ones and 4 zeros, and then the third and fourth octets are all 0. Since we are counting number of ones, we have 8 in the first octet and 4 in the second octet. And if you count those together, the subnet mask in CIDR notation would be a /12. That means that the first 12 bits are for the network ID, and the last 20 bits would be for the host ID. We've looked at the subnet mask in binary, and we've calculated the CIDR block notation, but we often refer to the subnet mask as a decimal value. If we were to convert these binary subnet masks into a decimal value, there are only a certain number of these that you would run into. For example, all zeros would obviously be a decimal 0, but anything that starts with a binary of 1 and the rest zeros would be a decimal of 128. If there are 2 ones, it's 192. 3 would be 224, and so on. This means that you could create a chart that shows all 8 of the bits within a single octet and what the decimal equivalent would be. We can now use that chart to calculate the CIDR block notation and what the decimal representation of that subnet mask would be. So let's look at a subnet mask of all ones in the first octet. There are 4 ones in the second octet, and the rest of this would be all zeros. If you refer to our chart, you can see that all ones is 255, 4 ones and 4 zeros would be 240, and then of course all zeros would be 0. And if we were to count the number of ones, we know that correlates back to a /12. So a /12 CIDR notation is the same thing as 255.240.0.0 in decimal notation. And of course, since there are 12 ones, the network section is 12 bits in length, which leaves the remaining 20 bits available for the host ID. Let's look at a subnet mask we've not seen yet. This one is all ones in the first octet, all ones in the second octet. There are 3 ones in the third octet, and of course the rest of this is zeros. If we look at our chart, we can see that of course all ones is 255, and in the octet that has 3 of these ones, we refer to the chart, that is the same as 224 in decimal. And obviously all zeros in binary is the same as 0 decimal. If we then count the number of ones in all of these octets, they all add up to 19. So your CIDR block notation would be /19, which corresponds back to the decimal representation of 255.255.224.0. This of course means that the network part of this address is 19 bits in length, and the host section is 13 bits in length. Of course, we can do this in reverse as well. Let's say that we have a subnet mask that's been given to us as a /26 in CIDR block notation. If we were to write this out in binary, that means that we would have all ones in the first 3 octets and 2 ones in the last octet. And if we would refer back to our chart, all ones would obviously be 255, And the last octet that has 2 ones correlates back to a 192 in decimal. So a /26, where your network ID is 26 bits in length and the host ID is 6 bits in length, is the same as a /26 in CIDR block notation or 255.255.255.192 in decimal. Let's do another one where we've been given a /20 in CIDR block notation. That means there are 20 ones in this particular subnet mask. So your first 2 octets are all 1, and third octet has 4 ones and 4 zeros, and of course the last octet will be all 0. If we refer to our chart, we know that the decimal version of that binary subnet mask will be 255.255.240.0, which is the same as a /20 CIDR block notation. That means the network part of this address is 20 bits in length, which leaves us 12 bits available for host IP addresses.
This is the one who never stops. She works around the clock and knows when it's all on the line. Having the right supplies makes all the difference. The industrial grade products you need. Call quickgranger.com or stop by. Granger, for the ones who get it done.
Spending time with the ones you love is priceless. That's why Kroger Delivery, proudly serving King Soopers, makes grocery shopping effortless. Get $20 off your first order. We'll deliver your groceries in our refrigerated trucks and bring them to your door. King Soopers, fresh for everyone.
In this video, we're going to look at a detailed calculation of subnets and hosts using IP version 4. If you stumbled across this video, I highly recommend you go back and look at our video on binary math, classical subnetting, and IPv4 subnet masks. As we've been going through these subnetting videos, you may be asking yourself, why do we have to go through this process of calculating IP addresses, their mask, looking at default gateways, and understanding what the first and last available IP address might be? Well, that's because it would be functionally impossible to have one device that would know where every other device in the world might be. Instead, we create smaller networks and we build routers that are able to get information between all of these smaller networks. This allows us to communicate to anywhere in the world without knowing exactly where that destination location might be. We simply send out the packet, and the routers every step of the way allow us to get that information to the final destination. Well, this means that we need to create these smaller networks, and we do this by using a process known as VLSM, or Variable Length Subnet Masks. As the name implies, these subnet masks are not like the class-based networks that we looked at earlier, which have a very fixed number of bits in the subnet mask. Instead, we can create a subnet mask that has a different number of bits on every network, therefore creating a variable length of a subnet mask. This means you, as the network administrator, can build a network that is exactly the right size with the right number of networks and the right number of hosts. And you have complete control over what the subnet mask might be for that network. This is a lot like cutting a pizza into smaller pieces. How many pieces do you need in the pizza? Should the pizza be cut in 2 pieces? Should it be 4? Should it be 8? Or should it be even more than that? If we apply this to IP, we can look at a Class A network, which has 10.0.0.0 and a subnet mask with a /8. But if we wanted to cut that pizza into smaller pieces, we might have a subnet mask of the /24 or even a /26. Since we're using a different number of bits than 8 in the subnet mask, we're using a variable length subnet mask that we can define to be whatever we'd like. Let's perform some of this variable length subnet masking, but let's first look at the default subnet mask for a Class A address. This would be 10.0.0.0. The default is Class A, since that starts with the number 10. And the default subnet mask for that would be 255.0.0.0. This would be the default subnet mask if all we did was have classical addressing. If you were to look at this classical address in binary, the first 8 bits would be 1 and the remaining bits would be 0. In decimal, that means it would be 255.0.0.0, and if you were to use the CIDR block notation, this would be a /8 subnet. This means that the network bits would be those first 8 bits of the address, and the host bits would be the last 24 bits of the address. Since this is a /8 subnet mask, we are drawing our line after those first 8 bits of the subnet mask. But in reality, of course, we could pick a different number of subnet bits. We just need to decide what works best for our network. For example, let's draw our line right after the 3rd octet. This means that we still have our default first 8 bits as part of that class A address, but we're going to borrow the middle 16 bits as what we call our subnet bits. This means those subnet bits would now be turned into 1, and the host section of the IP address would shrink down to 8 bits. This means that the decimal subnet mask would be 255.255.255.0, and the CIDR block notation for this new subnet mask would be /24. We've been doing a lot of these calculations in binary, and then we've been converting that binary back to decimal. But that process tends to take time. And one of the faster ways to perform these calculations is to look at a list of the powers of 2. For example, you can look at 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. If you want to calculate the number of subnets and the number of hosts, you can calculate the number of subnets as 2 to the number of subnet bits, and the number of hosts per subnet would be 2 to the number of host bits minus 2. That subtraction for the 2 means that we are subtracting the number that we would use for our network address and the number that we would use for our broadcast address. Everything in the middle would be our host addresses. So let's now use this chart with our powers of 2 to calculate the number of subnets and the number of hosts per subnet. Let's take the IP address of 10.1.1.0/24. If we perform our calculation in binary, we would write out all 24 of those bits as 1s, and the last 8 bits would be 0. The default for a class A address such as this one, though, would normally have our network address as the first 8 bits. But we are moving that line another 16 bits over so that we are borrowing an additional 16 bits for the subnet. That leaves us with 8 bits left over for the host. If we were to calculate the number of subnets using these powers of 2, we would take 2 to the number of subnet bits. And since we have 16 subnet bits, 2 to the power of 16 is 65,536. If we were to calculate number of hosts per subnet, it's 2 to the number of host bits minus 2. We have 8 host bits, which means 2 to the 8 minus 2 is 256 minus 2, or 254. So for this IP address of 10.1.1.0/24, we can have a maximum number of subnets of 65,536, and on each of those subnets, we can have a maximum of 254 devices. Let's calculate another one. We'll look at an IP address of 192.168.11.0/26. If we were to write out that /26, you can see there are 26 ones. That leaves us with 2 ones in the last octet, and we have 6 zeros left over at the end. If we calculate the class of this address, we look at the first octet, which is 192, which means this is a Class C address. That means it has a total number of 24 bits as the network address by default. But we borrowed a couple of extra bits into the last octet, so there are 2 additional bits available that we will call our subnet bits. And then, of course, we have the last 6 bits available as the host bits. Let's perform our calculation again. To calculate the number of subnets, we use 2 to the number of subnet bits. We have 2 bits left over as the subnet bits. 2 to the second power is 4. To calculate the host per subnet, we have 6 bits, so we take 2 to the 6th power and subtract 2 from there. That means we have 64 minus 2, or 62. So for this IP address of 192.168.11.0/26, we can create a total of 4 subnets, and on each of those subnets, we can have a total of 62 devices. This same process works with any type of subnet mask. Let's take, for example, 172.16.55.0/21. If we looked at this in binary, we would have 21 ones, which means we have 8 in the first octet, 8 in the second octet, and 5 ones in the third octet. Everything else, of course, would be zeros. And if we look at this IP address, it starts with 172, which by default would be a Class B address. So by default, the first 16 bits would be your network address. We borrowed some additional bits, in this case, 5 additional bits to be our subnet bits, and then everything left would be our 11 host bits. Performing our calculation again, we have 5 subnet bits, so to calculate the number of subnets, it's 2 to the 5th power, or 32. We have 11 host bits left over, so if we calculate that as 2 to the 11th power minus 2, that would be the same as 2048 minus 2, or a total of 2046 devices. So for this IP address of 172.16.55.0/21, we can have a total of 32 subnets, and on each of those subnets, we can have a maximum of 2046 devices. If you use this powers of 2 to perform these calculations, it can be a very quick way to determine what the number of subnets might be and what the host per subnet might be. But there are some shortcuts available that might get you to these values much faster, and in the next couple of videos, we'll give you some different options for calculating this process using those shortcuts.
When you're watching the other football but don't want to ask your friends, what's offsides? And how can I sound like I know a lot about the game? You can just ask Google all of that at once. Oh, so that's it.
When you don't use bounce, dryer heat can be a real monster. It turns clothes into static magnets for your hair. Use bounce to stop it. If you want static resistant clothes,
if you've been with us with the videos just prior to this one, then you've learned a lot about subnetting, masks, cider block notation, and other important fundamentals when it comes to subnetting via IP version 4. All of that work has brought us to this point where we can start to answer questions like this one. Here's a network layout, and it says, here's your IP address assignment. We've been given the IP address of 192.168.1.0/24. And this says we need an IP addressing scheme with more than one network address that can support 40 devices per subnet. That is the optimal number we're looking for, and we need to determine how to subnet this network address to be able to get 40 devices per subnet. Now you could of course write out all of the possibilities in decimal and binary and be able to calculate what the differences are with the number of networks and the number of hosts per network. For example, if you look at the default subnet mask that we were given, which is 255.255.255.0, you can see this is the binary representation of that subnet mask and the CIDR notation, which is a /24. That gives us one single network with 254 hosts per network. If we borrow 1 bit from the host side, so that we are at 255.255.255.128 as our subnet mask, or a /25, we would be able to create 2 networks with 126 hosts per network. We are getting closer to that number of 40. Let's keep going by borrowing another bit so that our subnet mask is 255.255.255.192 or /26. This allows us to have 4 networks with a total of 62 hosts on each of those subnets. This is certainly getting close to 40, but let's go one more step to see if we're getting even closer to that 40 value. The next step would be to borrow 1 more bit from the host side. So now we're borrowing 3 subnet bits, which means our subnet mask is 255, 255, 255, 224, or a /27. If we subnet it this way, we can have a maximum of 8 networks, but it would only allow for 30 hosts per network. This means that the optimal subnet mask, if we're looking for a total of 40 devices per subnet, would be the next one up, or the /26, which would give us 4 networks and a maximum of 62 hosts per network. Now we can certainly speed this process along by performing a calculation based on powers of 2. let's look to see how we might do that. We have a starting IP address of 192.168.1.0 and a subnet mask of 255.255.255.192. And based on this information, we can show the network address and the subnet mask in binary. And you'll notice in the subnet mask, we have the default number of bits for that address, plus the 2 extra bits that we borrowed from the host side. Visually, you can see where the 24 subnet bits might be, the 2 extra bits we borrowed for the subnet, and the 6 bits that are left over on the host side. If we were to now calculate the number of subnets and the number of hosts per subnets using this powers of 2 formula, we would take 2 to the second power, because the second power would be 2 bits, and that would be a total of 4 networks. We would determine the number of hosts per subnet by taking those 6 host bits that are left over at the end and calculating 2 to the 6th power minus 2, which would be 64 minus 2, for a total of 62 hosts per subnet. This is a relatively straightforward way to calculate the number of subnets and the number of hosts per subnet, but it requires you to perform a binary conversion and then count the number of bits to be able to calculate what that total might be at the end. There are some shortcuts that we can use, and in this video, we're going to look at a shortcut that uses the magic number method. These calculations are intended to give us 4 separate pieces of information. First, we need the network address or subnet ID. This would be the first address in the subnet. We also need a broadcast address. This is the last address in the subnet. We need the first available host address. This is an address that we can assign to a device on this subnet. And then we need the last available host address. We need to be able to calculate these as quickly as possible. Now, obviously, we could calculate this by converting everything to binary, looking at the subnet bits, and then calculating for every possible scenario what this particular network address might be and the subnet mask for each one of these. And for this particular IP address, when we determined there were 4 separate subnets, these are all the calculations that we would need to do to be able to calculate all of that information for all 4 of those subnets. You can see looking at this screen that there are a lot of separate binary to decimal conversions you'd have to do just to calculate those specific details for all 4 of those subnets. We can simplify this process by using the magic number shortcut. This allows us to perform subnet calculations very quickly, and very often we can do all of these calculations in our head. There's still a little bit of math involved with the magic number method, but it's limited to powers of 2 and some very simple addition and subtraction. You could even create a few charts that might help you with the process, but once you get accustomed to using this method, you'll find that you memorize very easily what's in the charts. You may not have to write them down at all during your exam. One chart that might help you is a chart that easily converts between a cider block notation and the decimal subnet mask notation. You can see an example of this might be to use a /9 is 255.128.0.0, /10 is 255.192.0.0, and so on. You will notice that there are some patterns after a while. For example, a /9 has the 128 as the number that is a bit different than a 0 or a 255, and a /17 also has a 128. So we could write this chart in a simplified form that shows a /9, a /17, and a /25 use the 128 as the decimal value. In the magic number method, we have a number of different tasks that we perform based on the octet that we're working with. So we might want to modify this cider to decimal chart to have something that's a little bit different. For example, if you wanted to see the cider notation for interesting octet 2, you can see it ranges from a /9 through /16. The cider block notation for interesting octet 3 would be /17 through /24, and the cider block notation for interesting octet 4 ranges from /25 to /30. You notice that we don't use /31 by default because it doesn't leave any room for any hosts on the subnet, and we don't use a /32 because that leaves 0 bits available for any host. For each of these columns with the cider block notation, you'll notice there is a magic number, and in a moment we'll learn how to use that magic number value. We can also put in this chart the subnet mask for an interesting octet, and you can see those mask values are also listed as well, starting at 128 and working all the way up to 255.
Looks like Jack just realized some people mix and match their game sense.
so he gave it a shot too. Is he the laundromat cool dude now? Mix, match, more happy with game.
Adobe Lightroom can enhance your dog's party photo. Easily remove any distraction in just a touch with generative remove. Now, your dog's the star of this party. Click to learn more.
Optionally, you can also create a host range chart where you can take an address block and then separate out what the differences are for that particular block. For example, an address block of 128 splits the network into two different pieces, 0 through 127 and 128 through 255. An address block of 64 hosts per block would be 0 through 63, 64 through 127, and so on. And you can continue this process with a host block of 32 hosts, 16 hosts, 8 hosts, and so on. So let's see how the magic number method works. It's a series of steps, and once you go through these a couple of times, they become very second nature. The first step is to convert the subnet mask to decimal if it's not in decimal already. From there, we need to identify the interesting octet. We'll talk about the interesting octet in just a moment. We then need to calculate the magic number, which is 256 minus the value of the interesting octet. We could then calculate the host range based on that, identify the network address, which would be the first address in that range, and then identify the broadcast address, which would be the last address in that range. So now let's take an IP version 4 subnetting problem and answer this problem using the magic number method. We'll start with this IP address of 165.245.77.14, and we've been given a subnet mask of 255.255.240.0. Our first step would be to put the subnet mask into the chart. You can see that it's already in decimal form, so we simply need to copy it over with 255.255.240.0. We can then also fill in the IP address that we've been given, which is 165.245.77.14. From here, we can start to make some decisions about what to put into this chart. For example, if the mask is 255, you simply copy the IP address down. So in this case, the mask is 255 in the first octet, so we're going to copy that down, which means our subnet ID will be copied down with the same number that's in the IP address row. Let's perform that same task again with the second octet. It is also 255, so we're going to copy that through. This 245 then will be brought down into the subnet ID row. We no longer have any octets with the 255, so our next step will be to look at any octets where the mask is 0. And if the mask is 0, we bring that 0 down to the subnet ID row. In this case, our last octet does have a 0, so we're going to copy that 0 all the way down and put it into the subnet ID row in the last octet. In our example, the subnet mask in the third octet is a 240. That is obviously not 0 and not 255, so that octet is our interesting octet. Now that we know the interesting octet, we can use that to calculate the subnet ID value for that particular octet. To be able to do that, we need to subtract the interesting octet subnet mask from 256. In our interesting octet, the subnet mask is 240. So if we subtract 240 from 256, we have the value of 16. This means our magic number is 16, and there would be 16 hosts available on that particular subnet. If we put our chart at the bottom that shows the 16 different hosts that you would have and the delineation between each one of those subnets, you can see that we have a range between 0 and 15, 16 through 31, 32 through 47, and so on. Now, if we look at the IP address, we can see the IP address is 77. And if we look on our chart, we can fit the 77 IP address in the range between 64 and 79. Since we're trying to determine the subnet ID, we take the very first number in that particular range, which would be 64, and we add that 64 into that subnet ID in our interesting octet. So for the IP address 165.245.77.14 that has a subnet mask of 255.255.240.0, the subnet ID is 165.245.64.0. Of course, not only do we need to know the subnet ID, but we also need to know the broadcast address. To calculate the broadcast address using the magic number method, it's a very similar process. We use the same chart with the same subnet mask and the subnet ID, but at the very bottom, we have broadcast address instead of subnet ID. The rules for determining the broadcast address are very similar to the rules we used for the subnet ID. If the subnet mask is 255, we copy the subnet ID all the way down into the broadcast address row. We have two of our octets that show a 255, so we'll do this for the first and the second octet. Here's where the rules are a little bit different when calculating the broadcast address versus calculating the subnet ID. If the mask is 0, we're going to write into that column a 255. And of course, if the subnet mask octet doesn't contain a 0 and it doesn't contain a 255, then that octet is our interesting octet.
You can have ants or guests. Not both. Choose guests.
New Cloud Paint Plush Blush for a pillowy, soft, sunset-inspired blush.
This will obviously be the same interesting octet when we're calculating the broadcast address as it was when we were calculating the subnet ID. To calculate the magic number, we perform the same process that we did earlier. We take 256, we subtract from that the value that's in that interesting octet mask, leaving us with a magic number of 16. To calculate the broadcast address for that interesting octet, we take the subnet ID and we add the magic number and subtract 1. So in this example, we use 64 because that is the number in our subnet ID. We add 16, which is our magic number. We subtract 1, and that leaves us with 79. So in this example, the broadcast address is 165.245.79.255. Now that we know the subnet ID and we know the broadcast address, calculating the first available IP address and the last available IP address is relatively straightforward. To calculate the first host, we would take the subnet ID and add 1. So the first address on the subnet is 165.245.64.1. To find the last usable address on this subnet, we take the broadcast address and subtract 1. So the last usable address on this subnet is 165.245.79.254. And that is the magic number process. Without doing any type of conversions between binary and decimal, we were able to calculate the subnet ID, the broadcast address, the first available IP address, and the last available IP address. Let's see how well we can use this magic number method with another example. We'll use the IP address of 10.180.122.244, and the subnet mask is 255.248.0.0. We will first fill in our chart, so we'll put our subnet mask in that mask row, and we'll put our IP address in the IP address row. We'll now look at our subnet mask, and everywhere there's a 255, we will use that to copy down the IP address. So in this case, in the first octet, we'll copy down that value of 10. Every place there is a 0, we're going to copy down the 0 and put that into the subnet ID row, and the third and the fourth octets both have a 0. Since we don't have a 0 or a 255 in this second octet, that means that this octet is our interesting octet. To calculate the magic number, we use 256, subtract the value that we have in that subnet mask range, which means we use 256 minus 248. So in this example, our magic number is 8. This means that each subnet has a total of 8 IP addresses that can be assigned, including our subnet ID and our broadcast ID. And we put the chart at the bottom that separates this into those multiples of 8. Now we need to find the IP address that is the starting for this particular block. If we look at our interesting octet, we know that the IP address is 180. So if we look at our chart, we can find that 180, which is in the block starting with 176. Since that starts with 176, we can simply fill that in, which means the subnet ID for this example will be 10.176.0.0. Now we need to find the broadcast address for this example. We'll use a similar process we did before, where if we had a 255 in the list, we're going to copy and bring down that subnet ID. So the first octet will simply copy down the number 10. Anywhere that we have a 0, we're going to copy down and put a 255, and we have zeros in both our third octet and our fourth octet. As we already know, the second octet is our interesting octet. So we're going to perform our calculation taking 256, subtracting 248 from that, meaning our magic number is 8. It's obviously the same magic number we calculated earlier. To calculate the broadcast address, we need to take the subnet ID, add the magic number, and subtract 1. So the example here would be 176 plus 8, since that's our magic number, and if we subtract 1, that leaves us with a number of 183. We'll add this to our broadcast address row, which means the broadcast address for this example is 10.183.255.255. Now that we've calculated the subnet ID and the broadcast address, it's relatively easy to determine the first host ID because we take the subnet ID and add 1. So the first available host on the subnet is 10.176.0.1. To determine the last address, we take the broadcast address and subtract 1. So in this case, it would be 10.183.255.254. Hopefully now you can see that the magic number method is a bit faster than going through the steps of converting to binary and then back to decimal again. But there are some ways to make this process even more efficient.
Razor bumps? Get a shave with a touch of aloe. Venus Extra Smooth Sensitive.
If you've already created a chart that shows all of the possibilities of an interesting octet cider block notation and has the magic number predefined along with the subnet mask for the interesting octet, you can perform this entire process in one single chart. Let's take the example of 172.16.242.133/27. If we look at our predefined chart, we know that /27 falls into the cider block notation for interesting octet 4. This means that octet 4 will have a decimal value of 224, so if we wanted to write out the entire subnet mask, it would be 255.255.255.224 because 224 is in that interesting octet number 4. The process for calculating the magic number is exactly the same as it was before. We take 256, we subtract that subnet mask in the interesting octet, which in this case is 224, which means our magic number is 32. There are 32 available addresses on each subnet of this particular IP address and subnet mask combination. Here's our chart, which is written out with 32 numbers in each of those sections. And if we look at our IP address that has a 133, we can move forward to where the 133 would be, and it is in the block that starts with a 128. Since we know it starts with a 128, that means that we can now change our fourth interesting octet to be that value as the subnet ID. So the subnet ID in this example would be 172.16.242.128. If you recall from our earlier calculations, to be able to calculate the broadcast information, we need to take the subnet ID value in the interesting octet, add that to the magic number, and subtract 1. So we'll take 128, we'll add 32 to make 160, we'll subtract 1, and that makes 159. So the broadcast address on this subnet is 172.16.242.159. Now that we know the subnet ID and the broadcast, we can calculate the first available IP address and the last available IP address. We add 1 to the subnet ID to determine the first IP, so the first IP would be 172.16.242.129. If we subtract 1 from the broadcast address, we would get 172.16.242.158. So there is the faster way to be able to calculate our subnet ID, our broadcast address, the first IP address, and the last IP address using the In previous videos, we've gone through the process of manually converting an IP address and subnet mask to binary, performing the proper calculations, and converting it back to decimal. We also looked at a shortcut called the magic number method that allows us to very quickly calculate the same information without performing that binary to decimal conversion. This shortcut is the 7-second subnetting shortcut, and this is the process that I use when calculating subnetting on an exam. This is a process very similar in structure to the magic number method, and indeed most of the shortcuts you find will have some variation of this within them. The part that's very different to the 7-second subnetting is that there is no math involved. You don't have to perform any calculations to determine a magic number, and everything you need will be predefined in the chart that we create at the very beginning. You'll find that the only math you end up doing is adding and subtracting the value of 1 to be able to calculate the first IP address and the last IP address. This is one of many available shortcuts to help you with the subnetting process, and I highly recommend you look at a number of different ones to find one that works for you. This 7-second subnetting process works equally well whether you are online taking this exam and using the online whiteboard, or if you have a physical whiteboard in front of you at a testing center.
This is the Dell AI PC, built for AI. It was designed to optimize your battery life, so it works longer without a charge, and in places without a charger.
Zibo works 24/7 to kill 99.9% of bugs trapped.
Well, welcome back from lunch,
Process of
everybody.
calculating the subnet is really
Good
how
to see you.
network into smaller pieces. You may start with a network
Hope
that
everybody
has
had a good
256 total hosts available, or you might break it up into smaller subnets,
Good
such
to
as
go.
a .128, where you might have 2 different subnets.
Well,
a
one thing we're going to
.192
get into
separates it
this
into 4 different
afternoon,
subnets. A
we have
.224
services once again coming in at 3 o'clock.
subnets, and so on.
And then they'll be here Wednesday again at 3 as well. So we'll just get in 45 minutes of some good talking and before they even get here. Prior to getting into this, are there any questions from anything we covered this morning? Any lingering questions from the weekend or any other coursework that we can collectively add more light
We
on?
also have a networks column. You would calculate that by starting with the
Seems
number
like everything,
2, doubling
everybody's
it all
good.
the way up until 256.
All right,
And then
you guys
have
know how to
a
get in touch with me if you
reference
know,
column
if you need
that
to.
starts with 128.
Okay, so here we go.
Divide by 2 all the way down until
All of this stuff builds on top of each other,
And
right?
to help with the conversion between the cider block notation.
Okay, so here we go. We have the screen up here. The day 4, we're going to get into configuring network addresses. Now, here's the beautiful part about this. Close my patio door real quick. Beautiful part about this is, when we're talking about configuring network addresses, we've already covered it. The big majority part of this lesson is cider. We've covered cider last week. That's why I wanted to get into it early. Ha 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 ha. So now what we're going to do is add a little bit of Brian. We're going to put a little bit of season on top. Season on. Some little season on. Just so it can make sense and round out the edges. How about that? So when we talk about configuring network addresses, a couple of things we're going to look into. Here's the domains that we're going to address. 1 and 5. 1 and 5. And again, this is day 4 of the slide presentation. We're going to talk about ports, protocols, and services, using appropriate IPv4 network addressing, summarizing, evolving use cases, and then some common issues for troubleshooting. And lastly, in 5.5, because 5 is the biggest domain here, just what appropriate tools will you use to solve some network issues? So it's just kind of walking through it. All right. So as we get into IP basics, what is the purpose of a package mailing label? What information is important to deliver for the delivering company? Now, as we see here, that's why I gave you that tool as well. Everything that's sent, and this is on networklessons.com too. So even if you put datagram header, everything we talk about in Network Plus is in the networklessons.com. Gives you a little bit more clarity with the mind map. So one thing you'll see that's familiar at the top of the IP header. Well, let me ask you a question, because I have a lot of students that in the past couldn't tell the difference in this.
Welcome back.
When data is being transmitted, when they slice it up like a cake, or before it gets sliced up, is there only one header for all that information? Meaning, if I have just 5 gigs of data, does one header get attached to 5 gigs, or is it to each segment?
It's
What do you think? Let me pull up my chat so I can follow along with you.
segmented.
Yes, you're correct, Charles. Each segment. Mr. T, you're correct. Each segment. Yep. So a couple of things remain the same, but you have to know the difference. Okay. Martin, are you still familiar with TCP?
All right,
UDP,
take
right? The
care.
difference between the two?
I'll see you on the next stream.
Okay. Which one is like registered mail?
All right, have a great day. See you next time.
You're correct, sir. It's the TCP. The reason why I asked you that,
appreciate
and you
you,
gave us
stopping by.
clarity on that, is because the datagram header for TCP will always be bigger than a UDP packet. TCP is connection oriented, so therefore it requires more fields to make sure the information is being received and being received with integrity. UDP, like a Netflix movie, Elaine, do I care if you get it or not? UDP?
No.
Not really.
No.
I'm sacrificing integrity over speed. I want to send it to them as quick as I can because I have tons of customers I need to facilitate this with, and I don't have time for registered mail. It's going to bog down my network and steal bandwidth. So that's why with UDP, like, X gonna give it to you. I'm gonna give it to you. Yep.
Yeah.
So I'm just gonna give it to you. Really don't care what you do with it. All right. So if we look at this header, a couple of things that you're gonna see at the top. X gonna give it to. Okay, let me stop. You guys gonna get me. This is already like this dude.
Yeah.
Now in binary, I have to make sure we have one key point pointed out here. Dad joke. One key point pointed out.
Yeah.
All right, I'm gonna move on. When we're talking about figuring out IP addresses or CIDR, we always go 1 to 32. But what you see here on the IP header, remember in binary, they treat that as a digit.
Yeah. So
So
0
now
0
it's only, when you're talking binary headers, 1 to 30, 0 to 31. You get me? So all they did was slide one number because 0 is a number when it comes to binary.
Mm-hmm.
So what you're going to have is the version. The version is IPv4 data. Then you're going to have the header length. Now, these are in bits. 0 to 4, so that's 4 bits. 4 more bits. 8 bits is the difference. Anything that's in these boxes. Right here, 16 to 31, total length of the header is going to go here. Mine's just not cooperating with me. Okay. Then you have the identification, the flags, fragment, offset, time to live for the packet, which is important, the protocol used, and then the error correction checksum to make sure everything gets received in its proper order for us to rebuild, let's keep the theme, the wedding cake, right? That was sliced up into 4 slices, right? Mm-hmm. So all in here, they make sure they make room for it. They can put all of these fragments back together in order to put the total package back together in the right order. Then you have the source address, destination address, any additional options, but here's where the payload's going to be. Whatever it's sending is going to get attached. It's just like the box. If you need to put something in here to get shipped, Amazon will put it inside the box. Inside the box is the payload. This is the cardboard box, and the payload sits inside of it. Okay? So that's how you're going to read the IPv4 header. As this relates to addressing and forwarding, here we go. Here's the trash we were looking at. You'll be presented with something like this on the exam. And real quick, /24. Somebody tell me what we're looking at. What's the telemetry? Go. We gotta get quick at looking at this stuff.
24, we're looking at.
Then we can start looking if this is a public or private to see what side of the fence it sits on. So /24, what we looking at, Mr. T?
Looking at 512.
Real quick snapshot. And then Charles, you can tell us about the or Martin. Let's say Martin. Martin, can you try to give us some details on /28s? All right, so Mr. T says 512. You can put 500. Oh, wait a minute. /24. Yeah, we're at 256. Yep. So 256 devices can sit there. What's our subnet mask? 255, correct.
255.
So it'd be 255, 255, 255, placeholder 0. We're in the third octet. Everything shifts over 1. Doop. Because it's a /24. All right. Martin, you want to give us a try on 28? What are we looking here? How many devices can we put on here? On the 28. And if you need, okay, he says 16 hosts. Okay, so 16. What's the subnet mask on that bit position when we go straight up? What's the subnet mask? Because we're in a class C now, so we know what the prefix is going to be.
240.
Yep, 240. He's got it. Boom. So that's the telemetry we're looking at. The next thing we look at, we want to make sure that this can accommodate the IP of the device range that they have. All right. Wait a minute. 198.51. Is that public or private?
198.
Bring up your CIDR list. Is this a private network we're looking at or an ISP network?
198.
Now, we all use the same addressing schemes. They just use the public address scheme. We use the private address scheme. Everything that the ISP uses is routable on the internet.
198 public.
Public. Bingo. See, this is why the ISP exterior, ISP interior. Bingo. So now you see how the addressing scheme can differ when they're using it from when we're using it. Great example. Next. As we said, this relates to how something's being shipped for you. Isn't this they're using flowers? Hey, let me find you. We know that ARP will help us find anyone. Can anyone remember what is the purpose of ARP? What will ARP do that? ARP resolution. What does it resolve?
Address resolution protocol.
Address resolution. I wouldn't say duplicate IP, but IP is it? There is IP. IP to what? An IP address to what? It will resolve it to another address to make sure it's being sent to the right place. Correct. Yep. It will resolve it to the physical address. Yes. So ARP is, our address resolution protocol is, Everything has an IP address that's on a network, so they can all kind of interconnect and talk. Doesn't matter if it's a 69 or whatever. It's an address given, and then it resolves it to the MAC address in order to give validity to make sure it is sending it to the proper place. All right? So, to make it even more simpler than that, ARP, since it's the responsibility of layer 2, says, oh, Aaliyah's computer sits over here. Her MAC address is over here. Let's see what the network gave her. Oh, they gave her 192.168. Yeah, it seems to be it seems to be the same computer. Here you go. Hands it to you. Address resolution protocol. Access to subnet versus remote using the ARP. If we're looking over here, here's the ARP request, here's the ARP reply. Well, we're looking at this over here for one, host packet .17, sends it to 19 as the SRC and as the source and the destination address are the same on the network. It checks its ARP table cache, but it doesn't find an entry in the router or the switch. Okay? So what happens is 17 broadcasts the ARP requests. So therefore the ARP request will go up to the switch. The switch doesn't see it, sends it up, comes back down. Hosts that do not own 19 ignore the broadcast. So basically, there was an address entry missing in the address table. Since the router knew that there was an address attached to 19, they're broadcasting, yo, y'all see Mike? Then what happens is the switch comes down and says, oh, I got it. 19 replied with their MAC address. Let me go ahead and make an entry. Let's make a correction. And then anytime after that, as it says over here, now they can talk. 19 is recognized by the IP address of 17. It will log their address of 19 in the switch in the router, and then life goes on. Now, all of this stuff is happening at nanoseconds, like super fast. Okay? And we say that IP tables and MAC tables are built off of forwarded requests, not receipt. So they always want to make sure you are where you're supposed to be as they do that. Mr. T says change logical is a physical address. Yes. I think I addressed that one already. But yes, you are correct. Okay, let's look at unicast and broadcast addressing. If we're looking at unicast or multicast, there's a lot of stuff addressed only to the destination IP, sends only to the destination. That's in a unicast. If we want to set up a network where we only want one device talking directly to another, yeah, we have to set this up. It's either going to be in unicast, multicast, and broadcast, we know is automatic. That address is already reserved. But if there is some appliances that you want just to exchange information directly, you have to log into that switch and or router and configure that manually. Okay? We look at the example up here. Let's say there were several routers. Let's say we wanted this router to always communicate with this router and or over here. So we'll make believe there's two of them here. We could set up a unicast at kind of like highway. So anytime this gets something coming in here, we can open up a route and it will go directly to here. We have to configure the port and anything that goes along with this to point to that IP address. And then we have to configure this to talk back if we wanted to do the same thing. So if we own both of these devices, it's important to know we have to get into the command line, config T, configure terminal, bring up the port, but drop the IP address subnet, click unicast, do what you need to do, or enter a series commands, save it, and then you're on your way. But you have to do the same thing to the other half if you needed to talk back. Does that make sense? Now, this is only going to happen primarily if you own all of your own devices. They all have to sit in your domain. Or you have to get permission for the person that owns that device in order to manage it. Or you have agreed upon where Martin says, hey, understand you need your server to unicast to my server. I'm like, yes, sir, there's some stuff we need to send over all the time. Martin's going to be like, well, we'll make it a special exception. Send me over your data. We'll vet you and we'll let you come in. We'll let you send stuff. And he'll go in and configure. If it's an outside organization, he'll have to go in and put their MAC address, their number, their organization, their IP address they're forwarding from, blah, blah, blah. And Martin has to approve that, okay, in order for it to come into his domain on behalf of the other company, because it's something we might need, okay? So we have to take all of that into consideration and security. All right. So here with multicast address to a specific group of hosts, IP addresses. So it's one to many. Or the anycast address to any one device out of a group of devices, typically the closest one, used for load balancing and redundancy. So the anycast is used for load balancing. Okay. And what's an example of load balancing? We all use Google, right? Request comes in, your local Google server farm in your area has a bazillion million requests per second. You might have, to keep this simple, 2 servers. So when a request comes in from Mike, oh, Mike, you go that way. Martin, you go that way. Oh, Charles, you go that way. Brian, you go that way. Aaliyah, you go that way. Wait, Mr. T, you got to go this way too, because we got network lagging over here. You get what I'm saying? We got a lot of bandwidth usage, so we'll keep everybody over here. Elaine, oh, you're the next one in? Great, you're going over here. So it balances the load in all the service requests from the server to bring you back your information. Okay? The one thing I want to clarify is that you want to know on the exam, this will be an option for you to pick a set of IP addresses. Do not use it. That's multicast. On the exam, you will not use a multicast. There'll be a question. What does a multicast address start with? Oh, that's D? Out of a class A, B, C, D. D is multicast addresses. They all start with 224. Why would I even use that on a home network? No. So you'll pick that. In a PBQ, you're not using 224 addresses. Don't even think about it. What did I just say, Charles, about 224 addresses on a PBQ? What's the likelihood of you using them?
Not very likely. 0.
0. Now, will you see them on there as a selection?
Mm-hmm.
Yep. But like Charles said, don't do that. Wave a finger at it. Charles, let me ask you again. Will you use that 224 address? I will not be picking it, James. Good. Thank you very much. Thanks for playing along. But yeah, so that's what you're gonna see. Now this looks familiar. Here we go. I'm not teaching this. I'm not gonna undo what I just did. Do you think I'm crazy? I just got you to this point understanding it. Do you think I'm gonna go over it again? No, sorry.
Yeah.
Read that at your leisure. I got you where I need you to be. You understand? Now, this looks familiar. Binary conversion. 128, 64, 32, 0, 16, 8, 1. There you go.
Yeah, this is useful.
Each one represents a space. If you're trying to figure out what in the different octets what the numbers are, each octet you'll use the same chart. Looks the same as CIDR, right? But instead of using it for conversion, we use it in CIDR for knowing the number of hosts you can put on a network.
197.
So if you want to know what 192 is, you just say, oh, I would add the sum of these two, which creates 192. That's my first octet. So I would turn them on. 1000. Get it? 11000000.
It simplifies it too.
Elaine's typing something. I wonder what he's typing. Yes, this simplifies it too. You're correct. Yep. The sum of whatever number you need to make that IP address in each octet. Just add them together. If you use that number, you put a 1 over it, you're turning on the light switch, saying it's being used.
Yeah.
Like Motel 6, we'll turn the light on for you. This number's we used, right? If it's not being used, turn the light switch off. Simple. Yeah. We already know net ID, host ID. We know subnet mask. Identifies the network portion of the IP address. The network ID matches the local network transmission, meaning all the IP addresses belong on that subnet. Helps devices determine which network it belongs to. Pretty simple there. This will bring you back to your, 1202 days? Determining subnet mask and changing binary back to dot decimal and vice versa. That's what it looks like. Now on the Network Plus exam, you will have to turn a dot decimal, a binary back to a dot decimal.
Network?
Yep. They'll have a multiple choice of what it should be.
Oh, okay.
So they'll present to you the whole binary number in 32 digits. You have to count 8 spaces. 1, 2, 3, 4, 5, 6, 7, 8, dot. 1, 2, 3, 4, 5, 6, 7, 8, dot. Separate them all. And then the positions where the 1 are, add those back up to turn it back to the real number. Like they've done here. 8 positions. 1, 2, 3, 4, 5, 6, 7, 8. They're going to show you this. If you did your chart, 128, 64, 32, 16, 8, 4, 2, 1. All they did was add 128 and 64. Bam, 192. Move to the next one. Okay, whatever these numbers are that are turned on, 128, 64, 32, 16, 8. Oh, so they used that 32, 8, bam, 168.
Yep. And then they just use 1.
And so on and so forth. Of course, the last number is 1. That's an easy thing. 1.
Yeah.
Everything else gets turned off. It's the same digit.
Yeah.
Charles says, are they gonna do this to us on the yes. You're gonna have one question that gives you this. Or they're gonna give you this and say, what's the binary? So you have to convert it. So quickly, you need to sit down, 128, 64, 32, 16. No matter what, this should be written down because you're gonna use it for CIDR and you're gonna use it for converting. You should be writing that the whole time when you sit down. It's going to be used for dot decimal conversion to binary or vice versa. And you're going to use that as one of your starting rows in CIDR. It serves 2 purposes. The proctor is going to say, trying to count. And think I'm throwing up gang signs. Is that hold on, is that a 0? Cruising down the street in my 6'4". My Easy E bike. Yeah. So that's what we're looking at. All right, there you guys go. I don't know what's going on. My neck works freezing a little bit. Give me 1 second. Let me see what's going on. Let me troubleshoot something real quick.
Yeah.
All right, I'm back. So this is what we have here. Now, this is an example of your Soho network. Okay. We know, well, you guys are coming along. So I'm at the point now, I would like for you to explain it to me because it helps you in the exam.
1.4.
So with the Soho range, with the ranges, can somebody type what's giving out all these IP addresses? Let's start here. Where does that address belong to?
192.
Yep, Class C,
Yeah, it's a
private, CP. All right. What address is this? What does this belong to? So if you were to cut your router, we know. See, I just gave you the answer. It's the private side of your router. I don't have my tablet hooked up, so you're going to get some crazy looking writing. Looks like I'm drunk. I'm not. Okay. So what's sitting inside of the router that gives you these addresses? DACP. Y'all got it. I don't know why it's a delay on Zoom today. Okay. DACP. Bam. So I got another question. This is going to confuse y'all. Because like, huh? But y'all know the answer. Just think about it real quick. This is a Class C address. Which part of this is the network and which part is the host?
192.
Let's say about octets. Which octets? There you go. Mr. T said it in the simplest way possible. The fourth is the host. That means the rest is the network.
Yep.
I like the way. So the reason why this matches in a Class C is because anything that has 255, 255, 255 turned on, it has to match the network side. If this of the IP address, if this were a Class B, that matches the network side. That means in the IPv4 address, the first 2 octets are the network. The last 2 belong to the host. Same thing in the Class A. That's why I said I'm gonna say it over and over and over. The address scheme that has 255 turned on in the Class A, it's right there. 255. That's the network side. It matches any IP you're going to use for Class A. First octet will always belong to the network because they turn on all the digits. It belongs on that network. Does that make sense? If it doesn't, please let me know. All right, cool. So that's a quick way that you can use that. Your default gateway will be the router. In a Soho environment, you have at least 3 areas that may share the same address. What are they? We just talked about this. And Kevin, on a Soho environment, you may have 3 areas that share the same IP address. Bingo. DNS, default gateway, and we could add maybe DHCP because the router gives it out, right? But primarily, the DNS and the default gateway on a Soho will always be the same address because your home is the DNS. All right. Is Zoom acting wonky for you guys too? It's up and down. Yeah, it's doing that to me too. So if we get disconnected, just log back in at your leisure. Okay. Yeah. For y'all, it's doing the same thing for me. So I don't know what's going on. We'll just play it by ear. If we just get disconnected, just log back in. That's all. It's all good. And then the last IP address in the range will be your broadcast address. We already talked about public and private addressing. Y'all know the two. ISPs use public. Private addressing, we have our own scheme that we'll use because it saves address space. Yeah, I'm getting a delay. I don't know what's going on. Hold on one second. I'm gonna stop there while the getting is good. Okay. But that is CIDR. The rest of this lesson that we were supposed to go through was CIDR, in which I've already taught you. Again, I do not want to go back over it on the slides because some people will get confused. But it's there if you want to look at it. All right. And if you have any questions, please let me know. There is one slide that we will go over probably toward the end of the day that talks about VLSM. Variable length subnetting, okay, or subnet mask. All that means is that I have to pick the appropriate slash in order for my network to hold as many addresses as I need to create CIDR. That's it. I don't use more than what I need, and I can put that into the DHCP or the routing table, right? That's what's going on. All right. So this is what I'm going to do. I want to make sure I don't want to have anything disrupting career services when they come in. So what I'm going to do is restart my computer. All right? Because something's going on here. I just want to make sure.
Yeah.
Please log back in within the next 10 minutes, okay? All right, I'll see you then. I'm going to restart my computer.
All right.
Recording in progress.
All right, we are back if you are there. We get cameras back on and wait for folks to jump back in. All right, good, it's working. All right, so we'll wait for everybody to get back in. Yeah, that was weird. My system was doing an update of some kind, and it was taking all of my resources.
Oh.
Because I looked at my system info, and then it froze on me. Then I had to do a hard reset. Crazy.
Probably.
I paused all my updates for like
probably a CPU.
A month. All right, everybody. So, yeah, Charles, I was letting them know my resources were being used because some update was being put, and it was just dragging everything.
Yeah.
My computer had froze. I had to do a hard reset. He said, I know a guy. Got to update the RAM. I know a guy. Here's the thing. There's 32 gigs in here. All RAM ain't made equal. Something's going on. I got a leak somewhere. Crazy. Yeah. Tell your client to download RAM from Russia. Now that's funny. Download RAM. Oh my gosh. Let's see what we got here. Wow, now I'm getting like, what is going on? Now I'm getting updates. Okay. That doesn't apply to me, so I'm not going to pay attention to it. All right, so what we'll do, since with binary and stuff, we're good there. What's it? Elaine says my Apple laptop does it when I'm editing video. Yeah, something's quirky's going on. But luckily, I'm in a room full of IT experts, so y'all can walk me through it. Y'all are great.
Yeah.
So this is what we're gonna do, since it's just us right now. Michael will be back in a sec. Let's go. Step one. Turn it on. We'll get started on an early break. See if you can be back here by 2:58 or at 3. Career services will be in.
Yeah.
So let's go ahead and take advantage of this time for that so you can get settled in. How about that?
Yep.
And I'll see you then. All right.
Is that better now for you?
Oh my God! There was a system update happening.
You test volume. Test.
Can you hear me now?
I hear you now.
Okay. Ooh, I don't know how to turn. See, he's acting wonky. So a system update was going on. So I said, let me go in sysinfo real quick to see what's happening in performance. My RAM was like up to here, and my CPU was being. I'm like, what? So I looked real quick, and when I looked, it froze.
Gotcha.
So I was like, yeah, let me just do a hard reset and start over again. So
noted. Okay.
But y'all go ahead and take a break because career services will be in here at like 3. So Mike, if you got something to do, I'll just see you here in 10 minutes. All right. When Jewel will be back.
Nice.
All right.
Addresses have a 128-bit address, which gives us a much larger address space to use when we're assigning these addresses to all of those many devices on the internet. Another way to visualize this would be to say that every grain of sand on Earth could have 45 quintillion unique IP version 6 addresses. You can see that this larger address space with IP version 6 resolves that IP address constraint that we have with IP version 4. There are a number of differences between an IP version 4 address and an IP version 6 address. This is an IP version 6 address, FE80:5D18:652:6FFD:8F52. You can see that is a very different style of addressing than IP version 4, where we were only dealing with decimal numbers and periods. In IP version 6, we are using hexadecimal values, and we're separating those with a colon. If we were to write out that entire address into its entire 128-bit form, you can see that it is completely listed here, and that is a much larger address than we deal with IP version 4. If you wanted to view this in a binary form, you can see that we have the representation of that same address listed in binary. You can see here that each section of an IP version 6 address that we separate with colons is 16 bits in length. You can see the 16 ones and zeros listed in each one of those sections. This also means that each section is 2 bytes in length. You may also see it represented as 2 octets in length. So in total, the IP version 6 address is a total of 128 bits or 16 bytes in total. You might see an IP version 6 address written out with all 128 bits being shown on the screen. But you might also see these addresses listed in a compressed form, which makes it much easier to be able to read. When we're using this compressed form of an IPv6 address, there are a number of rules to keep in mind. One of those rules, if there are groups of zeros that are together, we can abbreviate that entire group by simply replacing those zeros with a double colon. We can only do this one time in an address, but usually that's all we need to make this address much easier to read. We also can remove leading zeros from each group within the IP version 6 address. Let's take an IPv6 address and perform this compression to see what that would look like. The IPv6 address we'll work with is 2600 colon delta 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 colon 1111 colon 0001 colon 000. You can see the zeros go all the way through to the end to the number 1. Our first rule here is that we can remove any of these leading zeros that might be in all of these groups. This means that our IPv6 address with those zeros removed would be 2600 DDDD1111, and then each of those leading zeros in all of the remaining groups would be removed. You'll also notice that there are 3 individual groups here that are simply zeros. And one way that we can simplify the writing of this IP address is to abbreviate 2 or more of those groups together with double colons. So all 3 of those zeros would be removed, and we would replace them with one series of double colons. This means that we would have a very simplified form of this address. Instead of having all 128 bits of that address shown on the screen, the address is now simply written as 2600 DDDD1111 1 double colon and 1. Let's look at another IPv6 address and perform the same compression. This IPv6 address is 2601.04c3 4002 BE00, 3 groups of zeros, and it ends with 0066. Our first step would be to remove the leading zeros in all of this. We have our second group has 1 0 in front of it, and there are a number of groups at the end that have leading zeros that we can simply get rid of. You'll notice in this example that there are 3 different groups of zeros that are combined together, so we can remove all 3 of those zeros and replace it with a double colon. This greatly simplifies this much longer address into 2601 4 Charlie 3 4002 BE00 colon 66. As you can see, the IP version 6 addresses are very different than the IPv4 addresses that we're used to seeing. And because of this, IP version 6 and IP version 4 cannot directly communicate with each other. Therefore, we need some method to be able to have these older legacy systems that only understand IP version 4 be able to communicate on our more modern IP version 6 networks. This creates some communication challenges when trying to combine IP version 4 and IP version 6, but fortunately there are a number of different ways to bridge this gap.
Years of hard work. Decades of dedication. Committed to giving back. You've been there, done that, and you're still here for more. So now that you're 50 or older and at increased risk for pneumococcal pneumonia and IPD, be proactive with Capvaxive. A vaccine specifically designed for adults to help protect against pneumonia, an invasive disease caused by certain types of pneumococcal bacteria.
One of these methods would be to tunnel the traffic. We would either tunnel IP version 4 within IP version 6 or tunnel IP version 6 within IP version 4. This would give us a way to communicate even across networks that were very different than the protocol that we were using. Another way to bridge this gap would be to use a dual stack configuration where the system that you're using can communicate with both IP version 4 and IP version 6. And another way would be through the process of translation, where we are converting one IP version 4 address into a completely different IP version 6 address. Obviously, these are stopgap measures, and they're not designed to be a long-term solution for connecting these different types of networks together. Ideally, the best long-term solution would be for all of us to move to IP version 6, and hopefully one day we'll be able to take all of our systems and be able to run them as a pure IPv6 environment. In the early days of IPv6, where we did not have a lot of infrastructure devices that understood IPv6, we did a lot of tunneling of that IPv6 traffic. This was obviously designed to be a short-term use, and these days it's not very common to still see this tunneling being used. One of these tunneling types is 6-to-4 addressing. This allows us to send IP version 6 traffic over an existing IP version 4 network. It creates an IPv6 address based on the IP version 4 address that you're currently using, but it requires you to have a specialized relay router to be able to transfer that data. And one big disadvantage of 6-to-4 addressing is it does not support any type of network address translation. Because of both those limitations and because we have more devices these days that natively support IP version 6, we no longer commonly see 6-to-4 being used, and this functionality has now been removed from all Windows versions. If you can tunnel IP version 6 traffic across an IPv4 network, you can also do the reverse with 4in6 tunneling, where we can tunnel IP version 4 traffic across an existing IP version 6 network. Both of these were used as relatively short-term solutions, and it's very unusual to find 6-to-4 addressing or 4in6 tunneling still being used on our enterprise networks. A much more common method of migration, and one you're probably using on your existing system, is dual stack routing. This allows us to use both IP version 4 and IP version 6 at the same time on the same system. You might have an Ethernet adapter on your computer, and that Ethernet adapter has both an IP version 4 address assigned to it and an IP version 6 address assigned to it. The IP version 4 side works exactly the same as it always has, and all of your applications that use IP version 4 can use that address to be able to communicate onto the network. If you have applications that would prefer using IPv6, they can use the IPv6 addressing associated with that Ethernet adapter. These applications will use the IPv6 address that is assigned to your Ethernet adapter. It will use the routing table within your system for IPv6, which is a different routing table than you're using for IP version 4, and all of the IPv6 settings that are associated are all independent from...
Hello, Miss Jewel. How are you doing today?
This tends to be...
All right, how are you guys doing?
We're doing good. Doing good.
That's good. Bear with me a second. Okay. Looks like it's 6 o'clock on the dot, so we'll go ahead and get started. What I'm gonna do is I'm gonna share my screen. We have a good
our server. This server is going to make a DNS request on our behalf to that IPv4
Give me a thumbs up
network,
if you got that
which is
email.
the DNS server that is used by ProfessorMesser.com. And of course, that
Thumbs
DNS
up.
server
Got
is
it?
going
Okay,
to
great.
respond back with
Okay,
the
so
IPv4 address.
what I'll say is that interview success
Once an
handout that
IPv4
actually
address
pertains to
is
this
received
particular
by the DNS
presentation.
server,
Outside of that, you're going to
it
see the
creates
all-in-one
an
interview prep
IPv6
document.
version
That
of that
document in
address
particular
that
is
redirects it
actually
to that
essentially like a walkthrough. It's essentially
The
helping you to
IPv6
kind of come up
client
with
thinks it's
responses
received
to
the
different kinds of
IPv6
interview
address of
questions. So it's basically like a
professormesser.com,
worksheet,
but
if that
it's
makes
really
sense.
received the
And then
IPv6 address of
it says Word highlight version
out.
interview handout.
So now when that
That's also
browser
just giving other really good
communicates with
insights
professormesser.com,
that are good to
it
know when
sends
it comes
this
to
initial
prepping
send
for
to that
interviews,
IPv6
especially
address
some of the
to
insights that
router.
you'll see on that
That router
figure
is
that's on that
responsible
first
for
page and
performing the
second
network
page as
address
well.
translation,
So
where
with
it
that being
enables
said, I
the
just wanted to make sure that you
IPv6
guys have
address
some
that
good
we use
materials to prepare for that. I will say, looking at the schedule of how we have everything laid out for this particular class, what's going to happen next week is I'm going to come in and basically we will start doing mock interviews. So essentially, you guys have a week from today to kind of work through that worksheet and refer to those materials in order to prepare for your mock interviews. And actually, you want to know what? Give me a second here. I'm going to drop another document into the chat. So just bear with me a second.
AI summaries save 97 minutes per week. What say you, Rocks from Gosney?
For the mock interview, what we're going to do is we're going to use, basically I created like a fictional company and I created an entry help desk role. I understand not all of you are interested in going into help desk positions, but this makes the mock interview process a lot easier because we're referring to a specific role and everybody knows which role that role is in particular. So I'm dropping a link in the chat right now. Go ahead and give me a thumbs up once you've downloaded it.
It's a relatively straightforward process, although there is a lot of technology under the surface that makes this happen. But if we were to look at this in a very simplified form, we could see that the router is performing a series of relatively
All right, thank you, Aaliyah. All right, thank you, Elaine. All right. I want to make sure everybody has downloaded that document. Thank you, Charles.
To the packet, identifies what the destination IP address is, and makes a note of where it should
All right,
be
thank you,
sending
Brian
its
and
traffic.
Martin. All right, looks like everyone gave me a thumbs up. Okay, great. Okay, so with that being said, the way that we'll kind of use that particular role is entry-level help desk roles are great to help you prepare for a variety of roles in IT. Basically, it's like an entry-level role. I wanted to choose something that has some element of being universal. So even if you're interested in cybersecurity, even if you're interested in going into, for example, like a system admin, network admin, that role will have some elements that overlap. So when it comes to prepping for that role, you can kind of use the elements that overlap with it in order to really play up the skill set that you have and kind of play up the focus on how you would like to utilize that skill set when it comes to work. With that being said, give me a thumbs up. You guys can all see my screen?
That routing table becomes very important.
Yes, okay, great. All right, so when it comes to interviewing, let's just get actually some quick insight. What have you guys' experience been actually going out on job interviews so far? You can type it in the chat, you can speak up. Have you guys had good experiences going in for interviews, no experiences, bad experiences? I just kind of want to get a little bit of a idea of how it's gone for you guys in the past. All right, Aaliyah says no experience. All right, Aaliyah, you're not the first to say that. I've seen that before. Anybody else? Okay, experiences. All right, Kapasan, that's good. Better than bad, at least. $50-50. I've seen that too. All right, and I guess a follow-up question for those of you that have had okay experiences or 50-50, what were some of the elements? Like if you think about those interviews that went really well versus those that didn't, what were some of the distinguishing factors? Okay, the vibe, all right. Okay, do you mean that you felt like you didn't mesh well with the interviewer, or you did feel like you meshed well with the interviewer? Okay, all right. Good to know. Okay, you're able to build rapport with them pretty quickly. All right. Anything else? Any other factors that contributed? If you guys, and this is open to everybody, if you've ever had good interviews versus bad interviews, what were some of the distinguishing factors? I guess mum's the word. All right. What we'll do is we're going to talk about some of the factors that can really help you to make sure that you have a good interview. So when it comes to interviewing, you'll see some figures on that first little section in that interview success toolkit. The reality of interviews, about 20% of applicants actually get an interview. And out of those, 1 in 5 gets the offer. I would say even it could be even slimmer than that, just because if it's a position that hundreds of people are applying to, but your resume, for example, is optimized to be able to get through the applicant tracking system, or conversely, maybe you know somebody that's actually recruiting for that role, that can increase your chances of actually getting pulled in for an interview. So I would say it could be up to 20%, but it could be a lot slimmer, especially in instances where it's a situation that there's hundreds of people applying for that role. Okay. Hiring managers do make up their minds pretty quickly as to whether they think that you're qualified and whether they actually want to hire you for the position. And so if you look at the figure on that handout that I sent you guys will see a man with a tuxedo, and they'll talk about all the many different factors that go into play. Keep those things into mind, because if you keep them into mind, and you can set yourself up for success, it can be really helpful in helping you to secure that position. A figure being 5 to 7 interviews before actually landing a job. But with that being said, again, even if it takes you 5 to 7 interviews before landing a job, if your primary way of finding work is going to be through applying to a bunch of different roles, you're going to have to apply to a lot of roles before you even get those 5 to 7 interviews, if that makes sense. I've seen some figures of maybe between like 40 to 60 or even 60 to 80 positions that you would apply to before you even interview and you're actually able to get a job offer. So Michael, you said 5 seems like too many. Explain.
It's like jumping through hoops to go through all those interviews and not even get hired. It just seems like it was just a waste of time.
I would say I can understand your perspective. Conversely, you could think about it like this. Even if it's a situation where you interview for a position and you're not offered the role, I've even had situations myself where I interviewed well. They felt like the other candidate was more qualified, but they reached right back out to me and said, hey, we don't think you were qualified for this particular role, but would you be willing to interview for this other role instead? I've actually had job offers for other roles that I didn't even interview for or apply for because of the fact that I interviewed so well, and I was able to take it in stride and made such a positive experience where they still were like, hey, we want you to actually come and work with us, even if it's not the role originally that you were intending to interview and actually secure. So what I'm saying is it's actually not a bad thing to go to multiple interviews because it gives you more practice. It helps you become more confident. And in the process, you can be building your network, building more connections, and possibly finding yourself on the end of having other job offers come up. Actually, yeah, if I'm thinking about those situations, I actually didn't end up even having to interview for the other positions because I already went through the interview process for a different position. So it can work out in that way, if that makes sense. When it comes to acing the interview overall, the thing that I want to really make clear to you guys is foundationally, you need to understand yourself and you need to understand the position. What does that mean practically? I highly recommend printing off a copy of your resume or bringing up a copy of your resume, going through and highlighting the job description and comparing it to your resume to really see where's the overlap between the skills and experience that they're looking for and where you actually have those skills and experience displayed through your prior experience. Okay, so first things first is the elevator pitch. This is often conveyed when you are asked the question, tell me about yourself. So anybody want to volunteer? How many of you feel like you kind of got this one down pat when it comes to responding to an interviewer and letting them know about yourself and your professional qualifications? Aaliyah says no. Okay, Aaliyah, I won't call on you. One thing I really want to make clear as well is, yes, interviewing can be challenging, but interviewing is a skill that you can develop. Okay? I will let you guys know there's a time in my life, listen, I absolutely sucked at interviewing. I was bad, believe me. And what do you know? I did not get the job offers that I wanted. And it kind of got to a point of me going to so many interviews, bombing those interviews, and really getting to a situation where I really needed a job, but I wasn't able to secure it, that I feel like it made me even worse, if that makes sense. Because it kind of put me mentally into a panic, where it's like, okay, I don't really understand what I'm doing wrong. I'm trying as hard as I can, and things are just not panning out. So I really had to take a step back and really reflect. And I actually went and accessed a lot of different resources and put in a lot of time and practice to help me to improve in my interview skills. And I can say that's why I am as good of an interviewer as I am today, because I actually worked on that skill set. But with that being said, nobody wants to jump in and give their response of how they respond to tell me about yourself? No? All right. Okay, you guys, you already have that entry-level help desk role that I dropped in the chat, right? I'll let you guys know that's the entry-level help desk role. The two primary skill sets that are important to have for that particular role are, you need to have technical skills as far as working with hardware, software, working with networks, troubleshooting, and then also have good people skills. Let's just put it that way. So how about this? We can actually, I'll give you guys a sample. Tell me about yourself, and we can kind of work through so that you guys can get some insights into what comprises a good tell me about yourself response. So who wants to take the role of the interviewer, and I'll take the role of the interviewee. Michael's eye says, don't ask me.
a switch, and our telephone cables would connect to a PBX, or a private branch exchange. With the advent of voice over IP technologies, we can get rid of that individual voice cable completely and run both voice and data over the same Ethernet connection. And in many enterprise environments, you have a switch that is on the network, you have telephone that you would connect to the switch, and on the back of the telephone is an additional Ethernet cable where you can plug in your local computing device. One of the challenges that comes with adding both voice and data to the same network is that you now have a great deal of contention between both of those technologies. Data likes to use a lot of bursty bandwidth on the network, but voice communication prefers a very consistent level of access. If there's any type of congestion or a lot of usage on the network, this could affect the voice over IP communication, and none of your phone calls would sound very good. To resolve this issue, we can put our voice communication on one VLAN and put our data communication on the other VLAN. But of course, we're using a single wire to connect both our phones and our computers, so we can use VLAN technologies to do that within that same cable through the use of trunking. This requires you to use a switch that will recognize that you're connecting both a phone and a computer at the same time, but once you're using the right equipment, this becomes a relatively straightforward process. So now with this switch configuration, we can assign our phones to be VLAN 200, assign our computers to be VLAN 100, and send all of that traffic to our switch, where it will be able to break those two apart and put them on the correct VLAN for that particular use. This means we can now download as much information as we'd like from our computer while we're on the phone communicating with others, and be able to perform both of those seamlessly.
What's a threat actor? There are 7, and I can name them. Look, I used to think IT security was just like passwords and maybe locking your screen. Then I started the Dion Security Plus course, and I swear I started seeing everything differently. And I can't even open public Wi-Fi now without doing a full risk analysis in my head. I see attack surfaces, I see misconfiguration. It's wild. It's like someone handed me the blueprint for how networks actually work, not just tech terms, systems thinking. And the best part, I'm not memorizing. I get it, because their labs and practice tests make it click without even trying. Now I hear port 22 and I don't panic. I smile because I know what it is and I know how to protect it. Security Plus didn't just help me pass, it gave me a whole new mental model for tech. I see stuff now that I used to miss completely. If you want to work in IT and not be lost 24/7, Dion's course is the move. It literally changed the way I think.
When the night has come, and all the land is dark, and the moon is the only light you ever see. No, I won't be afraid. No, I won't shed a single tear. Just as long as you stand by.
When you're configuring a router interface, a switch interface, or an interface that's in your local computer, there are a number of options available. In this video, we'll look at some of those interface configurations. We can start with the basic connectivity that we have to the network. When we plug in an Ethernet cable, there are a number of Ethernet settings we need to consider, and two of the most important are the Ethernet speed and the duplex. The speed is obviously going to be how fast this connection is going to run. This might be a 10 megabit connection, 100 megabits, 1000 megabits, which would also be 1 gig connection, 10 gig, or even faster. We have to be sure that this configuration is the same on both sides. So if we have a computer that's connecting to a switch, The speed on both of them has to be configured the same. In many cases, we would set this to automatically configure itself. So you can simply plug in any device and the switch will automatically adjust to the configured speed. The other option we might have available is either half duplex or full duplex. In most cases, this is also set to automatic, but if you do set these manually on both of these devices, you have to make sure that both of them are set to be the same. If you have the speeds mismatched on both sides, the connection will not work at all. You'll never get a link light. But if you mix the duplex configuration, where one side is set to half duplex and the other side is set to full duplex, you'll find the connection does operate, but you'll notice that it is not quite as efficient as it should be. And in fact, you'll have very poor performance if you start putting a lot of traffic over that link. This is why one of the initial configurations we'll look for when we're troubleshooting Ethernet is the speed and the duplex, and make sure that they're the same on both sides of the connection. If those match, then we'll shift our focus to the Internet Protocol, or the IP configuration for that interface. This might be an Ethernet connection, it might be a VLAN config, we might be setting up management interfaces, and all of these will need an IP address, a subnet mask, a default gateway, and perhaps other IP configurations as well. These will usually be values that have been assigned by a network administrator. So we'll want to configure and make sure that the IP address, subnet mask, default gateway, DNS settings, and everything else matches the configuration that we've received from our admin. If this configuration doesn't match what we've been given, let's say we've used a different default gateway IP address, or we put in the incorrect subnet mask, then we may find that we're not able to connect to other IP devices on this network. Fortunately, this is a relatively easy configuration to validate. We can simply look at what we've been given and look at what we've configured in the system and make sure that both of those match. Another useful configuration, especially between switches, would be one for link aggregation. This is sometimes referred to as port bonding, or you might see it abbreviated as LAG for link aggregation. This means that we are connecting multiple interfaces together on these two devices, which normally we would not want to do because we would be creating a loop. But if you've configured all of those interfaces as link aggregation, the switch will interpret them as one very large connection rather than 4 individual connections. So if all 4 of these were gigabit Ethernet connections between this switch, we would configure those as lag, and you now have 4 gigabits of throughput to be able to communicate between those two devices. Some switches will support an automatic configuration of this link aggregation using a protocol called LACP. This is the Link Aggregation Control Protocol. This allows you to simply configure the interface as LACP, plug in the interfaces, and all of the underlying link aggregation configs will automatically configure themselves between those two devices. If you were to capture traffic between these two devices, you would see LACP traffic being transferred from one switch to the other. To be able to have the most efficient communication from one device to another, we need to be able to send packets across that will not be fragmented along the way. Since we don't always know what networks are located between the two devices, there may be times when our data is fragmented and therefore is less efficient to transfer across the network. Fragmenting a packet tends to slow down the overall communication, and if we lose one of those fragments, then we have to resend the entire frame again. Normally, the determination of the most optimal MTU, or maximum transmission unit, is done automatically when you first connect to a device. But sometimes filtering and firewalls won't allow the automated process to work properly, and you may need to manually configure an MTU on your system. On some networks, we're not trying to minimize the size of our communication. Instead, we're trying to maximize the size of our frames. And one of the ways we can do that is through a method called jumbo frames. Ethernet frames, by default, are 1,500 bytes in length. If we're transferring large amounts of data, we may want to increase the size of those frames to make the communication that much more efficient. And with jumbo frames, you can increase the size of an Ethernet frame up to 9,216 bytes of an MTU. On many devices, you'll find that they'll use 9,000 as the accepted high end of a jumbo frame. In fact, here is the configuration from my computer. It says that I can configure frame sizes on my network to be between 1280 and 9000 bytes. This means I can transfer a single frame that contains the same amount of information as 6 normal frames on the same network. This means there are fewer packets to have to switch or route through my network, and I can transfer much more in a shorter amount of time. The challenge, though, is all of the devices that are in that communications path must understand jumbo frames. So all of your switches, all of your routers, and the other devices you're communicating to have to also be configured to use these jumbo frames. If there is any device in the middle of this communication that doesn't understand jumbo frames, then they will drop these frames and you won't be able to communicate to that device at all.
Tonight, Phil's 4-year-old asked, why is water wet? It took Phil buckets of water, puppets, and 3 hours to answer. Let the frosted greatness pat you on the back. When cereal hits the spot.
If you had 2 switches and you connected them together with an Ethernet cable, and then you connected another Ethernet cable to those switches, you would create a loop on the network. This means an Ethernet frame would loop around that particular connection until you disconnected one of those cables. There's no mechanism at the MAC address level.
All right, everybody, welcome back. Welcome back. As people start coming in at 10 after, we will continue giving you the time that you need to dig into your studying and or your courses that you need to complete. So that's what we'll continue to do for the next hour or so.
Seconds until people start calling the help desk stating that the network is down. Fortunately, this is relatively easy to resolve. You simply go back to the switch where you plugged in that cable, you disconnect the cable, which removes the loop from the network, and now everything is back up and running. But of course, we're not always standing in the data center ready to plug or unplug a cable from a switch. We need some type of automated method to recognize a loop on the network and to prevent those loops from occurring. Fortunately, we have a standard that's able to recognize and prevent loops on a network. This is the IEEE 802.1d standard, one that we call the spanning tree protocol. Spanning tree can configure interfaces on our switch in a number of different ways. It may configure the switch port to be blocking, which means it's not going to forward any traffic. This is commonly used to prevent loops on a network. If we were to plug in that second cable to our switch, Spanning Tree would recognize that a loop was being created and it would cause one of those interfaces to be in a blocking state. The listening phase is used by Spanning Tree to clear out existing tables and restart the process. It's going to go through a learning process where it listens to understand where all of the other switches might be and if there might be any loops on the network already running. And then it will configure an interface to be forwarding, which means traffic can be transmitted through that interface, or will configure an interface to be blocking. We might also have interfaces that are administratively disabled. Those obviously would not participate in this spanning tree process. Here's a network that is already running spanning tree, and there are a number of switches. They're identified as bridge 1, bridge 6, bridge 5, and so on. You can see there are 5 of them in this particular design, and you can see that many of these switches are connected to each other, and if we didn't have spanning tree running, there would be a loop on this network already. But on this network, we already have spanning tree that's operational, and it has configured a number of different interfaces. There are 3 different types that you can see on the screen. One is the root port, or RP. This is the interface on a switch that is connected ultimately to the single root bridge on the network. There's also a designated port, which would be any other port that can forward traffic, but is not the port that is connected directly to the root bridge. And there are blocked ports. These are ports where Spanning Tree has disabled that port from sending or receiving any traffic. You can see on this network that bridge 21 has a blocked port and bridge 11 has a blocked port, and those have been blocked so that there is not a loop on the network. If we were communicating from bridge 11, you can see there's a single root port, and you can follow that all the way back with those root ports to the final root bridge. The designated ports are also available to be able to send and receive traffic. In this scenario, let's say that we're on network A and we've been communicating with a device on network M. You can see that we can communicate through bridge 6, which has a designated port and a root port that allows us access to network M. But what if there is a problem on this network and we lose connectivity between network A and bridge 6? Now we need some other way to communicate to network M, but as you can see, there is a blocked port on bridge 11, so we would not be able to communicate through that connection. Fortunately, Spanning Tree recognizes that we have this disconnection, and it begins clearing out the existing configuration and relearning the topology of the existing network. Spanning Tree has changed bridge 5 so that the root port is now on the other side, and it has removed the block port on bridge 11, allowing us on network A to be able to now communicate all the way through the network back to network M without having another loop on the network. On many networks, we do talk about enabling Spanning Tree and making sure that our Spanning Tree configuration is turned on inside of our switches, but in reality, these days, we're probably running a newer version of Spanning Tree called the Rapid Spanning Tree Protocol. This standard is the 802.1W standard. In the original Spanning Tree protocol, it might take 30 to 50 seconds for the convergence process to occur. And on today's networks, that is a very long time to wait without any type of connectivity. With Rapid Spanning Tree Protocol, this convergence process goes down to about 6 seconds, which means anytime there's a disruption on the network, we can be back up and running relatively quickly. Fortunately, this Rapid Spanning Tree Protocol is backwards compatible with the original Spanning Tree, so if you have a mixed set of devices on your network that support one or the other standard, you can run them all at the same time. Fortunately, Rapid Spanning Tree Protocol works very similar to the original Spanning Tree configuration. It simply operates much faster. There are some shortcuts and other configuration settings within the Rapid Spanning Tree Protocol, but it has such familiarity that if you understand Spanning Tree Protocol, it will be very easy for you to understand the details of Rapid Spanning Tree Protocol.
Now we gotta go help people customize and save hundreds with Liberty Mutual. Leva, where's the golf cart? There it is. Only pay for what you need. Liberty, 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 liberty.
Dear Savvy, who says you can't have it all? You've got the tech, you've got the drive, and now you've got Toyota value. Toyota, let's go places.
We've become so accustomed to wireless networks being available that we often forget that there's a lot of work that happens behind the scenes to create these wireless connections. This work is done primarily by the Institute of Electrical and Electronics Engineers, or the IEEE. There's a committee in the IEEE called the 802.11 Committee, and that is the committee that focuses on creating worldwide standards for wireless networking. In the past, we've referred to the standards name to be able to describe the network. For example, we'll describe 802.11ac, 802.11ax, or 802.11be. The IEEE committee realized that these numbers and letters combinations weren't very appealing for most people. So
Oh, Linux Tech, I'm just now seeing your message, but I appreciate it, and I appreciate you stopping by. Stop by anytime and leave a message or leave a like on the video. But I appreciate you stopping by. Stop by anytime.
Major releases of the 802.11 wireless standards are released. They will also increment those Wi-Fi numbers. So in the future, we should see Wi-Fi 8, Wi-Fi 9, and so on. There are a number of technologies used by 802.11 wireless networking, and the first is the frequencies that are in use. 802.11 commonly uses 2.4 gigahertz, 5 gigahertz, and 6 gigahertz frequency ranges. Sometimes there's a combination of those. You may have an access point that supports both 2.4 and 5 gigahertz, and some access points may support all of those frequencies at the same time. Instead of having to memorize individual frequency numbers, the IEEE has created groupings of these frequencies known as channels. These channels help us easily understand what frequencies we may be using. For example, on this access point, we're using both the 2.4 gigahertz range and the 5 gigahertz range. The 2.4 gigahertz range is using channel 6, which is centered on 2.437 gigahertz, and the 5 gigahertz band is using channel 44, which is centered on 5.220 gigahertz. You can see that referring to this as channel 6 is much faster and more efficient than saying that this particular access point is centered on 2.437 gigahertz. The amount of frequency that we use is referred to as the wireless bandwidth. And when I say that channel 6 is centered on 2.437 gigahertz, there's actually more frequencies that we're using for that single channel. Different frequency bands have different sizes of bandwidths that can be used, but it's very common to see 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz bandwidths. Here's a diagram that shows the 2.4 gigahertz range, the 5 gigahertz range, and the 6 gigahertz range that's used by 802.11 wireless networks. We'll start with the 2.4 gigahertz spectrum. You can see there are 3 non-overlapping channels in that particular range, and it's using the 20 megahertz bandwidth to describe those 3 channels. Next is the 5 gigahertz spectrum, and you can see there are many more frequencies available in the 5 gigahertz range. You'll also notice that we might use different bandwidths depending on the access point that we're using. So we might use anywhere from 20 megahertz to 160 megahertz, and you can see the ranges that are available for those particular frequencies. And in the 6 gigahertz range, we have even more frequencies available, giving us options to be able to transmit and use these wireless networks without conflicting with other wireless networks that might be nearby. As you can tell, there are many frequencies available to choose from for your wireless networks, but not every frequency is going to be the best one to use. There may be differences in the environment where you happen to be, where one frequency might work better than the other, or there may be other access points that are already using certain frequencies. You might also be using older devices that aren't able to communicate on the 5 or 6 gigahertz ranges and may only be able to communicate on 2.4 gigahertz frequencies. But if you have a modern wireless device, you might have options. Your phone, for example, may be able to support 2 or more different types of frequencies. It just needs to be able to choose the optimal frequency for where you happen to be. Your access points can be set up with a feature known as band steering. This allows you to specify how the users might be able to use the frequencies in the best possible way. For example, you might have a user that has a mobile phone, and that phone can support either a 2.4 gigahertz connection or a 5 gigahertz connection. And you might have access points that also support both of those frequencies. So which frequency does your phone choose when it's connecting to that access point? If band steering is not configured in the access point, the device will simply use the one that has the best possible signal. Sometimes that best signal will provide you with the best throughput, but that's not always the case. And you may find that you get better throughput using a different frequency, even though that frequency may not be the one that has the strongest signal. If band steering is turned on, the administrator of the access point can determine what frequency a user will choose if they have a choice. For example, if a user is connecting to an access point with band steering enabled, and that device can support either 2.4 gigahertz or 5 gigahertz, you can force it or steer it into using the 5 gigahertz frequencies by default. One of the challenges with these wireless networks is that each country makes its own decisions about how this wireless bandwidth is to be used. For example, in the United States, we have the Federal Communications Commission, and they are responsible for managing all of the frequency allocations in the US. Of course, the FCC can't control how other countries manage their frequencies, but they do work very closely with other countries around the world to make sure that everyone is properly managing these very important frequencies. Another challenge with this is that we are coming up with new technologies and new ways to use these frequencies all the time, and we sometimes have to make sure that different services can use similar frequencies without any type of conflict. The popularity of these wireless networks has almost required that all of these countries work together to come up with standards that everyone can agree on. A good example of these organizations working together can be found in the 802.11h standard. This adds a number of interoperability features to 802.11 wireless networks so that you can have many different wireless networks in one area, but still allow all of those networks to work together. There are a series of guidelines for wireless communications that are published by the International Telecommunications Union. The ITU provides a worldwide approach to managing these many different wireless technologies. One of the things that is included in these standards is called DFS. This is Dynamic Frequency Selection. This allows our wireless access points to use frequencies that are not going to conflict with other access points that may already be operating. This is one of the reasons that when you turn on your wireless access point today, that you don't have to manually configure any of the wireless settings inside of that device. It automatically looks at the frequencies that are in use and chooses a series of frequencies for you that are not going to conflict with anything that may already be operating. And if something does change with the wireless environment and your access point needs to change its channel, it will tell all of the devices on that network to also move along with the access point. Another interoperability feature is TPC, or the Transmit Power Control. Traditionally, we've set the power that we would use for these wireless networks on our clients, but TPC puts the transmit power control in the hands of the access point. This means that the access point can tell a client to use less power to be able to communicate over this wireless network. This means that we can have many devices communicating at their optimal power level without having any type of conflict with other third-party services.
From hard hats to steel-toed boots, Grainger's got your safety needs covered. Literally. Shop Grainger's vast inventory of safety products. Call, click, or just stop by. Grainger, for the ones who get it done.
So there's a lot of stigma and misconceptions out there. People need to educate themselves on their options.
I think it helps having people they can relate to, like us, sharing our stories. The more they can see someone who is similar to them, the more they can start to change perceptions and stigma.
Ask your healthcare provider if Descovy is right for you.
When we think about wireless networking, we often think about connecting to an access point. But of course, you can communicate directly to another device without an access point. We refer to this as Independent Basic Service Set, or IBSS. You might also see this referred to as an ad hoc connection. This allows us to configure one device as an ad hoc connection, configure the other device as an ad hoc connection, and simply connect those two devices to each other over those wireless frequencies. You might have used this functionality when you've configured an Internet of Things device, such as a door lock or lights in your home. This is a way to connect to a device over an ad hoc connection, provide that device with information about your existing wireless network, and then have that device connect directly to the access point. And in most environments, we have an access point that many different devices are connecting to be able to network everyone together. Behind the scenes, we're using different parameters to configure this device. Two of those parameters are the SSID and the BSSID. SSID stands for the Service Set Identifier, and it's the name of the wireless network that we're connecting to. So you might have an access point with an SSID of SGC1, and when you bring up the list of all of the available access points in your area, you will see that SSID name appear in your list of available networks. Of course, this same SSID might be configured on multiple access points, especially if you have a very large home or you're in an environment where there are multiple areas of the building and you want to have wireless connectivity wherever you might be in that building. To be able to differentiate between one access point and the other, we need some type of hardware address on that access point, and that hardware address is known as the BSSID. This is the Basic Service Set Identifier. So although there is a wireless network name that we see, such as SGC1, There's also a hardware address that we normally do not see behind the scenes. In this case, this wireless access point has a VSS ID of 603 Delta 26112233. As we've already mentioned, in your home or a very large business, you may have tens, hundreds, or even thousands of access points to manage. All of these access points need to be able to work together so that as you are passing from one building to another or from one area of the building to the other, you're able to seamlessly move from one wireless access point to the other. This is often done by using the same SSID or wireless network name on each of the wireless access points. We refer to this shared network name that's used across access points as an ESSID. The E stands for the Extended Service Set Identifier. With the ESSID configured across all of these different access points, you can start on one end of the building, walk to the other end of the building, and you will be moving automatically and seamlessly from one access point to the other. Here's a configuration that uses ESSID to provide that seamless roaming from one access point to the other. In the middle at the top, we have a network switch. This switch has an Ethernet connection to an access point on the left and an access point on the right. And you can see that the BSS ID, or the Basic Service Set Identifier, which is the hardware address of the access point, is different on this access point than it is for the other. Although these are obviously two different pieces of hardware, they are sharing the same SSID. You can see it's configured as SGC1 on this access point. It's also configured as SGC1 on the other access point. As we move outside the range of one access point and move into the range of another access point, that access point will automatically pick up that we are nearby and seamlessly connect this device to that same SSID without any notification on your mobile device. This means you can continue to surf the internet, transfer files, and use the network normally, even if you happen to be moving at the same time.
New Cloud Paint Plush Blush for a pillowy, soft, sunset-inspired flush.
When you first connect to a wireless access point, you may be prompted with a screen that gives you information about the network or requires you to authenticate to gain access to that network. We refer to this screen that appears and the prompt with the authentication credentials as a captive portal screen. For this captive portal to work, there is a centralized access table that identifies individuals that are already authenticated to the wireless network. And if it notices there's a new device that has not previously authenticated, it will present this captive portal screen to the end user. On the captive portal screen, there may be a series of terms that have to be agreed to, or it may prompt for a username, a password, or some other type of authentication factor. If those credentials are entered properly, then that information is added to the access table and you gain access to that wireless network for a predefined amount of time. For example, your captive portal may be good for 24 hours, and at the end of that 24-hour period, you have to re-authenticate to gain another 24 hours of access. There are many different ways to configure security on a wireless network. If you look at the configuration of your access point, you may find that there are a number of different options that you can choose from. For example, on this access point, the security level is currently defined as WPA2 personal. This access point can also disable security. It can configure a security mode on this access point known as OWE, which stands for Opportunistic Wireless Encryption, which effectively allows someone to connect to the wireless network but prevents them from communicating directly to any other wireless device. This access point also supports WEP, different flavors of WPA, WPA2, and WPA3. An open system, of course, means there is no security, there's no authentication process, and anyone on this wireless network can communicate to anyone else on this wireless network. This access point supports WPA, WPA2, and WPA3 using a personal type of security. Sometimes you'll see this referred to as PSK, which stands for pre-shared key. This means to gain access to this wireless network, we need to provide someone with a pre-shared key that everyone will use. For example, you may be at a coffee shop and there may be a notice at the coffee shop that the pre-shared key that everyone can use to access the network is hot coffee. Of course, if you're in a business environment, having everyone share the same password for the wireless network is inherently insecure. So most enterprises will use a different type of wireless security known as enterprise or 802.1x security. This allows the network administrator to require a username, password, or some other type of authentication to gain access to the wireless network. And most people will use their own personal credentials to be able to provide that access. This means you would use the same username and password you would normally use to log into other devices in that same enterprise network. This means if someone leaves the organization and their account is disabled, they no longer have access to that wireless network. If you look at the different antennas that are used on many of today's wireless networks, you may notice a number of different styles. The style of antenna that you see connected to this access point is an omnidirectional antenna. It's a very common antenna type to find on our consumer or home-based access points. An omnidirectional antenna will evenly distribute that wireless signal on all sides of the antenna. So you can put your access point in the middle of the room, and everyone in the room will have the same signal strength as everyone else. This means you can put your access point in a centralized area, and anyone who's nearby will be able to gain access to the wireless network. But this may not be the optimal antenna type to use. For example, your access point may be in the corner of an outside room, and you're effectively only seeing a portion of that signal, while the rest of it on this omnidirectional antenna is sent to places where no one will ever connect. In that scenario, you might want to use a directional antenna where you can take that wireless signal and send it into a single direction. This allows you to focus the transmission and receiving of wireless signals to a device that may be in the corner of a room or may be connecting different buildings to each other. You'll often see these antennas measured as a total number of decibels. For example, a directional antenna may increase the performance of that signal by a certain decibels of gain. For example, you may see in the specifications of a directional antenna that it effectively increases the overall power by 3 dB. And for every 3 dB, we are effectively doubling the amount of power available. One type of directional antenna is a Yagi antenna. This is an example of a Yagi antenna. It is very directional and has a very high amount of gain. We also have other directional types such as a parabolic antenna, where multiple signals can come in and bounce into a single feed horn in the front, so it's focusing all of those signals into a single point on the antenna. This is especially useful over longer distances where you need to collect that signal and focus it into a single spot.
So let's say this is the IT career ladder. Are you stuck on the bottom rung? Greg here spent hundreds on a certification exam and failed. Now he's stuck on the bottom rung. And Mike here took Dion Training's practice exams with the Take 2 option. He passed Security Plus on his first try. And look how high up he is now on the career ladder. Dion Training's dynamic practice exams generate unique questions every time you take it, so you're prepared for everything. The practice exam draws from thousands of questions, creating a unique exam every time. This ensures you're learning the material and not memorizing it, which is necessary to pass the real CompTIA exam. Join over 2 million IT professionals who trusted Dion Training for their CompTIA, Security Plus, and Network Plus certifications. Your career is waiting in IT. Visit diontraining.com to find out more.
Wow, you finally replied to a text message from 3 weeks ago. You deserve the sweet and tangy reward of a new prickly pear raspberry Whataburger from Whataburger. Thumbs up emoji.
A nice gold tree for every small feat. What a burger.
Most of the access points that we use at home are autonomous access points. This means that the access point doesn't require any type of additional hardware or software to be able to operate. It's effectively a standalone device that doesn't rely on anything else to be able to maintain that wireless connectivity. But in an enterprise, you may not be using autonomous access points. Instead, you may be using lightweight access points. This separates the wireless functionality into the hardware that you would mount into the ceiling.
How are you doing? I don't
device are
I'm not sure what you were trying to say.
the access point is connected to. This not only allows us to have less expensive access points that we can deploy.
If you don't mind rewriting that.
To manage those devices. One standard for managing wireless access point is known as CAPWAP. This is control and provisioning of wireless access points, and it allows you as the network administrator to manage and configure all of these wireless access points from one central management station. We refer to this central station as a wireless LAN controller. It allows us to connect and view the entire wireless infrastructure from one single screen. We often refer to this as a single pane of glass. From this single management station, we can deploy new access points. We can monitor the performance of our existing access point infrastructure. We can make changes to the configuration of our wireless network and deploy those changes to some or all of our access points. And this might also create reports showing us how much of the wireless network is being used and by whom. This wireless LAN controller is often paired with the wireless access points themselves, so you're often getting the access points and the wireless management station all from the same manufacturer. There are a number of different ways to connect and configure wireless networks. And in this video, we'll look at some of these different wireless network types. One popular wireless network type, especially in home-based environments, is a wireless mesh. This is where you would have multiple access points that can all communicate to each other within a relatively close area. And then you would have other devices that are located on the outside of those access points that are able to communicate to that single access point and ultimately to the rest of the network. This meshing of access points in the middle is something that you would configure on the access point, and if you were to add additional access points onto this network, they would also be included in that same mesh of access points. Of course, this doesn't have to be access points. There are some devices that can mesh amongst each other in an ad hoc form. This allows for different options for sending data over these networks because all of these devices are now communicating to each other. And if one device leaves the network, it can automatically identify that that device is no longer there and self-heal itself to maintain connectivity to everyone who's left on the wireless network. If you only have two devices, you might want to connect them together without an access point. We refer to this type of connectivity as an ad hoc connection. This is where you would use the 802.11 wireless functionality of your device, but you would not be directly connecting to an access point. This uses the 802.11 wireless network functionality of this device, but instead of connecting to an access point, you simply connect to the other wireless device. You might also see this referred to as an independent basic service set, or an IBSS. This might be something that is a very long-term connection. If all you have are two devices, you can simply connect those two together and they will communicate as long as that connection is available. But you might be using this on more of a temporary basis. This might be used in conjunction with an Internet of Things, or IoT device, where you would initially connect to the IoT device over an ad hoc connection. This may allow you to transfer configuration details, such as the name of your larger wireless network and any security configurations that have to be included to connect to that wireless network. At that point, the ad hoc connection is then disabled and the Internet of Things device can connect to the larger access point network using those configuration parameters. Some wireless access points allow you to connect two devices directly to each other over a point-to-point mode. The point-to-point mode is commonly used to connect larger distances to each other. For example, one building connecting to another building. I've run this exact configuration between two homes, so you could have an access point in one house connected to a switch and all of the internal devices of that network connected to the same switch, and then you would have the same configuration in another home and have all of those networks now connected to each other over that point-to-point mode. Not all access points support this point-to-point mode, so you'll want to be sure that the software of the access point supports point-to-point, and you'll want to be sure that the hardware on this device is also able to transmit over that extended distance. You may, for example, require additional types of antennas to be able to bridge that gap between the access points. There might also be a requirement to change the power output between these two devices and to make sure you're using frequencies that are able to communicate over that longer distance. And perhaps the most common way to connect to a wireless network is in something called infrastructure mode. This is where you would have a centralized access point, and this is probably the type of wireless networking that you're using at home and in your office. All of the wireless devices in your home or office connect to that central access point, and you're able to communicate out to the wired network or between other wireless devices over that same access point. Some wireless access points give you the option to allow devices to communicate with each other over that wireless network, or to isolate each of these wireless devices to only be able to communicate directly to the access point and any networks beyond that access point. You'll want to check your access point to see how it's configured for these devices and make sure the proper security is configured on that device.
On your period, sudden gushes happen. Say goodbye, gush fears. New Always Ultra Thin. It's made with rapid dry technology that absorbs 3 times faster. Now cleaner, drier, fresher. Always gush ready.
The wireless networks we use both at home and in our businesses are sending private, confidential, and sensitive information all the time. And we're very concerned that someone might have access to that data, especially on a wireless medium that effectively could be tapped into and listened to by any device that happens to be nearby. One way that we provide security on this wireless network is to limit what users are able to access the network. We would commonly do this with some type of authentication method, such as a username, a password, or some type of multi-factor authentication. And of course, we want to be sure that everything sent over this wireless network is protected, so we need to add confidentiality in the form of encryption. And to be sure that we've received the correct information over this wireless network, we include a message integrity check so that we can verify the information that we've received is exactly the information that was originally sent. One of the first encryption types on wireless networks is a method known as Wired Equivalent Privacy, or WEP. Unfortunately, WEP was discovered to have some significant cryptographic vulnerabilities, so we needed to very quickly replace WEP with something that was much more secure, and that replacement was known as WPA, or Wi-Fi Protected Access. WPA was implemented as a temporary stopgap between the insecure WEP and a more secure version of WPA. This first iteration of WPA was designed to work on exactly the same hardware as that older style WEP that we were replacing, but we knew that we would need enhanced security that we would not currently have available in this initial WPA. This replacement to WPA we named WPA.2. This is Wi-Fi Protected Access version 2, and it's a version that's been around since 2004. You often see WPA2 referenced with a block cipher mode known as CCMP. If we were to spell this out, it would be counter mode with cipher block chaining message authentication code protocol, or counter/CBC-MAC. This effectively combined encryption and integrity in the same protocol. The encryption was available with AES, and the message integrity check was enabled using CBC-MAC. The update to WPA2 is WPA3. This is Wi-Fi Protected Access version 3, and it was introduced in 2018. This includes a different and more capable block cipher mode known as GCMP. This is Galois Counter Mode Protocol. This continues to use AES for data confidentiality, and we are using a message integrity check with the Galois Message Authentication Code, or GMAC. If you're planning to implement any type of security on your wireless network, you want to use the highest level of security available in your access points and on your client devices. And if you have the option, you should consider upgrading all of your devices to use the most capable security method available.
Tropic Fan Fest is back on at Tropical Smoothie Cafe. Get free smoothies every day all week with Bowler food purchase.
Olay is changing my shower game with 5 skincare benefits.
Olay Super Serum Body Wash.
A distribution frame is an area of the network where you are passively terminating cables. This usually involves punch-down blocks like the ones we see here, could be patch panels, or any other method where we are terminating those cables, usually in a data center or some other large facility. You will usually find this distribution frame on the back wall of the data center, and it's often terminating cables that are coming in for your local area network and voice communication. And although the punch-down blocks and patch panels that we have on the wall are technically the distribution,
How is everybody doing? Just want to check on y'all.
Good.
All right, I figure if y'all needed something, y'all yell at me.
Yeah.
Ryan
has probably sent a drone over my house and dropped something on my patio.
refer to the entire room where it's located as the MDF facility. The MDF is usually a single room. It's often the data center or central point of the network, and this is where we might bring in wide area network connections and punch those down, along with all of our internal local area connections as well. Since we have all of this connectivity in one place, it is a perfect testing point, especially if you need to test both your internal local networks and your external wide area network connections.
I love the
If
babies.
your network doesn't have this large set of punch-down blocks in the back, we sometimes even often refer to this central data center room as the MDF. Here's a view of one MDF. This one contains a number of different racks with computer equipment and the networking components as well. Here's another MDF. You can see a large number of punch-down blocks or patch panels that are on the single rack and some on individual racks as well, and it's intermixed with the equipment that we need to run inside of this data center. Another type of distribution frame is the intermediate distribution frame, or the IDF. Usually the IDF is in a separate floor or a separate building, and it's often directly connected to the MDF. Most IDFs these days include switches, routers, and other equipment that you need to be able to connect this area of the network to the larger MDF. You usually find this combination of MDFs and IDFs in medium to larger scale environments where you need to have many different remote rooms all connecting back to this central data center. Here's a view of what that would look like, where you have the MDF. Maybe this is where our internet connection comes in. There might be a core router and a core switch. You might even have file servers and database servers in the MDF. Maybe on different floors of the building, you would then have individual IDFs. In this case, there are two, but there might be more than that in this particular environment. And in the IDF, you might be connecting users on the floor to a central switch in the IDF, and that switch is connecting back to the main core switch in the MDF. We've already seen an example of an IDF and MDF, and one of the things that you'll notice is there are racks that are very common in each of those environments. That's because the racks that we use in these environments are standardized, and most rack sizes are 19-inch racks. They're 19 inches across in each of these, and we design our equipment to fit perfectly into that 19-inch width. You also notice that the equipment in these racks might also have different heights, and we have a standard for those heights known as a rack unit, or a U. One U would be 1.75 inches, and we can measure a different number of units based on that value. So you can easily tell somebody that we need 2U or 3U of space to be able to install a piece of equipment. And most racks, like the ones we see here, are generally about 42U in height. Although the width is standardized, the depth of these racks can often vary. There might be racks that are very shallow, or others that might support a much longer piece of equipment that you would install. Fortunately, most devices follow this standardized form. We know that if we're receiving a piece of equipment that is rack mountable, that it will most likely be 19 inches wide. We'll just need to make sure that we have a rack that is deep enough to handle that particular piece of equipment. Since we have these standard widths, we can start stacking this equipment and using every bit of real estate that we might have available. For example, this system administrator has installed a server that's about 3U in height, and they're installing another set just above it so that they can stack them one right on top of the other. Now that we have all of this equipment in the data center and it's all running constantly, it's creating quite a bit of heat. We need to make sure that we have a way to cool this data center so that all of this equipment continues to work optimally. We would do this by implementing an HVAC or HVAC system. This stands for heating, ventilating and air conditioning. This is very different than simply purchasing a window-mounted air conditioner and turning it on. There's a lot of engineering that goes to designing and implementing an HVAC system in these large data centers. For example, we not only need to make sure that the HVAC can support the amount of heat that's going to be created by these systems, we also need to make sure we have enough power to run the HVAC, and we also need to make sure this is integrated into the fire system so that we're able to turn this off automatically if a fire is detected. One thing that you'll notice in a data center is that the different aisles of the data center may be designated as a hot aisle or a cold aisle. This hot and cold aisle is an important designation, especially as we're installing new equipment into the data center. We want to be sure that we're installing the equipment in a way where the hot air is being blown into the hot aisle and it's pulling in cold air from the cold aisle. Here's a cross-reference of a data center. On the left and right sides, we have our HVAC system, and in this particular environment, the cold air is going under the floor, and the hot air is being pulled out of the ceiling. The cycle starts with the HVAC creating the cold air, and that cold air is going underneath the floor in this raised floor environment. There are vents and holes in the floor that will allow the cold air to flow into a cold aisle. This is often the front of the servers, and the servers are pulling in that cold air to cool the inside of the server itself. Once that air is heated up, it will be sent out the back of the server into a hot aisle, and that hot air is going to rise into the ceiling, where it will then be pulled back into the HVAC, recooled, and the entire system repeats again.
Confused about which IT certification to get? Let me map your path to career and salary growth. The CompTIA trifecta is your foundation for IT career success. First, A+ validates your essential hardware and troubleshooting skills. Network Plus proves you understand connectivity and network security, which is critical for any IT role. Security Plus is where your salary potential really takes off, demonstrating your cybersecurity fundamentals and making you eligible for government contracts. Complete this trifecta and you've built the foundation that will take you anywhere.
Here's a data center where we can see both the hot aisles and the cold aisles. You'll see the cold aisles are covered with this plastic to keep that cold air inside, and the hot aisles would be the ones on the outside without the plastic. You'll also notice this is a bit different than the previous diagram because there is a concrete floor and there's no way to have a raised floor in this environment. So it looks like they're blowing the cold air directly into the cold aisle from above. It's being pulled through into a hot aisle, and then it goes back into the ceiling where the entire process repeats. When we install network cabling, one of our goals is to not move or touch that cabling again. We want to be sure that once it's installed, we can trust that that cable will always be working optimally. One of the things that we'll commonly do is have all of the desks that are on a floor of a building all have single runs of wire all the way back to an IDF. Inside of the IDF closet, we'll have a patch panel, and commonly we might have a patch panel with a 110 block where we will punch down those wires onto the back side of the patch panel, and on the other side of the patch panel will be the traditional RJ45 modular connectors. This means that if we need to connect any user on the floor to any switch on our switches, all we have to do is run the appropriate cable from the RJ45 connector. We no longer have to touch any of the cable that's running from the back of this patch panel to the end user's desk. So we can begin installing all of the connections we need through these patch cables from the patch panel itself into the switch that we might be using. This also allows us to address any type of moves, adds, or changes. If someone out on the floor moves to a different desk, we can simply move where their patch cable happens to be and plug them into a different connection. And of course, if we hire new employees and we want to make sure that they have the correct network connectivity, we don't have to run additional cables because we've already run those cables. All we have to do is add new connections from our patch panel to the appropriate switch connection. Here's what this patch panel looks like in our IDF. You can see on this side of the patch panel, we have the RJ45 connections. And we're coming out of those RJ45 connections and we're plugging them into the switches that are directly underneath. This means we can keep all of those cables in place between the patch panel and the desk out on the floor. All we have to change are the internal connections inside of our IDF. Here's another view of a patch panel. This one is connecting from the patch panel directly to the switch that's above it. And notice there are numbered connections on that patch panel, so we know exactly which desk we're connecting or disconnecting. There are similar but slightly different configurations for fiber optics. This is a fiber optic distribution panel where we're bringing in fiber runs from another building or another floor, and we're bringing all of those back to connections that we have access to on the distribution panel. One of the important characteristics when installing fiber optics is making sure that we don't exceed the bend radius. And you'll notice in this distribution panel that we are looping together in a very large loop the fiber to make sure that we don't break the fiber by bending it too far in the panel itself. And it looks like in this distribution panel we have some additional fiber that is wrapped around. We refer to this as a service loop, so that if we need to move this distribution panel or add additional fiber, we can simply extend it with the fiber that's already run. This gives us flexibility in the future to be able to make changes without having to rerun a very expensive fiber optic connection. In some of the previous pictures of the data centers, you saw that some of the racks were open, but there were some racks that were completely closed that had locks on the front of the rack. This is not uncommon in any type of data center because it allows the system administrator a level of additional security and control over the components inside of the rack. We'll often install these racks side by side directly to each other to optimize the space that we have in the data center. And it's not unusual to have a door on the front of the rack where we can have a lock and a way to prevent others from gaining access to the equipment inside of the rack. Here's a good example of racks that are completely locked up. You can see in this case that we do have ventilation in the front. There's often ventilation in the top and the bottom as well, so that the equipment inside is able to be cooled properly. Here's a closer view of these racks. You can see that each of these racks has a handle with a lock.
All right, everybody, let's get our last break in for today. I'll see you at 10 after.
Transparency in the supply chain is no longer optional. It's essential. Today's global supply chain is more complex than ever. Businesses must now trace product life cycles digitally and be prepared to comply with digital product passport requirements, presenting a significant challenge in gathering and digitizing data across multiple tiers. Regulations like the EU Deforestation Regulation, US UFLPA, the upcoming EU Digital Product Passport, and more are necessitating multi-tier transparency, requiring companies to have visibility across all tiers of suppliers. Consumers want transparency. Brands need traceability. Governments demand accountability. And organizations face increasing pressure to ensure compliance across all levels of their supply chain. To effectively address the demand for enhanced multi-tier transparency, you need a robust supply chain network solution. This is where NextTrace comes in. NextTrace addresses these evolving challenges, collecting data and creating a digital product identifier that helps our customers along their journey to trace and verify every material and every component in every product in one place. With NextTrace, you can automate product traceability down to the lot and serialized item level. By leveraging advanced AI capabilities, our powerful lot crawler technology scans and collects information specific to the materials and components involved in making the finished goods. RFID scan and pack technology collects and associates the individual serialized items to the trace materials. Powered by Infor Nexus's multi-enterprise supply chain network, data entered by a supplier in one tier can flow to the scores of suppliers in the next tier, eventually to hundreds of brands and millions of consumers. When it comes to traceability, supplier participation is critical. But with the amount of new data and partners required to make multi-tier traceability successful, traditional data integration methods, such as point-to-point API or EDI, are often impractical.
NextTrace takes a supplier-centric view, making it easy to upload tracing data using our smart import technology. Suppliers can simply export data from their existing systems and upload it directly to NextTrace. NextTrace then uses advanced AI to map their data to the required fields and remembers that format the next time it's imported, lowering the time and effort needed to trace and reducing costs for the suppliers. NextTrace is powered by the Infor Nexus network, connecting you to a pre-existing ecosystem of over 94,000 plus organizations globally. With this vast network, onboarding your suppliers is quick and easy, and collaboration happens in real time on a single platform. When combined with other Nexus products, NextTrace can enforce validations when goods are being packed, or even stop payment to your finished goods suppliers if they have not complied with your tracing requirements. As a leader in supplier visibility and collaboration solutions, Infor Nexus is built for managing complex supply networks. Combining advanced AI with unparalleled data quality and collaborative capabilities, the single instance Infor Nexus platform spans all tiers of the supply chain, meaning that both buyers and suppliers need to only log in once to collaborate on and manage all aspects of their supply chain, creating greater efficiencies and value whilst ensuring smooth multi-tier collaboration across all parties. With NextTrace, you're not just meeting today's regulatory requirements, you're staying ahead of tomorrow's. Gain better visibility to the flow of goods in your upstream supply chain, anticipate problems before they happen, reduce risk to your brand reputation, streamline supplier onboarding, and ensure your products are compliant with the latest global regulations. Traceability realized. Learn more about Infor Nexus NextTrace and request a demo at infor.com/Infor-Nexus/sustainability.
PIF's annual report illustrates sustained growth and further economic transformation, as well as its commitment to transparency. Assets under management were up by 19% as of the end of 2024, reinforcing PIF's position among the world's largest and fastest growing sovereign wealth funds.
The report shows that PIF continues to deliver on its mandate and drive economic transformation in Saudi Arabia and globally. PIF financial position was also recognized internationally in 2024. Moody's upgraded PIF credit rating from A1 to AA3. PIF also rated A+ by Fitch with a stable outlook, further validating its robust credit profile. Globally, PIF investments are serving strategic objectives by growing and diversifying assets and retail. PIF has formed partnership with innovative companies, investment managers, and influential investors, and invested in cutting-edge technology that is shaping the future of global economy.
PIF is driving the digital transformation forward by leveraging cutting-edge AI tools and innovating automation solutions, as well as advanced data and analytics to boost investment performance and optimize operations. PIF has developed one of the strongest governance frameworks among global investment institutions that extends across the PIF ecosystem at multiple levels to guide its investment strategy locally and internationally. PIF follows a governance framework that encompasses all its activities to ensure strong, transparent, and informed decision-making.
In this video, we're going to talk about power, and an important thing to remember is that you should never put yourself in a position where you will be able to, in some way, come in contact with any type of voltage. You want to be sure that when you're working with the device that you are always disconnecting from the power source before ever putting your hands or any part of you near that particular component. Even when you disconnect from the power source, you should also keep in mind that some devices will store a charge in capacitors. Older CRT monitors, laser printers, and other devices can easily shock you even when they're not connected to a power source. Your goal should never be to connect any part of your body to anything that is continually being energized. For example, example, you should never connect yourself to the ground wire of an electrical system or anything else that might have some type of voltage go across it. If you respect electricity, you will have no problems keeping yourself and others around you safe as you're working on these devices. When you start looking into the electrical specifications and the design of electrical systems, you'll see a lot of different terms being used. One of those is an ampere. We often refer to this as an amp, and it's often abbreviated with the capital letter A. This value measures the rate of electrons that are moving past a particular point in a single second. You'll often hear electricity compared to a water hose, where electricity flowing through a wire is very similar to water that may be flowing through a water hose. The amount of water that you can fit through a hose will depend on the diameter of that hose, and the diameter would be the number of amps. We also measure electricity in terms of voltage. This is often abbreviated as volt or the capital letter V. This is describing a pressure of electricity flowing through a particular wire. If we go back to our hose analogy, as we are turning the water on, we are increasing the amount of pressure of that water through the hose, and as we increase the pressure, we are increasing the voltage. For example, you'll often see electrical systems described as a 120 volt system or a 240 volt system. And if you need to describe how much power is being used, we would describe that as a number of watts. You'll often see this abbreviated with a capital W. We can calculate watts by multiplying the number of volts times the number of amps. For example, if you're connected to a 120 volt power source and you have a device that is using 0.5 amps, you are using a total of 60 watts. The type of power that we usually get from our wall outlets is alternating current, or AC. AC power is relatively easy to distribute over long distances, so it is perfect to use for bringing into a home or an office. You'll often see alternating current abbreviated as AC, and it's often represented as the wavy line. This wavy line demonstrates the directional change of this power as it's moving through the wire. That up and down frequency of that wave is different depending on where you happen to live. If you're in the US or Canada, we commonly see 110 to 120 volts of alternating current, and it's usually running at a frequency of 60 hertz or 60 cycles per second. If you're in Europe, it's common to see 220 to 240 volts of AC current, and its frequency is 50 hertz. Our electrical components often use DC power to operate. This is direct current, where all of the current is moving in a single direction with a constant amount of voltage. This is often abbreviated with a DC, and the symbol for direct current is this solid line on top with the multiple lines across the bottom. This is why when we look on the back of our routers, our switches, and our other devices, we often see that we're plugging into a wall outlet with this alternating current, and we are converting that alternating current to direct current using the power supplies that are in those devices. This conversion may be occurring in power supplies built into the device, or it may be in the power cord that you're using to connect that device. And obviously, as an information technology professional, power is one of the most important components we have. None of these systems would work without this power source, so it's important to consider how our switches, our routers, and our other devices will continue to operate even if there is an interruption of that power. One way to protect yourself against a power outage is to use a UPS. This is an uninterruptible power supply. This is usually a device that is connected to our power source, and inside of this device are a number of batteries that provide us with additional power if we lose that main power connection. This can also help if the voltage on our line tends to drop a bit. We refer to that as a brownout. And if the voltage tends to spike or go much higher, we refer to that as a surge. The UPS will even out that particular surge or brownout and provide us with the power we need to remain up and running. There are a number of different types of uninterruptible power supplies. One of the least expensive are the offline or standby UPS, which is simply waiting for the power to go out before it kicks in. As you can imagine, there's a small amount of time where there would be no power available to your systems, and often with switches and routers, that small gap of time is enough to cause that device to reboot. One step up from that is the line interactive UPS. If you happen to have brownouts and your voltage begins to drop, the line interactive UPS will begin to increase the amount of power provided to be able to compensate for that drop. But many data centers prefer to run an online or double conversion UPS where you are always running from battery power and the batteries are constantly being refreshed by the power source. If you lose the power source, it has no effect on the systems that are connected to the UPS because they've always been running from that primary battery power. There are many different types of UPSs with many types of features. There are some that can automatically shut down your system if the batteries happen to become very low. Some of them have a higher battery capacity than others. The number of outlets on the back of the UPS can vary, and some of them have additional interfaces to plug in phone lines or cable modem connections. Another useful power component is a PDU. This is a power distribution unit. And although it looks like a normal surge suppressor, these are actually relatively intelligent devices that allow us to remotely connect to the device, manage each of those interfaces, and even allow you to power off and power on a device from a remote location. You can see this one is a rack mountable unit, and we would put that in our rack and connect our routers and switches to these interfaces. There's also an Ethernet connection. We would assign an IP address to this device. Inside is a web server, and that allows us to connect and manage this device from wherever we happen to be.
Why do growing businesses love working in Slack? Let's ask Christy at RE Bikes.
Running things in Slack saves me so much time.
AI summaries save 97 minutes per week. What say you, Rox from Gosney?
Slack helps us build community, it helps us build connection.
Your partners, vendors and customers all in one place. Take us on home, Ashley from Caraway.
If we didn't have Slack tomorrow, I would explode.
Well, let's not let that happen. Visit slack.com/podcast to get 50% off Slack Business Plus.
In the United States and indeed around the world, we have many different data centers that are operating 24 hours a day, 7 days a week. It is estimated that approximately 2% of all U.S. power consumption is used by these data centers. Much of the power we use in these data centers is to manage the environment where all of this equipment resides. This allows us to manage the humidity, the temperature, and other environmental controls. Managing humidity in a data center can be a bit of a challenge. If you have a high humidity, then you've got condensation, and having any type of water in a data center is never a good idea. If your humidity is too low, you could have excessive static discharge, which is also potentially harmful to the equipment. Many industry guidelines put the ideal humidity levels somewhere around 40 to 60%. This is high enough to prevent any type of static discharge, but low enough to prevent any type of condensation. This can vary a bit depending on the geography, but these humidity levels tend to be the average that you'll find in most data centers. A lot of this power also goes to keeping the data center cool. As this equipment is running, it's generating heat, and all of that heat needs to be cooled down. There is an optimal temperature range, and many data centers are trying to keep the temperature somewhere around 64 to 81 degrees Fahrenheit. The cooling equipment in our data centers is constantly working to keep the temperature at that range. But of course, there are external influences that can affect the temperature inside the building. For example, the outdoor temperature may increase or decrease, and that may add additional load to the cooling systems. You might also find that as your system load increases and you're creating more heat from the systems inside of the data center, that we will need to add additional cooling. Most data centers will have a well-engineered heating, ventilation, and air conditioning system. This is an HVAC. This HVAC system is designed to maintain a particular humidity and temperature level. Most of these HVAC systems have sensors that are located throughout the data center, and they're working to make sure that the same temperature and humidity is the same across the entire data center. Another important concern for data centers is what you do if there is a fire. Data centers contain a large amount of electrical equipment that are in a very large area, so we need to be sure that we have some way to suppress any type of fire. Normally, we would use water to be able to control a fire. But in an environment such as a data center, when you have this much electrical equipment, you'll want to use other means for fire suppression. If you were to look into the back of the data center, there's probably a tank that contains some type of inert gas or chemical agent that is designed to either suppress the fire or remove any type of oxygen from the air. If somebody pulls the fire alarm, all of those chemicals are dispersed throughout the entire data center, and although this may cause damage to the equipment, it will prevent a fire from spreading. You'll often see these fire suppression systems integrated with the existing HVAC. This means that if a fire is detected, the HVAC system will shut down and prevent any type of oxygen from feeding that fire.
Audra Rewards introduces the industry's most expansive global rewards marketplace featuring millions of unique products and experiences, all delivered seamlessly through a single powerful solution. With maximum choice and unmatched flexibility, it is designed to create personalized, dynamic experiences for any audience. This is Audra Rewards. Schedule your demo today.
Nothing smells like regret more than the smell of your own BO. Ugh, no thanks. That's why you deserve a deodorant that keeps you smelling fresh. Your One True Dove, aluminum-free deodorant.
One common type of network documentation is the network map, and there are different types of network maps that you might want to create. One type is a physical network map, which shows the physical layout of the equipment, the cabling, and everything in between. This is an example of a physical network map. It shows a connection in from the internet with the physical cable plugging into the internet router, which can be found at 10.1.1.1. There's a physical wire connecting to the internet firewall, and then another wire connecting to the core router, which is located at 10.1.10.1. This physical connectivity continues on through the rest of the diagram, and if you were to go into this room, you could track back that cable to this equipment using this physical network map. We can often create these network maps using third-party software such as Visio, OmniGraffle, Glyphy.com, and many others. This software can be used to create physical network maps. It can also be used to create logical network maps. Logical network maps show a higher level view of connectivity where you're not focused on individual interfaces and cables, but more on how the entire network is connected. This is a logical network map that shows a cloud connection in the middle and different headquarters buildings connected from different locations into that single cloud. Obviously, in the middle of all of this are a number of routers, switches, and other servers, but all of that is broadly shown as a single location in a logical network map. These might be good maps to use if you're planning additional locations. You can view the layout of the existing wide area network cloud and then decide where the best location might be for another installation. And if you wanted to get into a detailed view of exactly where equipment is located and what that equipment looks like, you might want to use a rack diagram. Rack diagrams are designed to give you a physical view as if you were standing in front of that rack in the data center. It's very common to have restricted access to the data center, so a documentation like this can be used for individuals who may not have that level of access into the building. You can then use this documentation to tell someone to stand in front of the rack, look about 3/4 of the way up on unit 14, and you'll see the power strip. You can even use this documentation to locate the exact rack in the data center. You might have on the documentation that this is in row 3 of the data center, and this is rack W. This gives us a way to provide detailed documentation for someone who may be standing in front of the rack when we may not be in the same building. So instead of telling someone to reboot a server that's in this rack, we could specifically say, go to unit 15 in this rack and reboot that individual server. Another useful physical piece of documentation is the cable map for your office. This would allow you to see a view of the office and exactly where the wires are installed in that facility. You'll often see one of these diagrams in the IDF or MDF. It's usually on the wall so that you can understand where these wires are going when they leave that closet. This would show you where the physical wires are running, either under the floor or above the ceiling, and you can see that each drop for each one of these is numbered. This allows you to correlate the network drops out at each individual desk with the network drops that are connected to the patch panels inside of the wiring closet. These are not just useful during the installation process, but they're also useful when troubleshooting. You can track back exactly where a wire was run inside of the building and be able to correlate that back with problems that you might be having with that particular network drop. You can also create network diagrams that combine layer 1, layer 2, and layer 3 views of the network. Layer 1 would be the physical layer, layer 2 would be the data link layer, and layer 3 would be your network layer. Here's an example of a network diagram that includes a number of switches, routers, and end stations, and we have labels here for layer 1, layer 2, and layer 3. We can start with the layer 1 connection, which shows the physical interfaces for the switches and the routers where all of these wires are connecting and providing this connectivity. We can overlay on top of that a layer 2 perspective, which now includes MAC addresses for all of these different components. And if you wanted to include IP addresses, we can overlay the layer 3 addresses so that you know exactly what IP address is associated with which MAC address, which is also associated with each physical address. Another important part of documentation is a need to track your assets. This means that we need to put tags or labels on every asset that we're bringing into the organization. This would be laptops, desktops, routers, firewalls, switches, and anything else that we're buying and installing into our network. Once we have all of these devices tagged, we can use that tag when we're referring back to a trouble ticket or some type of problem. For example, we could say that a router in the data center that's labeled with number 42 is the one that's causing this particular problem. We can also use these tags for financial purposes. We may need to track these devices over time to be able to track their depreciation. Or you may need to reference the asset tag to know when the device is purchased, which would also tell you if that device was currently still under warranty. These asset tags are usually very visible so that you can find them when you're on the phone with someone in the support team. There might be a barcode or RFID associated with this, and there might be additional information if a third party runs across this device. They'll know exactly who owns that particular piece of equipment. The asset tag that's connected to the device, the components within that device, and then the user who is using that particular device may all be combined within one single asset database. This becomes a centralized database that can be used by the asset support team, by accounting, by folks that are in the finance department, and anyone else who may need access to this data. If we need to know the physical location of a device, we can look at our asset database and see what user has been assigned to this particular component. If we then know the user's location, then we also know the location of this particular device. As we've also mentioned, we may want to use this also for warranty tracking to be able to understand when a device was purchased and what the status is of that particular warranty. And if we're tracking the number of devices, we can also track the software that's running on those devices. This can be very useful if we need to determine how many licenses we need to purchase for our organization. We can determine very quickly how many we own by referencing back our asset database. Another important piece of documentation relates to the ongoing use of
Where are you watching from?
in our organization. We would commonly track these by using
should I say what country are you watching from?
ICAM solution. This is something that can provide us with a way to plan, track, and configure the DHCP and IP address schemes that we are using throughout our company.
So let's say this is the IT career ladder. Are you stuck on the bottom rung? Greg here spent hundreds on a certification exam and failed. Now he's stuck on the bottom rung. And Mike here took Dion Training's practice exams with the Take 2 option. He passed Security Plus on his first try. And look how high up he is now on the career ladder. Dion Training's dynamic practice exams generate unique questions every time you take it, so you're prepared for everything. The practice exam draws from thousands of questions, creating a unique exam every time. This ensures you're learning the material and not memorizing it, which is necessary to pass the real CompTIA exam. Join over 2 million IT professionals who trusted Dion Training for their CompTIA, Security Plus, and Network Plus certifications. Your career is waiting in IT. Visit DionTraining.com to find out more.
Not all oral care is created equal. The Colgate Total Active Prevention System is engineered to be 15 times more effective at fighting the root cause of oral health problems. It's our best science ever to prevent problems before they start. Be dentist ready with Colgate Total.
Using IP address management, we can document what users may be using what IP.
Oh, Germany! I've been to Germany twice, and
a user with a specific IP address.
I didn't get to do much there, but
This might also give us the ability to identify any problems or
I've been there. So I'm currently doing studies in IT, so information technology, particularly cybersecurity. So I'm currently doing the classes.
This is a way to manage all of our IPv4 and IPv6 addressing throughout our
Oh yes, so I have on one of my monitors there's a particular lecture that I have playing on that, so I could learn from that as well. And it's on the internet, so it does have ads from time to time. So you'll hear the ads in the background.
You'll need some way to verify that you're getting the proper level of service. This is often done.
I'm not sure if that's what you're referring to, but yeah, if you hear something that's not pertaining to the lecture or the learning, then that's probably what you're hearing.
If you're contracting with a wide area network provider or an internet provider, you may have an expectation you'll be up and running 99.99% of the time. And you might want to have that level of service documented as part of this SLA. You can use this for any type of service level. For example, you might have an SLA that your organization will have no more than 4 hours of an unscheduled downtime. This means that your service provider will need to have
cybersecurity has to do with everything pertaining to you being on the internet, and it can start from your email, simply receiving emails. So if an advice would be if you regularly check your email, or just for prevention within your email, is to don't open emails that you don't recognize, or it could be an unrecognized link. Or if you even open up the email and the address doesn't seem correctly, then you probably shouldn't click on it, because it could be someone trying to hack into your device just by doing that. That's a tactic of cybersecurity.
Once we understand all the frequencies in use, we can then document those and configure our systems to have the minimum level of interference for all of our access points.
Another one as well, when it comes to cybersecurity, is pertaining to being protected on the internet. So you don't want your computer getting viruses or malware, getting hacked. So precautions that you can take is to install an antivirus software if you are going to be browsing sites that you don't particularly browse, or just for a precaution. And just you can keep your computer security firewall on. That in most cases will help you. But if you're going to be going onto sites or doing more beyond the regular, then you might need to get an antivirus software. But one of the biggest ones is your emails. Not clicking on emails, or if you're receiving text messages that it's unfamiliar to you, you probably just don't want to click on it. Just delete it right away. The same goes for the emails as well. And sites, when you're visiting any sites, if it doesn't have, so in the bar on the site, on the internet, when in the top where you see that small lock, it's gonna say HTTPS. If you're logging onto a site and it doesn't have the S on the HTTP, if it only has HTTP and not the S on there, it simply means that the site is not as secure. These are stuff that you particularly learn in cybersecurity. You wouldn't know unless you checked it out. So that's one way to know if a website is secure. It needs to have the HTTPS on the hand. If it doesn't have the S, then that means it's an unsecure site.
We refer to this as end of life, or EOL.
I suppose there's a lot that I could particularly get into, but these are some of the basic things that you can look for.
They may continue to provide security patches.
Cybersecurity in general is to be secure while browsing the internet.
And eventually the manufacturer of this equipment,
so you can counteract the effects of someone trying to hack into your device.
When there are no type of updates coming from a product, we refer to that as end of support, or EOS. You won't receive any patches, any updates, any new features, or anything associated with that particular product. When a product moves into end of life, we can put together a plan and a budget for replacing that product over a period of time. But when a product hits end of support, this becomes
I suppose it would be a lot for me to get into all the specifications of what I am learning particularly. But those would be the basics, the general aspects of what you need to be
maintaining the uptime and availability
be
of
looking
these
out
devices,
for.
especially when these updates are associated with stability fixes. But these might also be fixes that close security holes, which may be just as important as maintaining the uptime of the device. We often see this with operating systems, where we may receive a service pack every quarter, and we may have to install a large number of updates to these systems when we first install the OS. Many organizations provide monthly updates on a recurring schedule. This means we know exactly when the latest updates are going to arrive, and we can set up our plans for deployment around those update timeframes. And occasionally a manufacturer will introduce an update outside of the scope of that normal monthly update. This is often associated with a security concern, especially when a 0-day or some other type of significant security event occurs. It's not unusual to see updates to operating systems occur constantly across many aspects of that operating system. For example, we can have updates for Windows, Linux, our iOS and Android devices, and anything else that might be running an OS. It's very common to see these monthly updates occur for the operating systems. These might have bug fixes and security patches, but we might also be making changes to the operating system ourselves. We might be modifying user accounts and changing the way that users interact with the operating system. For example, we might increase the minimum password lengths, we might change the complexity of the passwords required for the operating systems, or we might change the way that users are able to access the operating systems, and we might deploy those updates to the operating systems on demand. We might also change the configurations of the built-in firewalls on these devices. These operating systems provide us with a way to limit where a user may visit by IP address or URL, or there might be changes that enhance the security features on that device. And there are constant changes to the embedded anti-malware and antivirus that's included with many of these operating systems. If we're managing a purpose-built appliance or a purpose-built piece of hardware, then we don't usually have access to the operating system that's on that device. And often these devices have their own operating system and configurations. We refer to this software that's running this piece of hardware as the firmware of that device. So if you're working with printers, cable modems, or other devices that have their own embedded operating system, you might be required to update that firmware occasionally to close security holes. This update may be done over the network, or it may require you to visit the device and physically connect to the device to perform the update. We know that we can't use this hardware unless the software in this device is working properly. So it's a good idea to have a plan for upgrading this that would include a way to fall back to a previous version if that newer version runs into a problem. It's often a good idea to save those firmware binaries in a safe place so that later on down the road you wanted to go back to a previous version, you would have access to all of that code. One of the challenges with managing firmware in your printers, your modems, and other devices is that these companies are very good at manufacturing hardware, but they may not be as good at maintaining the firmware that runs in those devices. An example of this would be the Trane ComfortLink 2 thermostats, where you could control the temperature on the thermostat from your phone. There were 3 vulnerabilities presented to Trane in April of 2014, but we didn't receive updates to the firmware until April 2015, and it took until January of 2016 to be able to get the final update for that device. It would be up to the security team of your organization to determine if that device should remain on the network or if you should find other alternatives instead of that thermostat. Another important aspect of lifecycle management is what you do with the device when you don't need it anymore. This would be the decommissioning process, and it's the way that you dispose of an asset once you no longer need to use it. We see this often with desktops, laptops, mobile devices, and anything else that becomes outdated and is no longer supported by the manufacturer. But there's data on that device that we want to be sure doesn't get into the hands of someone else. We need some way to sanitize the media or simply destroy the device to protect all of that data. This might also involve legal issues, especially if there's certain types of data that your organization is not allowed to destroy. So you may end up storing this equipment off-site or in a secure location until such time that it's able to be destroyed or disposed of properly. And what you do not want to do is simply dispose of this in your normal trash. Eventually someone will come across that equipment and they will either get access to the data or they'll sell that equipment to someone else who will then get access to the data. Although we often want to recycle this hardware, we want to be sure we do it in a way that protects the confidentiality of the data contained on all of these devices. An ongoing part of lifecycle management is change management. That's because we are constantly making changes in our computing environments. We're upgrading software on a switch, we're making changes to a firewall configuration, we're modifying a router table, or making some other modification to software.
Determine what
or
IP addresses
configurations. This needs to be a managed process and something that we can track, monitor, and be able to modify if we run into a problem. Most organizations will have a very clearly defined change management process. This would include how often you're able to make changes, the window that you have to be able to make those changes in an environment, the process itself for installing those changes in your environment, and then finally, a process for rolling back if you run into problems. And if your organization does not have a formal change management process, this might be difficult to implement. You need to make sure that everyone understands the importance of having a centralized change management process and that everyone follows that process before making any modifications to any device. Another important aspect of lifecycle management is how we handle ongoing service requests. This is often done through a help desk. They'll receive a phone call, they'll input the ticket into a centralized process tracking system. Those tickets will be triaged and provided to someone who can resolve the problem, and then they will close the ticket and move to the next one in the list. Almost every organization has a process tracking system, and although there are many different types of software to provide this function, they're all very similar in how they operate.
It's the final game, folks. This one wins the series. Struck out with the cheap seats. Important things aren't worth compromising. At Farmers, we offer both quality insurance and great savings. Here, take mine.
We are farmers. Bum, 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 bum.
Change is inevitable, and we need to have some type of process on our network to be able to manage all of these changes. There might be updates to operating systems. We may have to patch a series of devices. There might be updates to applications that we need to roll out. And of course, we have network devices, firewall configurations, new applications that need to be installed, and many other changes that will occur on our network. Instead of simply making a change without any processes or thoughts to what may occur in the future, we need to have a formal process for managing all of these configurations. We need to know when these changes are going to occur. We need to be able to plan for those changes, and we need to inform everyone that the change is going to take place. This documentation becomes very important if this system needs to be rebuilt, especially if there's some type of disaster and you're required to get that system back up and running as quickly as possible. Having some type of documentation that leads you from the installation of that software through all of the changes that you made will be extremely important in getting that system back up and running. When we first install a switch, a router, a firewall, and we make our initial configurations and get everything working perfectly, we now have a production configuration. This is the configuration that everyone will use when we roll out a new router. This is the configuration that will be the standard for that production system. When we install a new firewall, we have a standard production configuration for that firewall. This is not just individual configurations inside the device, but it covers all aspects of changes to that device, including all the hardware and firmware versions, any device driver updates that need to be made, and any updates to the software, especially since there are certain versions of the software that might work better or worse than other versions. This is not something that we would usually install into production to see how it runs. We would usually do extensive testing behind the scenes, make changes to all of these aspects of the system, and then deploy that final configuration into a production environment. Of course, not every possible scenario can be tested in our lab, so we need to have a plan if something was to happen in production to be able to revert that back to a previous configuration. In these situations where something does not go as designed, we need to have some type of backup that we can revert to. This applies to our firewalls, our switches, our routers, our operating systems, and anything else we might be making a change to. The standard operating procedure is commonly to make a backup of that system before making any type of change. Once you make the change, you can then decide whether that's something you want to keep in production, but if there's a problem, you may need to go back to that previous backup. Sometimes this can be accomplished by simply copying the files that will be updated during that particular change. It might be a single configuration file, but now we have a copy of that file prior to those changes taking place. We can simply copy that file back if there's any problems. If this is a virtual machine, this process can be relatively easy. You can click a button to create a snapshot of that VM that saves everything, the files, the configuration, and everything else associated with that VM at that point in time. If you run into a problem when you're making a change to the VM, you can then easily revert back to that date and time of the snapshot. This is also useful if later on you decide you would like to revert back to the previous configuration. You now have a backup that's stored either as a snapshot or as separate files that you can then revert to if you run into future problems. When we're deploying a new application, it's usually often more than a single server and a single executable. There are usually many different components that allow that application instance to operate. This might include configurations on the user's workstations, changes to the firewall, and of course the application server itself. To truly understand the scope of this application, we need to document every aspect of that application installation. This allows us to create a golden configuration that certifies that this application will work properly if all of these configurations are in place. We can also use that golden configuration as a way to verify that we are using the proper software and the correct configurations. We can create integrity checks that will compare the configuration running in production with the configuration on our baseline or golden config. If we find there are changes between those two environments, we can make changes either to the production environment to match the golden config, or we can update our baseline configuration so that it matches the new configuration in our production environment. Once we make those changes, we now have a new version of our baseline configuration, and we can use that as our integrity check going forward.
Tropic Fan Fest is back on at Tropical Smoothie Cafe. Get free smoothies every day all week with Bowler Food purchase.
Colgate Optic White's unique technology gives you a visibly brighter smile in just 3 days.
As a network administrator, you will install switches, routers, servers, firewalls, and many other pieces of equipment into your infrastructure. Once you install that equipment, how do you ensure that it's running optimally and that there are no errors or problems that you need to address? One of the ways to do that is by querying this device through a protocol known as SNMP. This is the Simple Network Management Protocol, and it is designed to provide a management interface to these devices over a standard set of protocols, regardless of who happens to manufacture that device. Usually the network team will have a central network management console, and that management console will query devices via SNMP and ask information that it would like to receive. For example, it would request from a switch how many bytes have gone into a particular interface, and that device will respond back with a particular value, and that information is stored in the management station. The query that is being made to this device is querying a number of different parameters that are stored in what is known as a MIB. This is a management information base or central database of data that is stored on that remote device. SNMP queries specific values in that database by referring to an object identifier. Sometimes you'll hear this referred to as an OID or an OID. All of this polling occurs over UDP port 161 and allows us to access any of the devices on our network and gather information about how those devices are performing. When configuring SNMP on your network management station, it may ask which version of SNMP that device is using. There are usually 3 different versions you can choose from. The first is the original.
All right, y'all ready for some flashcards?
Version 1. This provided a way to query those structured tables.
See what we can do. All right, here we go.
On this device, but it sent all of that information across the network.
Let's round out the day with a couple of questions, see how good we can fare.
With any of the transmission using SNMP version 1. A newer version of SNMP was released that we named SNMP version 2. You'll sometimes hear this referred to as SNMP version 2.
So we got some Quizlet flashcards. When you think you know what it is, even if you need to guess, guess. All right? That's how it's going to stick. All right, here we go. First one. What port does SIP use? Me and Mr. T talked about this today.
The latest version of SNMP is SNMP version 3.
How ironic.
It provides encryption and a number of different cryptographic capabilities, such as message integrity and authentication.
Well, with the ports that it uses, it tells you.
561.
There's 2 ports that it uses. There you go, Elaine. 5060, 5061. Yes, it does. That was our void. The word SIP itself meaning Session Initiated Protocol. It uses voice, video, and data all at the same time. Examples of SIP, what we're doing right now, Zoom, teleconferencing room for the kernels, SIPR rooms, right? Where they're exchanging data, telemetry, video from drones, all that stuff. That's all SIP.
This is how we're able to have hundreds or even thousands of
nice one there. Hold on, let me check that out real quick.
Information base, and we can query each of those.
Oh, I got you, Charles. You're all good.
By referring to their
I graded it.
Sometimes these object
all right, next.
are very standardized across devices.
What is SIP? I just told you. You can't forget in 2 seconds.
Yes.
That MIP2 standard.
I don't know, Charles. I think you got a better memory than that. I don't think you're going to forget.
But sometimes the manufacturer has.
So what's SIP again? Session Initiated Protocol. Yes. It is a signaling protocol initiating, maintaining, and terminating real-time sessions. There you go. Next. What is VRRP used for?
You can add that file to your network management station. At that point, you can retrieve.
I was recording it in my Mentor Rolodex. What layer is the session layer? That is the 5.
For SNMP information is to use a MIP walker. This is software that will cycle through.
Please do not throw sausage pizza away.
Pull down everything associated with the MIP inside of an individual device. This is a MIP walker on my Mac OS device called MIP Browser, and you can see
VRRP. What is it used for?
1.10.64. It's using port 161. And I configured this MIP walker to use.
Here we go.
Of SNMP.
Used for automatic assignment as available internet protocol IP routers participating in order to increase availability and reliability. There y'all go. Y'all got it. It is for redundancy. Automatic default gateways. It assists in that. Good job. Man, I thought I was going to get you on that one. Next.
See the list of those.
So what ports does it use?
Pull back a system ID
What
information,
ports?
some contact
VRRP
information, my email.
ports.
It even shows me the name of this system and how I can then correlate that back to a specific physical device. If we scroll down a bit in this list, we can even find individual variables as part of this MIP and see the individual values associated with each one of those. For example, SNMP in request has a total of
Bingo.
4.
Mr. T got it.
112. Okay.
Has a value of 1,000.
Just thinking of Armbury Group 112.
Start collecting that information over time.
Yeah.
You can begin to build out
Next.
very large visualizations of how
What port does remote desktop protocol use?
created through a series
Leah
of
got it.
SNMP queries that take place
Mr.
on
T's
a
got
daily
it.
basis. So you can see that
3389.
start to map out information such as response
All
time
right, here we go.
values, any type of errors, or anything else that might be
What
contained
port?
within that MIB.
Does. There should be
This
does.
implementation of
TFTP. We saw this in the video with East Charmer when she was configuring a switch.
network at regular
There you go.
It would be common, for example, for a
69.
to query every
And
device
what
in the
is
network
what is TF? What is a trivial file again? Somebody remind me.
But if there's a problem on that
Please.
device,
Because I forgot.
What is it? A trivial file?
For that reason, you may want to configure a different.
Yep, it is a transfer protocol used for small configuration files. Yes.
As a proactive
Yep.
alarm that is
Good man, y'all are on it. Here we go. Next.
without the management station needing to pull that.
True or false?
These SMP traffic
802.11 AC is known as Wi-Fi 5.
switch or router to look for a certain number.
I taught you this trick on what, 1201?
A large number of errors, for example.
Charles says true.
That device will
True. Brian says true. Mr. T says true. Michael says true. Here we go. We got the majority. Bam! Good job. Woo. Next. True or false? AX is Wi-Fi 6.
That MIB walker to be able to gain access to that system. That value is referred to as.
Everybody, Jesus says true. Aaliyah says true. Michael says true. Elaine, everybody. Bam. You are correct.
Multiple community strings within a device, so it's not unusual to have a
What is the frequency band and max data rate for 802.11? Bravo!
Strings are relatively simplistic, and they're only used for S&P version 1 and S&P version 2 or version 2C.
The max frequency.
What's the data rate?
2.4.
Of S&P, and in S&P version 3, we use a
11
username and
MB.
password that is sent across the network as a password hash. This is a
Ooh, y'all seem so sure.
Authenticate if you're running S&P.
Bam.
Probably a good idea. S&P, that the most secure
You
type
know,
of
there is a, I'm glad we're going through that because on the N10009, there's like one or two questions that may ask data rate for either cat cable or Wi-Fi.
Yeah.
It's a hot flash.
Yep.
This is a
What was the trick, Elisa? Oh, to remember it?
This is not.
Yeah.
You know what? Anybody have a trick for Leah to remember? That's what she's asking.
Oh.
How do you remember the correlation? I just kept reading it over and over and over again.
The max.
I need your trick for the last one too. Now, cat cables are easy because it started out with 10,
Yeah.
100, 100, 100. Like three categories of cat coming out the gate was 100 Mbps. I was like, woo! In 100 meters. Wi-Fi is, yeah, you really got to try to get that. All right, here we go. What is the frequency band and max data rate for 1105?
So let's talk about research projects.
I think I just gave you a way to answer for the.
Yeah, it's
That was for cat. Bam, they got it.
5 and 54.
Good job.
Yeah,
Dozens or even hundreds of articles, studies, and websites. Just figuring out
What is the frequency band and max data rate for 11G?
Well, with Gemini Deep Research, you can do hours or even days of research.
So you got A, B.
Let's say we have an assignment that involves
And
utilizing sensor technology in self-driving cars. We need to research
1 to
current
2
sensor trends and
Mbps,
present a case for which technology
2.4 gig, 2.4 gig.
navigation.
Okay, we're getting some consistent answers here.
Yeah, it's
2 point. All right, seems like everybody's unanimous on this one.
Yeah, it's 2.4.
For my robotics aspect.
There you go.
2.4, yeah.
Now there's a chart. Did I drop a chart? There's a cheat chart I can get you.
The first thing we'll get
Gives you a
back is
visual.
research plan, so we can review the methodology. If we want to edit it,
What are the frequency bands of 11N?
good to go. We'll choose start research. This is a more in-depth request, so it may take
Drop that.
Deep research.
2.4G.
There you go. It's both.
Yeah.
The reason why, so
Dives into the web.
if you get a PBQ that says you want to install new wireless access points for the company, it doesn't say anything about money's not an issue and all that. Their primary concern is compatibility for the whole company. The compatibility is you don't know what type of device that somebody's bringing in, so they can choose the band of 2.4 or 5. It accommodates everybody. So 11N would be the choice that you would want to use as a broadcasting frequencies. All right? 11N, it accommodates everybody. Correct. 6 does not do that.
So we can dig further into that.
They've made some that do it,
Part of the assignment.
but not all. So you got to read the box before you buy it. It'll tell you it's not backwards compatible.
Everything with a list of credible sources.
Here we go.
With a research assistant like Gemini.
So what's the data rate of N?
To make new discoveries. And maybe even have a major breakthrough.
Wireless access point. Uh-oh, Brian's typing fast. You got to look out for him. He sneaks it in. Like, darn it. 600.
On your network, you're probably using routers, switches.
And what helps Leah is us going through this like this, because it'll just stick.
All of these devices are running 365 days a year, 7 days.
What's the freak?
4 hours.
Get your freak on. Get your frequency on. Get your freak on. What is the freak band and maximum data rate of AC, baby?
What type of load they're seeing, perhaps log file information, and other details from each individual device.
2.4 and 5.
To authenticate properly to the device, if there are any security
1300.
concerns, or how much utilization.
We're in the gigs at this point.
in CPU or network. Many times the network
Data rate.
administration team will have a central console, and that console will roll up all of this different information.
There you go.
From many different sources.
3.5.
One single screen for analysis.
3.5. 5 gigs, 3.5. 5 gigs, 3.5.
Oh, it can go up to 1300 too.
I know. Charles was like, I'm just trying to keep up with the first one. Okay. All right. What is the theoretical max? Theoretically, it could probably push up to 5 gigs GBP. But 3.5, and that's a, wait a minute, that's not a,
This probe may be sitting in the middle of the connection using a physical tap, or maybe using
it has better security. It has the thread security. You'll still get the push to 3.5 coming through. Okay, I was thinking of something else.
And that NetFlow probe is compiling statistics based on all of the packets going across.
Frequency
The
bands
summary of all of that information is then
of
sent out to a single NetFlow collector. This means you don't have to go to separate NetFlow probes to be able to gather all of this detail. You go to the
2.4.
single collector, and you can create all of your reports from that
9.6.
one central place. The collector is
Oh,
only
I like to see what Kevin put on the end. He's trying to be slick.
but often the collector will also
What y'all say?
Yeah, 2.4.
AX.
summary views on
Yeah,
your console,
2.4
or they may
to
be able
5.
to configure long-term reports to be generated every day.
GAC.
This is a NetFlow console, and the current screen is showing a NetFlow traffic analyzer.
2.4 and
See that it
5.
contains top 10 conversations, which are ingress and egress data for all of these
All right.
devices. This is over the last hour.
Next,
You can also
what is
see the
this?
top 10 endpoints
I'm playing.
on your network. This is listed by IP address.
It's a picture of a sticky.
Yeah.
Sources of that NetFlow data.
All right, here we
You
go.
also have traffic analyzer events that are.
What is
from
the
NetFlow
first
NetFlow
flag
can also
in
summarize
the
information by port
TCP
numbers that
three-way
application
handshake?
traffic is traversing the network. These are the top 5 applications on this network.
So what is the
Things
first
like
flag?
SSL is the largest amount of traffic on this network, and then there's SQL Server, other web traffic, NetFlow UDP traffic, and port 0 traffic. All of that NetFlow information is effectively metadata that was created based on the
Synchronization.
traffic going
You're correct.
across the network.
Yep.
You can
So
also
it's
view the raw
SYN,
packets themselves using a
SYN
protocol
act.
analyzer. This allows you to see
X.
the exact
That's how you remember.
bytes sent
And I have to,
Synchronize
get, like,
acknowledgement.
cool
Yeah.
with it, like SYN, SYN.
Yeah.
Like, you gotta have it stick.
in a form that is easy to read.
All right, everybody, we've come to the final hour. It's 6 o'clock. I don't want to keep you past the time. And y'all have done good. I've been grading your stuff. Tomorrow, we're going to do a study room breakout
troubleshoot a slow application.
Leah has something to do. Is it the
All
afternoon?
of the conversations taking place over the network.
Tomorrow? Is it tomorrow?
It's during lunch. It might go like 30 minutes into class afterwards, but not for long.
Not much. Okay. Well, tomorrow afternoon we'll open up a study room, study breakout room. We'll cover anything in 1201, 1202, or if you want to talk net. So, me and Leah could jump in there for about an hour at 1400 and cover any questions. That way we got anybody that wants to peek in. But primarily, she's going to be the room running. I'm going to sit back until she looks at me and says, James, what's the answer to that? I'm like, okay. But she wants to give it a go. So, what day is the test? The test is the 30th. Oh, thanks for reminding me. We got to schedule the exam tomorrow. We don't even have this thing scheduled. Yep, we got to do that tomorrow. So we'll do that too. Any questions for me? All right, week 1 will be in the books tomorrow at 5 p.m. What you got, Mike?
The trick to remembering are those bands, the AO2 bands.
Oh, I gotta drop it, don't I?
What would you do if you were not afraid of falling?
Drop it like it's hot. Okay, I'm gonna send out a mass email. It'll be in your email.
Okay.
Look forward in the next 30 minutes. Everybody's gonna get it.
Never be afraid of falling.
All right, y'all. Have a great night and skitty hip, Captain.
All right. You guys.
Read.
So you're able to get a very detailed view across many different devices on your network by simply compiling this data into a central baseline. If your organization is using a management console